can hear you.
Perfect. Yeah.
So you're good.
Awesome. Thank you very much again.
Over.
All right. Just need to share the video. Okay, I can see that there are some remote attendees already here in the virtual room. Can you hear us here in Vancouver? At this point, somebody should open the mic and say, yeah, Michael, we can hear you. Anyone? Can you double check, Jasmine? Maybe that just to make sure that people can hear us in the Zoom room. You can hear it? Okay, great. Okay. So we should be good. Now I need to do some screen sharing and then we should be good to go. Okay, cool. I think we can get started.
Yeah. So I basically talk about the first four, and then he will take over talk about the program. How would
Nice.
share?
Can you also present the slide for the keynote speakers?
Just only, yeah, not much driving tips, okay? Just make sure everything and then you go into the some details.
Yes.
Right, technical problems. And then how the program look like for the day, like what are the things.
Yep.
And then
Good to go, always.
yeah,
Then we will hand over to Robert.
yeah, so you have one of things.
Okay. Yeah, I will go through them very briefly.
Yes, and then after that I will. For the next session.
Yes. By the way, you also will introduce us, right? So maybe we will quickly, maybe ask us to stand up to all the audience will understand who are the pairs and stuff. So okay, so feel free if you like use the stick. You can use it for pointing if you like, or you can use the mouse if this is more convenient for you. Whatever you like, right?
Sure.
Okay.
So this should be good, right?
No, we have to make it point down because otherwise we will not hear the people from the remote attendees will be here. So yeah. Just speak up a bit and we should be good.
Good morning, guys. Do you hear me? All right. Yeah, so welcome everybody to Vancouver. Welcome everybody to CVPR 2023. It's an exciting event for all of us to, to see each other and learn as well. Also, I want to welcome you actually to our workshop, the 18th workshop on perception beyond the visible spectrum. So many of you probably attended, previous workshops in this series. We've been organizing this workshop over the last 19 years. We're shy over 1 year to celebrate our 2 decades events. So hopefully next year we'll be part of that event. So again, on behalf of my colleagues, Michael Touch, right? Irhan, Engel, Eding, Eric Blash, and Wasim Al-Ahmar. I want to extend my welcome you again to this workshop. And
Click or scroll the mouse.
yeah. Okay, so this workshop basically hosts, unique sub areas of the computer vision and pattern recognition, topics. We're specialized in the beyond the visual spectrum, right? So the majority of the CVPR, attendees or researchers, they basically work on RGB, most on RGB images. So this workshop is, again, gathers folks who work on the infrared spectrum, multispectral satellite imagery, LiDAR, radar, and many other modalities that they are not very underrepresented in the CVPR, topics. So we're interested, again, in work being done, fundamental work being done in these spectra, but also applications, and that spans number of fields like automotive, defense, and robotics, and many other areas as well. Yeah, so over the past 19 years or so, we the team, the organizers, actually always worked with or invited the world-class keynote speakers to present their research, and provide guidance actually on where things are heading for basically for attendees. And I think we benefited a lot from their talks. We had a mix of keynote speakers. We had mix of keynote speakers from academia. Some of these faces, some of them had retired. Some of them, are CEOs of companies. Others are from government agencies, like, Air Force Research Lab. Others from Google. You probably familiar with some of these names. And last year we had folks from DARPA program managers presented their work as well. And this year, so we will talk about that. Like we have 4 keynote speakers, and we'll introduce them shortly. One thing actually we introduced in our conference or our workshop is it's a benchmarking data set. So it was one of the first actually public data set that we made it, we gave it to the audience, basically to try their techniques on and contribute new data sets. So this data set basically is growing year over year. It has, a diversity of challenges, from object detection to maritime object classification and so on. Face recognition, one of the first, and some are basically near infrared, thermal, and so on. So yeah, I mean, we definitely would like to expand or add more data sets. So if you work on a data set and you want to make it public and get exposure to your publications, please contact one of the organizers and we can add it. It's very easy to add it and, provide wider exposure to your publication. And yeah. Okay, so as I started, on the organizing committee, we have, I think by now, who they are. But please, raise your hand as organizer or co-organizers, so people can recognize you. Yeah. So Wasim, yeah. So we have basically on this committee, we have folks from industry, we have folks from academia, and kind of like distributed. We have folks from government agencies as well, who can provide like guidance on keynote speakers and on aspects to to emphasize in the workshop. So we've been organizing actually this workshop for 19 years. We try basically to follow the guideline of CVPR in terms of reviewing process, in terms of maintaining a high quality. And yeah, so basically we're serving the community by bringing to this organizing committee experts from different organizations, and it's distributed as well. It's not just in US, it's US and Europe and Canada as well. So this year in particular, I want to highlight that we added Wasim Al-Ahmar as our publicity chair. So if you have ideas on how to advertise, the workshop, and how if you want to contribute, please reach out to him or to any one of us, so we can include you next year in the organizing committee or the technical program committee. So this year, the organizing committee elected four world-class keynote speakers. Here they are, their names actually on the board. And they come from different, background. So two from Canada, Professor Robert and Zhang Lu, and one from Europe, and I think Jonathan Hu from Canada, three from Canada. So yeah, so I think it's going to be very exciting to hear their perspective on the work that we're doing and where actually perception beyond the visible spectrum is heading. So make sure you attend actually and benefit from their talk today. And with that short introductory, I want to actually hand over the other slides to my colleague Michael and Angel to talk a little bit more about some of the effort they did, to come up with the program that we have today. And yeah, so welcome again. Please, Michael.
All right. Also, warm welcome from myself. I'm Michael Teutsch from Germany, from German company Hand Electronics, and I'm the program chair of this nice workshop. I haven't been around for 19 years, but maybe for 5 years now. And maybe next year we have the chance to celebrate a nice anniversary. We will have to figure out who will bring the cake and the sparkling wine. I don't know. We'll see. And hopefully all of you will be there as well in Seattle, I think. All right, cool. So what remains to be said is that when we started setting up the program, why is this not working? Oh, come on. You just had to click on the mouse, right?
No, scroll down.
Yes, I do that. Don't know what's happening here. Well, let's do it this way. All right. So we want to say a few words about the paper submission process and the review process. So we have received, besides the program parts that have already been mentioned, like the keynote speakers and the challenges, we also accept submitted papers and get them presented in oral presentations later. So for the process, we had 41 submissions in total. Not all of them were valid, but after figuring out the valid submissions, we had, I think, like 35 or something submissions. We strictly followed the CVPR double-blind review process to get these papers reviewed. We had between 4 and 2 reviews per paper in total. And at the end, we came up with like 11 borderline papers. The others were clearly accepted or clearly rejected. And for these borderline papers, we made a separate review process, including all the PBVS chairs. We had a discussion about each paper. We made a rating, a voting, and at the end, we decided based on this voting which of these borderline papers are accepted. At the end, we came up with 22 accepted papers. We will present all of them in oral presentations. The reason is, we also discussed the idea of making a poster presentation, but we thought that oral presentations would be much better for also the remote participants to really interact with us, yeah, because posters, you cannot really bring these remote attendees to the poster session here in Vancouver. So that's the reason why we said we will do oral presentations. They're quite short, like 8 minutes per presentation, but I think we should, within this 8 minutes, get a nice idea of what the authors, what is the contribution, the idea in the paper. And at the end, we have like a 53% acceptance rate in total. We in particular want to thank the reviewers. We had quite a lot of reviewers, as you can see, all around the world, who severely supported us in figuring out like the review process, and they provided really valuable reviews for us to support our decisions. So again, thank you to all of these reviewers. Having a quick look at the program, we can see that this workshop will take place until 5:30 p.m. today. We have a full program starting with the keynote of Robert right after my introduction here. We will have 4 sessions where all these papers will be presented that have been submitted and passed the review process. We will have some nice breaks here, like the first one will start out right after session 1, the coffee break at 10 a.m. We will then have another keynote, another session. Then we will continue with the lunch break. We have 1 hour lunch break from 12 to 1 p.m. Then we will again start with a keynote and a session. After this third session of papers, we will have the announcement of the PBVS challenge winners. This is where Engel, as a challenge chair, will take over, and his colleagues. And we will have another coffee break at 3 p.m. Again, with the last block starting with a keynote and the session of the submitted papers. After we will end the workshop with some closing remarks. Just a very brief look at the challenges. We had 3 challenges this year. The first challenge, which has quite a background now because it's running for the 4th time already. It's the Thermal Infrared Super Resolution Challenge. We have 2 tracks here where in general we want to perform super resolution to thermal IR images, as we can see here. The cool thing here is that it's not like with quite often, let's say that super resolution challenges or benchmarks, they do like they take high resolution images and they downsample them in order to then get them upsampled again. And instead, what we did here is we used cameras with a higher resolution, strictly following a process to acquire the same scene from the same viewing angle to have real thermal infrared images of higher resolution for this challenge. And we also have a second track on guided thermal image super resolution. What I want to emphasize here, I mean, I don't want to say too much about these challenges yet because we'll have this dedicated session later on, is that we have 150 teams participate in this challenge, which is awesome. I'm really thrilled. It's a huge number of people and teams attending. We have a second challenge called Multimodal Aerial View Object Classification Challenge. The idea is here to use synthetic aperture radar images and electro-optical imagery to perform object detection and object classification in satellite imagery. And this is, like, I think, the second time that we are running this challenge. We also had it running last time. As I already mentioned, this challenge focuses on SAR and SAR plus IO fusion classification. And we saw a strong improvement of the methods and this results submitted by the participating teams compared to last year's challenge. And also here we had more than 90 teams participating in the challenge. And the third challenge, running from the same organizer, is the Multimodal Aerial View Image Translation Challenge. The idea here is to use SAR imagery, as we can see it here, and to translate it into visual optical images. So it's an image translation challenge. And this is running for the first time, this challenge, and we had already more than 50 teams participating here. Before stopping the introductory slide and finishing here this session, I want to do a little bit of advertisement. 3 of our chairs, including myself, we quite recently published a book, a small textbook on computer vision in the infrared spectrum, challenges and approaches. It's like a survey-ish book, just like having a look at all the different topics of thermal infrared computer vision and pointing out the current state of the art and where we are heading towards. So if you're interested in this book, you can easily find it in the different stores and Amazon and stuff like that. Yeah. Okay, so I think with this, I would like to end this first session, and I would like Robert to come at the front of the stage to give his keynote presentation. Riyad, you want to do the introduction, right? So I will quickly set up the stage here because I did a mistake during screen sharing. I want to correct that. This should be it. I'm not really familiar. How can are you familiar with Zoom? I would like to share just this screen. I mean, I make an extension of the screen. I would like to have this screen, not like this screen being private and this one being shared. Any idea how to do that?
Okay, well, everything here is.
No, this is not correct.
Maybe should select a window.
Yeah, I was expecting that, but it's not here, unfortunately. I don't know why. Maybe we will continue like we just did. I'm not really. Yeah. Okay.
Just close this one.
Yeah. Okay. This is not good. Zoom crashed.
Still share something again.
I'm not fully sure. Okay. Can you still see us in the virtual room? Because Zoom just mentioned that it faced an issue. Ah, cool. Great. Okay, then I'm glad to hear that. Okay, cool. So let me quickly share the screen again. And we will get the slides. Okay. Okay, now it's working. Great. Okay.
Right, so next I want to welcome actually Robert, Professor Robert Laganière, as our keynote speaker. So the title is Perception from Radar Sensors, Principle and Challenges. So Robert is a professor at the School of Electrical Engineering and Computer Science of the University of Ottawa and the CEO of Sensor Cortec, a startup company developing AI solutions for perception systems. Robert is the co-author of several scientific publications and patents in content-based video analysis, visual surveillance, embedded vision, driver assistance, and autonomous driving applications. Robert authored the OpenCV2 computer vision application programming code book in 2011 that many of us actually read, and co-authored object-oriented software development in 2001. He co-founded Visual Cortec in 2006, an Ottawa-based video analytics startup that was later acquired by iWatch Live in 2009. He also co-founded Tempo Analytics in 2016, a company proposing retail analytics solutions, and founded Sensor Cortec in 2018. So welcome, Robert, to CVPR PBVS 2023.
It's a problem in screen sharing. We quickly need to fix that. So okay. Really? Okay. We cannot share the screen anymore. There's a Zoom error. I don't know how to handle that. If I leave the room now, I think everybody will be thrown out. So it's not a really good option to do that. But it's simply not working. Is there anyone here familiar with Zoom? I'm using Teams usually, so I'm not really so much experience in Zoom.
The window.
Yeah, of course. I mean, this is. But if like this, the screen sharing fails, any idea? Maybe do we have to restart Zoom?
The Zoom now? I guess yes.
Yeah, and I mean, if I go to screen sharing, it just gives like an error code saying like it doesn't work.
What does it say?
It's not working. Here is the error code.
Okay,
Congratulations.
So Michael, can you restart?
Yeah, I think we should, but in that case, all the people who are remotely attending will be thrown out of the room and have to rejoin the room. But I think we don't have an option, right? Yeah, I think they should be able to hear us online. Do we? Yes. Okay. So in that case, all the people who are joining us remotely, we have to apologize. We have to restart Zoom because there is a problem. And so you all have to rejoin our session after I restarted the meeting. Sorry for that. See you in a bit.
Michael, can you make one of the attendees
Oh, yeah, good idea. I like this. Correct. Let's see if we can do that. Jasmine, I will choose you as a host, right? So I hope you can take this responsibility. Okay. I guess you are now the host. And if I
real world application. So you have to look at the and the complete. Yeah. Radar is an active sensor, so it basically you the the technology that the other active sensors are using, the LiDAR and the sonar. So the principle is always the same. You emit a signal, that signal will bounce back to an obstacle, and then you read the signal that you see from there. From that, and then you can infer some information about it and about the property, some of the properties of your obstacle. So radar is a relatively old technology, as we will see, but today there's new applications that emerge. So that scientists to patent an idea of detecting objects to really way. And that was the first patented idea that we did. Obviously, like many other technologies, the development of radar was motivated or stimulated by before. So during the World War II, both German and British were very advanced in that technology. The American less. In fact, there is that story where obviously when you read out it, and these radar have been able to detect the aircraft that were really reliable. But the report from the radar operator simply this. They did not really believe in that symmetrical thing. So it does show that at this time, radar was pretty new. To provide too much information here, just to say that after the war, the civilian application of radar started, with obviously the component of civil flying. The use of radar for predicting weather. The idea of using radar for mapping, etc. So many applications created, and also during that time, the theory behind because the essence of radar was developed. So basically, the important technology for radar. The first one is the time of flight. I mentioned it at the beginning. We'll look at the wave and the motivation. All of that combined is the radar technology. So time of flight, obviously, that's what we said. So you get the review of pulse, and then you get the rebound. And from that information, just using the fact that you know that the wave are traveling at the speed of the light, we can easily get the entry point. That would be you can also use the Doppler method. So if you emit a continuous wave, you know that if this wave emitted at a certain frequency is an object that is approaching direction, the frequency of the signal you will get will increase. And simply because the object is approaching the wave toward you. So the change in frequency will be that object, and you have your typical effect. That is away from you, then the frequency you. So this is one important thing. Okay, so it's usually it's a corner reflector that you will use, so it's just a metallic object that will bounce back the radar signal very well. It will be very visible on the radar, and you can use it as a target. And so all you have to do is to position that reflector at different positions. So this is an example where you have a radar, you have a stereo camera system, and you have the reflector cone there, and you can move that cone everywhere in the scene. So you will be able to calibrate your radar with respect to the world. So basically, it's again some math that you have to play. So in red, you have the position of the object with respect to the stereo F. And in blue, this is the radar. And then you accumulate that, and you get the perfect, almost perfect, hopefully, perfect registration between your radar and your world effects. Okay, so you have installed your radar, you're ready to perform detection. So a good idea is to use AI for that. What do you know? What do you need if you want to use AI? You need obviously a large data set. You need that data set to be annotated. You will need to decide which representation you want for your radar signal. You will need to determine what you want as an output. And obviously you have to find the appropriate neural net that will perform the task. So annotating, I would say, is probably the most challenging part, because as I said, it's a signal that is very difficult to interpret. So you cannot do it manually, so you have to combine the information from more than one sensor. I gave you an example where we were using a stereo head in order to get the information about depth of object. So this is an example of the work we did in that direction. So basically, you have the radar signal, and on the bottom you have the stereo signal. We can perform, for example, segmentation. So you get the object in the scene. From the stereo head, you get the depth of those objects. So you know in which direction they are, you know the depth. So you can project back these objects onto the radar. And because you have registered the radar with respect to the stereo head, so you're able to identify these objects on the Cartesian representation or any representation of your radar signal. So you do that for thousands of images, and you're good to go with your with the training of your AI system. So this is an example that's probably difficult to read, but that person there is here on the radar signal, and you have a car that should be probably here, etc. So you see how difficult it would have been to detect these objects in the scene without having the ability to reproject from one modality to the other. Once you have your image, and this is more or less an image with annotation. So when you have your image, you can use any object detector that usually are applied on images. You can apply them on your radar signal. For example, you can use the YOLO, which is probably the most popular anchor-based object detector. So if you're familiar with the concept, basically you have to detect bounding boxes. So you have many cells that are responsible to detect a particular class of object inside the image with anchor of certain position, certain size. So you have tons of detections that are made, and at the end you keep just the one that are over a certain threshold, just to simplify the idea. So that's what we have with what we just did. We have those bounding boxes of our image. We can use the same principle, and that's what we did. We use just a YOLO core in order to detect
object onto the radar signal. We did it with two different heads. One is for the 2D signal, and the other one was trying to detect in 3D. Not that since it's a radar signal, you get the signal from the antenna, and you must apply the mixing, the ADC, the 3 FFTs in order to get the cube, and from there you're able to apply your neural net solution. And that's what you get. Was playing.
You just have to switch back to
Yeah. Okay. So you see the kind of detection you get using that solution. So it's relatively good. Obviously, you will miss some object, but you clearly see that pedestrian moving in the direction of the radar. You see the car passing by, so you get the detection. And again, I show the video here, but we'll just but remember that this is what we did. We get the FFTs, and then we apply the DNN solution onto the FFT signal. So this is already better than the classic traditional radar processing, in which we perform the FFT, the CFAR, the thresholding, the clustering of the technology. In that case, we simplify the chain. Can we do better than that? Can we just read the ADC, so the signal directly from the antenna, and get everything end-to-end, get a complete AI solution? Yes, this is possible because, in fact, if you look at the map of the FFT, you can transform that FFT into a graph, into a neural net. And in fact, you will input your ADC to this, what we call the Fourier net. So this is from the CubeLearn, from a recent paper. And so you're able to train your network to learn what is an FFT, and you get some information this way. So this is the experiment we did. So if we were to use directly the FFT, that's the signal we would get from the random coupler in that case. And this is the signal that was learned by the network. So this is quite similar, but not identical. So that shows that your neural net can also learn how to perform an FFT. So you combine that into a big network. In fact, what we did, we also introduced the idea of transformer, and since it seems to be very effective in object detection. So you have an ADC that you input to your Fourier net, and then you have your transformer applied to that, and you learn end-to-end from the input to the output, detection. And is it better than what I show you, the YOLO solution? So yes, this is better if you look at the 3D tensor. So this is the performance accuracy we get from the YOLO, the one that I showed you, and this is the accuracy we get from the end-to-end solution. But this is not that simple. Maybe I can show you the result from the other slide. So if you look at the per class performance, what you can see is that for a radar, the accuracy, the average recall is still pretty low. And depending on, are you using the ADC, are you using the RD or the RAD, the 3D cube, you get different performance. So it's all things that you should analyze. There's clearly a room for improvement there. So if you're interested by radar processing, I mean, that's certainly a subject that still needs to be studied. I just want to mention rapidly that what I showed you was all about bounding boxes detection. So since the radar is pretty sparse, it could be a good idea to use a point-based detection. So there's another family of object detectors that are based on points. And the benefit of using points is that you can get what I call heat maps. So in green, you have the heat maps of the vehicle detected by the radar. In green, this is the pedestrians. And that's the detection we get. I think that's the most valuable information you can get from a radar. Probability that you have a person in that direction at that distance. The probability that you have a car, because radar will not be very good if you have to detect individual objects. So if you have a crowd of 3 people together, the radar will have difficulty to tell you that this is 3 persons, but it will clearly be able to see that as a group. That's why I believe that heat maps are probably better. But if you still want to perform detection, you can do it by applying obviously resulting on that signal. Just to give you an idea, so I'll take the video. You will see circles. So those circles correspond to the ground truth. So there is a car at that position that the radar hasn't seen, and a dot corresponds to a detection like radar. So whenever you have a circle with a dot inside it, that means that we have a successful detection. We have just a circle alone, that's a miss object, and if you have a dot alone, that's a miss detection. So what should I do to play that video?
You just have to go to the next slide, actually.
Yeah.
And go start the next.
Yeah, right. Okay, so that's what you see. You see there's a crowd there, and that's very difficult for the radar to count the individual object, but still it detects. So again, there's a car approaching, so that gives you an idea of the kind of detection that you can get from the radar. Green obviously seeing the car. So this is far from being perfect, but the heat map is much better. Obviously, the challenge there is to evaluate the accuracy of that kind of detection. Finally, just to go quick, what else can we do? We can go for open space detection. We want to drive a car, for example, and see if we have the space to drive. So again, creating the ground truth is the challenge there. So one thing you can do is to rely again on other sensors. So if you have the camera, you can use the camera, the segmentation, and get the segmentation of the road versus the object. So that gives you a preliminary limit of the open space. If you're lucky enough to have also a LiDAR, you can also use the LiDAR information to detect a ground plane. And again, if you combine the two, you get a relatively good pre-annotation of your open space, and you have to go through that detection to clean everything manually. And after that, you can project that ground plane detection onto your radar signal. So in red, what you see is the ground truth applied on the radar. To test that, we use a popular network called the StixelNet. And the idea of the StixelNet is basically to divide the image into columns. And for each column, you try to detect what is the range of open space that you have. And you combine all these detections together. And you get the detection from the radar of the open space. Again, in blue, that's what we detect. In red, that's the ground truth for the open space detection. So this is quite reliable. It tends to, obviously, the radar has a limited field range resolution, but for close object, the detection. Okay, to conclude, radar, it's a good device because it's cheap, reliable, robust, solid state, so very easy to use. I mentioned that it is radar very good under adverse weather conditions, but this has never been convincingly demonstrated, and I think that should be done. Radar will become and are becoming part of any good EV system because that's an important sensor with very nice property. Radar are improving, and resolution and accuracy in particular. You can apply radar for AI for radar. It's a good idea and it works. And more than that, if you want to have a reliable perception system, you have to build multi-sensor system. So you have to perform sensor fusion. And if you're able to do that, I believe that radar should be part of your system. Thank you.
May I ask you to moderate the Q&A session to make start?
Okay, we'll take some questions. Go ahead.
Thanks a lot for the great talk. It's really inspiring. I have a couple of questions. I want to make it quick. Like when you mentioned about the learned FFT part, so are there also methods that just gets rid of the FFT part totally? Like why do we need to make the transformation to the frequency component? Like, well,
okay. Basically, what you're telling us is that we are currently sure that it's possible to have a neural net for the FFT part and a neural net for the detection part. Why not combining everything into a big network? It's more or less what you're looking for. And the answer is yes, certainly that should be possible. And I think that that's very interesting subject.
Another question?
Thank you very much for the presentation. So I was wondering, common time latency. So I'm wondering, like, if it has been done a combination of frame-based and radar to, for example, estimation of otherwise.
Oh yeah, so that's important because radar will work at 10 frames per second. If you're using an image, that would be more than that. LiDAR will work at another frequency. So, and you have to live with the delay. Not only these delays are important, but also you have to take into account that you must receive the signal, save it, send it to your network. So all that will introduce delay. And that could be an issue. Really high speed, for example. This has, you have to look at your system and measure those that possible latency. But I think what is even more challenging than the latency is the synchronization of all these sensors. And this is because they work at their own pace. And if you want to combine the information, that's where the challenge.
So if we bring everything to 10 Hertz, would that work?
If you have a clock to synchronize everything, that would help. Is that necessary? Maybe not. Again, you have to do your math and see what you want to detect at which speed, and is that important that you have only an estimate of the synchronization of a certain number of milliseconds. You have to find out.
Because usually what we do is like we bring down, the speed to 10 Hertz, so the LiDAR image.
Exactly. You can do that. Yes.
Just a quick follow-up. So in an idealistic case in which I'm process as fast as I want, the acquisition pipeline of the data, process it from like acquisition, how much would they allow me?
Well, the nice thing is that not like LiDAR, there's no mechanical part. So you just emit your signal and you get the bounce back signal. So you have a certain number of chips that you want to accumulate on your frame, and that could be your.
Take another question.
Yes.
I think go ahead. Very good talk. So I was wondering, roughly speaking, the learned FFT part, what's the basically like number of trainable parameters?
Oh, I have that information, but I can tell you. But okay. This is if you want to check that on our side, yeah, so I believe the information.
Okay, I see that. Thank you. My question is on the object detection part. So Is it difficult to distinguish multiple categories of objects from the radar signal?
Yes, but in fact, car are pretty obvious. You would distinguish between car and truck because of the size of the cluster you will get. Pedestrian, you know that it's a pedestrian because the reflection is medium. But after that, there's a lot of unknown, and that's why our recall was so low. And it's very difficult to all the that's a big challenge. And interestingly, this is something that traditional radar cannot do. The detection of the classes of objects. Maybe with some tweaks, but really you cannot detect. That's what AI can introduce. And I'm sure better performance can be achieved also.
So I have a question.
Yeah.
So nowadays we have, these vendors of radars like Conti, Bosch, and many other vendors. And when you get those radars, basically they come with their own software to get you the range, speed, and azimuth, right? So now you're basically in your presentation talk about, okay, let's take the raw radar signal and do some kind of radar imaging, like processing the chips and FFPs.
Correct.
So based on your experience today, so do you recommend to go this route that you suggested, or take the signal, the process signal from the vendor, right? Let's say at 10 hertz, 20 hertz, whatever, and then just do some early fusion. So which one do you recommend to go?
So you have basically three options. You get the signal from the antenna. That's what you have. You get the signal from after the FFP, so that what I call the RAD2.
Okay.
And the third option is to get the signal from the point cloud that those radar can output as well. So applying the CVPR to it. Clearly, it's better to use the RAD2 than the point cloud. But is that better to use the EDC? From the result we get, it's so close that it's difficult to claim that you should be the signal directly. But you save something because if you have a solution end to end, everything is a network. So computationally, it could be more easier to implement, to deploy. And that's one point. On the radar manufacturer, you have to be careful because you have to make sure that your radar you can access to the EDC, you can access to the RAD. So this is all proprietary software. So you have to make sure that you have the implementation.
Yeah, we have a question from remote.
Yes. All right. Do they hear us?
Yeah, thank you.
I think so.
Okay, so I'm gonna read a question from remote attendee here. How to handle vision tasks that are fine in this sense? Example, finger pose estimation with radar sensors.
Well, it's all about, there's many configurations in your radar. So if you have a short range radar, so it's all about the duration of your chip, the number of samples that you have per chip, and this will define the range. So if you want to do gesture recognition, you need a very short range with a finer angular resolution. We'll be able to do that. And in particular for fine motion, you need to perform an extra analysis on top of what I explained, which is to detect the micro motion.
Yeah, probably for gesture recognition, I would recommend just using.
I don't know.
It's also very cheap sensor.
Yes, but there is some limitation, lighting,
right?
And it's more intrusive. Remember that radar, the nice benefit is that you can deploy your gesture recognition in an elevator, for example, if you have no images.
Do you have a laptop that we can use instead?
Mine's broken.
Yeah, you
in general, I would say I prefer when your solution is customized for the application. I don't really believe even in AI solution that fits all applications. I think it's always better to, whenever you have a particular use case, to step back and look at the design of the network to really adapt it, make it optimal for what you want to do. So that's always what I.
So while they are finishing the setup, just another question. So in the results that you presented, you know, that maybe the third table shows that we have protection for cycles.
Yes.
So in your experiment, how far these motorcycles were, and what's the thought behind this low, you know?
Well, one of the obvious reasons is the number of samples.
Number of samples from radar.
The number of motorcyclists that were visible in the data set.
Yeah.
So that doesn't help for sure.
Yeah.
And yeah, it's probably one of the most ambiguous categories. You have some of the reflection of metallic object, but you also have a person. So that's very difficult to catch.
So basically, we're not getting enough returns from the cycles.
Yeah, the return is ambiguous. Yeah.
Because
so you have a shorter range of detection.
yeah, because I've seen that actually some of applications where
Motorcyclists.
yeah, it's kind of like the misses.
Yeah. Yeah.
Okay. Cool. So if no more questions, let's thank actually our special keynote speaker, Professor Robert. And this was very inspiring talk, very unique talk at CVPR. So thank you very much.
So we have to rearrange things. We will start with the second presentation of the session.
We don't have video yet. Okay. Can you see us now in Zoom? I switched on the cameras, and now you should be able to see us in a new laptop.
I can see your. I can just see you. Yeah.
Ah, we didn't plug it yet.
Yep.
Give me a second. Yeah. Where is the? Ah, okay. Here. Okay, got you. Okay. Yeah.
What is the presentation? Did you copy? Did you copy the
It
presentation?
didn't work to copy the presentation. We will put this presentation to the end of the session, and while the remote speakers are presenting, we will try to figure out how to transfer the slides. However, I cannot share the screen. Don't know what's going on. Or is it already shared?
Yeah, you're sharing the screen.
But it's not. For whatever reason, this is not working here to share it on the. No, sorry. We will find a way. We'll find a way.
You want to extend the text?
Yes.
Like this.
Yes.
Extended.
But there's nothing detected here.
In
Computers.
if you do click extend options, it won't show anything there.
Okay.
Please provide. Let me.
Did it work? No. Right. Okay, we'll do it differently.
I will give you my. This used to work in the past, so it should work again. Okay, here we are. Yes. Cool. Okay. Now, Zoom, you share the screen too. Yes, of course. The second screen, this is now how it should be. Okay, cool. All right. Perfect. And now we can start. Can the remote attendees hear us? Hello, hello. 09. Did we choose the correct device for the how can I choose a device for the audio? Yeah. Hello, hello. I hear you. Yeah, but it's not like the speaker that we have here. We should use the speaker. It's switched off. Okay, now it's again. Again. But it's not appearing. What's the problem here? But it sounds good. Yeah. Hello. Not connected at all. That's the reason why it's not working. This new technology is getting too difficult. The hybrid. Test 1 2. Hello. Yes. This one, we should be good. Okay. Again, can the remote attendees hear us? And can the speaker of the second presentation please speak up? The second presentation is C++. So it should be Abe Reyes Angulo. Are you here?
Yes. Yes, I am here. Can you hear me? Can you hear me?
This seems not to be the case. In that case, we have to use the video. But the video is not here, so I'm not gonna. Okay. In that case, I asked the third presentation, the three-stage framework for reliable sample pool. Does somebody hear? This seems not to be the case. Okay. We have Deep Mao. Anyone here?
Hello. Hello.
Okay.
Hello.
So severely went wrong. Maybe we just continue with the first session after the coffee break.
Yeah, maybe.
Okay.
The second session? No, the first session.
It's the first session, yeah, but it's
For the videos, we can download it from CMT.
yeah, but we will have to have some time for that. So we just we stop here. We will go to the coffee break and we will return here at 10:30.
So maybe we should call yours for a single computer, right?
Yeah, exactly. I copied all the stuff there, what I already had, but we need to use a new laptop.
Audio test.
Hello. Somebody can hear me?
I'm the last.
Yeah, wait.
I'm not sent you the slides.
Andres Reyes, you have sent me by email?
Not yet.
Okay.
This is not my USB. Okay.
Something happened?
Hello. Testing. Hello.
How do I, can I send to you by email?
Can anyone hear me? Hear me?
That is good.
Probably, yes. Oh, give me a second. We'll give you the USB stick. You don't have the USB stick with you?
Yeah, unfortunately, I know.
By
the way. Yeah, never mind. After that, I know that should work. I mean, now we have some time. Oh,
Yeah. Some the people who was here. Yeah.
But they didn't speak up. No, they know each other. It's not how.
There is no sound.
That's what I speaking here.
Hello.
But he was no sound. But this guy was supposed to do the sound. But I don't know what happened. Okay, probably
It's okay.
set up the audio settings correctly.
It's okay. All right. Thank you, Angel.
Maybe the keyboard broke down. I was not able to enter the @ symbol in the links to join Zoom. Maybe you want, I can check it out.
I tried it 2 times.
Do you have the program? Because people.
Okay, let's try it.
I'm not sure what's going on with the
Yeah, no problem.
Program.
It's
Aquí le Abel,
not your fault.
here.
Let's see. Oh, this sounds good.
Okay.
Did it open the USB stick?
Yeah, yes, yes.
So
trying
two
to-
things in
Yeah,
parallel.
I'm trying to answer these people that.
Copy the
Yeah,
slides to the.
yeah, perfect.
What? Have in total 4 videos, right? I'm just thinking if we may want to, but remote attendees will be bad. I thought about moving the first session to the very end of the workshop, but it would still be difficult for the guys who will be in a different time zone. Maybe we can still stick to. Thank you. Yes, sure. Oh man, I'm yearning for these times when we had workshops in presence only in person, you know, with this remote stuff and hybrid stuff. And
Hybrid is the most difficult one.
Yeah,
If
really.
it was only remote, it would be
we
fine, I
should
guess.
have to think about a different way of doing it next year.
Did you put a, no, I cannot see it.
You cannot see it?
No.
Okay, then we will do it differently. I will transfer my, I received an email from her and I will forward you the email
Okay.
with the slides and then it should work.
Am I still going next or am I going later?
I don't know yet.
Okay.
Give me a second to think.
And also,
Probably yes. I mean, it doesn't make sense to change something here. So
¿Puedes hablar a ver si me escuchas?
I forward the slides to you in your
Okay.
email account.
Hello, 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 hello. You listen to me
Sorry,
now?
this should be.
I listen to you. Yeah.
Okay, excuse me. Yeah, it's. Can you please ask him?
Hello. Hello, hello, hello. Do you hear me? Hello, testing.
Which is the file that you transfer to the USB stick? I cannot find it.
Something PBVS.
Ah, it's a Adobe file, right?
A PDF, yes.
Oh, yeah, now I got it.
Thank you.
Yeah.
Here the folder. Okay.
Which session are you in?
I'm in the last presentation.
Last, like,
Yeah, so
which is like session 5, session 4, right?
I think so, yeah.
But okay.
Alrighty.
So we will get this guy.
Maybe here is presentation. This is the folder.
Okay, okay.
Move everything there.
Which city are you based in Germany?
Berlin.
Oh, Berlin. Oh, must be a fun place.
It is fun. Yeah.
And we need to get it. So how long is it with Amazon?
More than almost 40.
Lady.
Yes.
Testing, 1, 2, 3. Testing.
No, wait a second. Veamos qué tenemos por ejemplo.
Es el audio en.
Aquí. Aquí dónde está el problema.
A ver, está activado.
Speaker.
Ah, no, it must be.
Which one? Again?
again,
This one here.
This?
Yes.
Abre.
And now you have to go again to this one, here again to this.
Yes.
Yep. And this one has to go to eMeet as well. Testing. Testing, testing. Hello, hello. Okay, it's working.
Perfect. One problem solved.
Check. Thank you.
One to see, can you hear me? Can you hear us? Okay.
Can we move a bit to the left? Test 1, 2. Hello, hello.
Hello, can you hear us? Vete afuera del. Okay.
should you also download videos somehow?
Yeah.
Because we have at least 2 remote section.
Yes,
One
but I
second.
mean, I think both of them mentioned that they are here, so maybe.
They're here?
Hello, hello. Do you hear me?
Can you hear? We can hear you perfectly.
I can hear you too.
Okay. Everything is over. Sorry for those.
Oh,
that-
here. Can you hear me too?
Yes, Abel. Sorry for the problems.
Excellent.
you have presentation in the first session, Abel?
Yeah, I have. Yeah, I was the second one.
Okay, we will try to organize again. Just so for the first session, we are going to do something. Okay, sorry.
Okay. Sounds good. No problem. Thank you so much.
Where are you from, Andres?
From Ecuador.
Oh, really? Come on.
Yeah, you are Angel Sepa. You are affiliated to sport, right?
Yeah. We are.
Yeah. I'm in Michigan Tech actually now.
Okay.
Yeah.
Okay.
I was supposed to be going there, but it's kind of like hard to get visa now for some reason.
Yeah, we got to.
Nice.
With laptop and then.
Nice
Nice to see you.
you.
Nice to meet you. Nice to meet you.
Okay, we are solving some final problems here, but everything.
No problem.
He's working now. Yeah. I mean, this guy is not really working anymore. I don't know what's the reason, but the keyboard has him. I don't know what's the problem. To be honest. But we should be able to transfer now the data that I had stored. You're starting that and then it would be good.
Yeah.
Okay.
Perfect. Are you copying? Okay.
Yes. It takes a bit.
Everything, and should I download the videos?
No, I transferred them to you.
How do you have space in this? Okay.
But I think we also should double check. There was one more guy who uploaded a video and I have to quickly check that if I can download.
Si quieres apagar tu cámara porque.
Sí, ¿no?
Sí.
Si no, de que yo no me veo acá, sí.
Por eso.
Gracias. Y el micrófono también.
Sí, mi mic.
switched on yet. Now it should be good. Yeah, do you hear me? Can you hear me?
Hello, hello.
Yep.
Hello, hello.
Cool. Okay, awesome. All right, good. So let's continue. Okay, welcome back to the PBVS workshop. The technical setup is challenging today. We are facing the same issues with another laptop that I had with my laptop. However, I think we found a nice workaround. We're all engineers, aren't we? And we now start to continue with this new session. We had to rearrange things a bit. So what we will do now is we will continue with the keynote as planned. We then will continue with session 2 as planned. Then, and I also kindly asked the presenters from session 2 to shorten their presentations a bit so that we can squeeze the entire session that takes 40 minutes to 30 minutes. Hopefully we will make it. I will try to do my best to do the moderation. And right after session 2, we will do session 1 that we missed in the first block that we had this morning. This means that we will go right into the lunch break. So if you are, I mean, I will skip lunch, but for all the people who do want to have lunch, they have to skip some part of the presentation. So maybe you can plan the best way you can find to let's say, find your way to do the lunch. Sorry for that, but otherwise we will not have a chance to catch up with the missed program anymore. Sorry for that. And also for the remote attendees of session 1, it means that you will have your presentation in about 1.5 hours. Yeah, then your session will start. I hope with your local time zones, this will not cause issues. If somebody has the fear of falling asleep or something, I don't know about the time zone, please just chat me, text me. I will reply in the chat of the Zoom meeting. Okay, so I hope this will work out. And now I'm glad to introduce the next keynote speaker. It's my honor to welcome Professor Zeng Liu. He's a professor of the University of British Columbia in Canada, so he's like the local hero that we have that we can have here as a keynote speaker today. His presentation title is Towards a Comprehensive Perception, Methodologies for Thermal Imaging Data Analysis. He's a professor at the Faculty of Applied Science of the University of British Columbia. Before joining the University of British Columbia, he worked for the National Research Council of Canada as a research officer and for the Toyota Technological Institute as a professor. His research interests include digital twin, data, information fusion, computer machine vision, machine learning, smart sensors, industrial IoT, and non-destructive inspection and evaluation. I will stop here with the bio to speed up a little bit, and it's my honor to hand over now to Mr. Zeng Liu for the next keynote presentation.
Okay, thanks a lot, everyone. And thanks a lot for the chair introduction. So for today, I will talk about the data analysis method for thermal imaging. If I talk too much, please remind me. Okay. So yeah, this is my bio. So one claim of the conflict of interest, because I'm happy to see my supervisor from University of Ottawa. He is the first keynote speak for this workshop. And I was educated in Japan, Canada, and China, and I work here and there, and get involved in the multiple IEEE societies. And my research is actually beyond the visible spectrum. I work on different things for living. Okay, and talk about UBC. We have the main campus at this city, Vancouver, and we actually have another campus in Kelowna, which is about a 4 hours drive from here to Kelowna. So the campus is relatively new. Since I joined this campus in 2015, it grows very fast. We have this number of students, number of the professor, number of the alumni, and number of the funding. Anyway, so the most important thing is this is the best place for wine. Okay, so it's not too late. After this workshop, you can package everything you have and move to this city. Okay, and for today, we talk about the thermal imaging introduction, data analysis, actually talking about the registration, presented as an image, presented as an object, and future research consideration, which I'm struggling with during this time and summary. Okay. For introduction, we talk about perception. So what is the perception? Okay. So when I have question, I always go to Wikipedia, go to Google, ask what are they? So perception, okay, we have the sensing modalities with us. We see, we taste, we smell, we hear. So then we got this sensory information processed with our mind, get some understanding about the environment and the situation. Okay, so visual perception surrounding environment. So you have different modalities, right? The spectrum. So this is about perception. So actually, there are two process associated with the perception: bottom up, top and down. So bottom up, that you see something, you work on that, you go up, that you try to present it, interpret it. Top down, you have your experience, you have your knowledge, then you're understanding that to process. So basically, I think we have some visual image, right? Then we go to the objective. This is where we are right now for the research, right? So this is the spectrum, so visual spectrum. So we talk about something beyond that on the right, on the left. So my talk is about the infrared, okay, thermal spectrum, okay. So
That was really disturbing.
yes.
Sorry for that. Okay, it helps a bit.
Okay. So when we measure object with the infrared sensor, so this should be considered, right? So material emissivity. So this is the measurement largely depends on the emissivity of your sensor, and so color no significant influence. Surface of the object, right? The surface structure, surface moisture, surface contamination, and foreign bodies. So this is the factors we should consider for measuring with IR. So the other is measuring environment. There are also a number of factors associated with that. For example, the surrounding temperature, the radiation, and parasitic sources, the weather condition, the humidity, the air current, pollution, illumination. Some has significant impact on your sensing, but some does not. To summarize this, so when you do the measurement with a thermal imager or IR sensor, so there are three things. One is the transmissivity, emissivity, reflexivity. So your measurement is combined of this. So any factor have impact on these three. So you may get the different things, right? Keep this in mind. We'll come back later for this. What doesn't work?
The presenter doesn't work.
Doesn't move.
Oh, I put the focus on a different window. Maybe you want to retry?
Yeah. Okay. So looking at the sensor operation, so I organize in two model. One is the uni model, let's say only with the infrared sensor. So when we look at this, I look at the different application. For example, non-destructive inspection, automotive, auto industry, chemical industry, and so on. There are different applications with the thermal imaging. The other multimodal, okay. So multimodal, let's say infrared sensor work with some other sensors for different applications. For example, they can work with ultrasonic sensor for distance measurements. They can work with the radar for tracking and searching, right? So this is a different potential for using the infrared sensor with others. Okay, so then I did some literature review. So I go to the Web of Science, search the database with a keyword, for example, infrared perception. So I got 376 publications from 2000 to 2023. So actually I use a package in R, it's called the this one, this is our package. So once you got this database, you can read it into the package. Then the R package generates some information for you. So one information is how the number of the paper publication goes up, and what is the main theme in different 4 categories. They have different theme, and the cloud for the keywords. So because I searched the perception, that is why this is the biggest one. Then looking at other things, you see, okay, there's maybe application for, let's say, brand or the other information. And this is interesting. This is to talk about the, let me, if I can. Okay. I don't know if if you can make it smaller.
How can I minimize that angle?
So that is the some keywords. So let's say this is a number of the year and how the keywords change from the past to the future. So that gives the information. Okay. So
Now it should work.
okay. So then I move to the infrared imaging data analysis. So before the first talk is about the registration. Okay. So one is the registration of infrared and visible image. So the idea is, so if we can align your visible image and thermal image, so then we can do something, let's say the fusion, target detection, or other things, because this is the pre-processing for that. So there are many solutions available. So people using the calibration board, which being heated, because heating that, the thermal image can detect that. So you use the color, white and the black board, so the visual image can capture that. So in this study, so we we propose a multi-objective optimization-based image registration. So this is the procedure here. So actually, we propose using the normalized grand measurements to optimize the affine transform. So then we do the registration. So here we consider 2 things. One is the linear distance. The other is angular distance. Linear distance is sensitive to the magnitude of the image, and angular distance sensitive to the phase information. So then we come up with some optimized solution and do the registration. So this is published on the Information Fusion journal. And we employed 3 metrics to evaluate the registration results. The mean square error, SSM, and PSNR. So also we do did some comparison with other solutions, and we claim that ours is better. So this is a number.
Recording in progress.
And here is the animation, which is available on the GitHub. So this is some of the data set we use in this exercise and show you how the image being registered successfully. Okay. So then I talk about how we process the data. So I think that it depends how you use that. Let's say we process the image, then you got a composite image or the resulting image that is presented to a person. I look at that. This is one scenario. The second scenario is I do some processing. I give that to computer. Computer work on that and give you some information. Let's say the bounding box tell you this is the object you are looking for. So this is a 2 scenario when I look at the problem. Okay. So for the first one, I think we can, let's say, you can present a infrared image, and you can present a fused image by the visible or infrared image, or you can present a visible image. So for each category, ABC, we have different researches here. For example, you have infrared image, you can do the image enhancement, super resolution, and colorization. If you want to present a fused image, so you can do the visible and infrared image fusion. And you want to present a visible image, they can enhance your visible image with a paired infrared image. So this is the way how you present an image to your end user. So again, I did the literature review. I got a 270 paper, and here is the information. Okay, they talk about the algorithm, some classic solution. I say histogram equalization, and the number goes up. And here is some the themes. Okay, for this. And first one is super resolution. So I searched the literature. I think this one is a good reference. It's on the archive website, and they talk about this is the architecture for this paper, not being peer reviewed and published yet. But looking at this, they talk about the traditional method and deeper learning method, how you can do the super resolution. And I think a smart solution is you use the visible image to help the super resolution of thermal image. The reason why we're doing that because thermal imaging system is expensive. So I have a low resolution thermal imager, but I want to have a high resolution imaging out of it. So how I can do that? So do the image super resolution may help you with this. For example, FLIR has the images thermal sensor which cannot attach to your cell phone, but it's very low resolution. But if you have this solution, you may get a better one. So this is just an example from a paper published before. They say once you achieve the super resolution, you get a nice clear picture. Okay, so possible. So nice clear picture. That is for your look at, right? So how you can further use the thermal image of high resolution for your application, right? You can do the recognition, do any other type of things, processing out of it, for example. So the other is the colorization. So this is the example for colorization. For example, we have the thermal imaging, but this is not good for human perception with their eyes. So if you can colorize that, that will be a nice picture, right? So this is an example. Let's say we do the colorization of thermal imaging. Finally, we got this one. So we actually have published a book, 2005. There is a solution how you can colorize your thermal imaging. And most recently, my collaborator, Dr. Zheng, we published together a book about how you can colorize and fuse the multispectrum images. So this is a example out of their book. So here, my question here is, this is nice. And when we look at the results, we use some image quality. Let's say you look at the contrast, you look at the other property of your image, you're gonna come up with a conclusion as this is a better results. But my eye tells me that I may prefer this one, right? So this is interesting. So we discuss this later. So the other quite a popular research is the fusion. So I searched the website, too many publications. So Web of Science can only download up to 500 publication. So I changed the time scale in the past five or 6 years. I got again almost 500 publications out of it. So looking at this is another way to present the keywords in the tree diagram. So we have the let's say this is the most popular keyword in that, and many other things. So after that, so this is a example to do the fusion of the visible and the infrared image, and they have this researcher created this GitHub website, and he collected a number of algorithms, totally 20, And they also have the evaluation matrix can be used to assess the fusion quality. The example on the left side, I say you have the visible image, you have the infrared image, and you can perform the pixel level fusion. You got this one. Then you applied the matrix to understand the quality, the results of your fusion results. So actually, we did a research years ago at comparative study. This is a tricky thing because when you look at the multiple matrix, each matrix tells you about maybe one aspect of your solution, right? So you have to look at them all, not just one of them. So this is the issue. So the question, sorry, with this type of work, yes, I think now people still publish about this pixel level fusion. But my personal opinion is this is not significant as a research. Why I'm saying that? If it happens 20 years before, good, that's excellent. But now let's say you got the fusion image, how we can use that? Who use that? So let's say if you feed this image to your deep learning network and your network is happy to find the target you're looking for, better, you did the right job. But it's not if you just present the people for their eye to see that. Why we have to see something beyond the visual spectrum? I like the picture in the visible spectrum. Why do that? But they argue that you have the matrix tells you it's better, right? It's better. So I think even for these conferences, people still submitting different sophisticated solution or architecture or framework to do this type of fusion. When I received that submission, I'm sorry, I just reject that. I think this is not, I don't see any breakthrough for this type of research. And I don't know how people using that. That's my question. But I gave the editor a comments that say, to be fair, because one of the author they justified, okay, this one has been published on the TIP transaction, so why I cannot publish? So to be fair to the author, I say try to weight the other reviewers' comments more than I do because I have my personal opinion about this type of research. Anyway, so the other thing is you have multiple matrix. But how significant? They say, okay, I improved 0.3 in terms of this metric. How significant it is? So I think we need to justify this from a different perspective. So therefore, we develop we implement the statistic comparison. I have this package using R. If you need that, just let me know. So let's say when you compare two algorithms, do this static testing. When you have the multiple one, larger than 5, you go this way. Smaller than 5, you go that way. So the difference, let's say you have 0.05 improvement in terms of your matrix. How significant it is. So some static testing may tell you this is a significant, this is not. So we publish this again in the information fusion of that. So then I did an exercise a couple years before. So I searched more than 40 publications about this topic. I grabbed their experimental results from their paper, put it in an Excel, and write my R package and work on this. So my finding or my observation is 35. This is 14 out of 40. Show significant difference based on the comparison, right? Only less than 50, that is significant. Even though they got the paper published, they show the difference of the number. So the statistics tell you, maybe not. Okay, so this is one. The other topic is how we can enhance the visible image from the thermal image. For example, this is a paired visible image and thermal image. So if you do the pixel level fusion, you got something like this. Again, I tell you, this is not good for your eyes. Let's say if we can enhance the visual image with the thermal image, but we still got a result in the visible spectrum. So that is good for your eye to see that, right? So this is, we propose a solution and publish in this journal. I think this is the way how we can enhance the visible image from the thermal image. So the other consideration is, let's say we have a thermal image. We only have the thermal image. I want to present to a human observer. So the first way you can do that, you can convert or translate into a grayscale image, and then you can colorize that. So human eyes will appreciate the colored image and grayscale image. So in this solution, we propose texture net, how you can convert or translate the AR image to a grayscale image, and how to convert the grayscale image to the colored image. So we published this on the optical engineering. So this is the architecture and solution of this. So I ignored the details. I told, okay, there's something. This is the evolve from the cycle GAN and do some modification. We did this. So then we use the Sensi-AC data set. So the data set, this is a good data set. They have nighttime, but nighttime, they only have thermal image. And daytime, it has the visible and mid-wave image. We have this number of the images. We use this and compare with the some available solution. And we say, okay, ours looks better. So then we do the colorization. We don't, we just shopping, do some shopping, get some off-the-shelf solution from the literature and looking at this and the number, the evaluation. Actually, we adopt the image quality matrix to do the evaluation. And it tells us, okay, this one, I think this is this one is the best. But I would see this one is more like the real life. And we also have some numbers here. We use the multi-criteria decision making. This is a TOPSIS to get a comprehensive evaluation from multiple metrics. So here is the just a short demo, because we translate that. So this image can be used because the information does not lost, right? So we can still do the target tracking from the translated image. Let's say from the image quality assessment, yes, and from the end use perspective, it can be used for target tracking, right? So this is the idea. So the other one is, if we present the image as an object target, so this is actually about the target detection. Again, I checked the some statistics information about this. And so we did one work that is for the liquefied natural gas leak detection. So the challenge is that is liquefied, not a rigid object. So the shape varied over time. Not many literature reported their study on this. And especially this is from the thermal imaging. So the leak detection that is significant for the oil and gas industry. So we're monitoring the above ground, let's say, pump station, oil and gas pipeline. And if we can detect that, there'll be a huge value for the industry. Okay, so we propose a foreground fusion-based detection for the IR image to detect the potential leak here. So this is a work with the industry in Calgary. So the solution here, we have the foreground image together with the IR image as the input and feature extraction, fusion, detection. This is the basic solution we have here. So again, I ignore the details here. I just we have the publication. You can check that. So if we just use the foreground, because this type of things detect the change, background subtraction, that is a solution. If we just use a foreground as an input, we still have some false alarm. But if we use both of them, we can successfully detect the real leak for the gas, right? So here is the ground truth. This is the other solution. This is our solution, which is faster, which is not. And we got some number. We say, okay, this is good for us. So with the for target detection and target detection, object detection. So with the specific data set, there's a challenge. Object scale variation, small and large object, complex background, let's say like this, and poor illumination conditions. And recall there are many other factors affect your thermal imaging measurement, right? But this data set, they have some we can use this for this. Okay, so, and they also have a different object, but unfortunately not enough to train a model to do the classification. So this is not a very complicated solution. We just do some exercise, how we can get a composite input. For example, we use the visible, the motion, the thermal imaging to generate a pseudo composite image as an input to a target detection framework, and we detect the target. And this is, I think this is published on optical engineering. So there's a different module, combine them and feature detection. And here is region proposed. And this is the classification of that. So finally, we found, okay, this is better. But okay, this is just to give you a idea how this works, right? Okay, so, and we did a research, let's say distance, the variation in the scale. So if you detect about 5,000 meters away, if you detect about 2,000 meters away, what change, right? So one observation we found, okay, at the distance 3,000, there is a big change of this, the performance drop, right? So then we look at why this happens. So we calculate the signal to noise ratio based on our definition of this signal noise ratio about the complexity of the background. We found that, okay, at this distance, so this is a lower signal to noise ratio. That's why that happens. Okay, so yeah, this is for some work we did before, but you say, don't stop now, please come to the PBVS. You have more reason to advance on this. This is one. For future research consideration, this is the most important I want to share with you. So this is the research situation here. So let's say there's a different algorithm. When they want to claim the credit and validate their solution, they say, okay, let's do a comparison with others. And they choose the data set. And they say, okay, for each data set, I'm the tallest one. So I'm the best. Okay, totally ignore the requirement of this application, right? So let's say you are the best, but you have the data set this, but it does not meet the requirement. But nobody asks what is the difference of data set. So my students work with a company in Montreal. They say, okay, professor, I got a accuracy rate 80%. I mean, it does not make any sense to me because for your data set, you have no information about the data set. What is the size? What is the specification of your target? You just tell me 80%. So if I change another data set, the number totally change, right? So that does not make sense. So then, but this is the real life case here. So people working on this. So now people for the target detection, object detection, they use the 5 matrix, right? So you're familiar with this. Finally, I got this. I do the comparison. I'm the tallest one. They claim their credit at this conference. Okay, but my because my background, I have another language. I do the non-destruct inspection. We have another matrix here. For example, we use the probability of detection. So what is that? So the probability detection talk about the capability of your sensing system. For example, we have a different size of the crack. You use your ultrasonic technique, you use your eddy current. So that system can detect the crack size of this, let's say 22 millimeter with the probability of 90%. So that is most important information. And when you have two entity system, we compare the probability of detection curve. Which one can give me a smaller number of this with the same probability detection? I pay for that. That makes sense. So then actually for our industry, we use the 90-95. You have the 95 confidence to detect size of this, you got 90% of the chance. And there's a chance to improve your detection curve. For example, I have a senior engineer do the work. I have the other way to advance the system to do this. So this curve associate with your technology, your solution, rather than your data set. So that is important because when the end user, I 2 minutes, okay. So you do this, you got the imager, you look at that, where I can see the target from my imager, the answer, you have the algorithm. So when you talk about the system, one is the infrared imaging, the other imaging plus your algorithm. So we're looking for something that can tell us about that. So now about the research data. So what we already have from this workshop and the other things, this is what we have, but what I'm looking for, design of the experiment. You have multiple vectors that may have a significant impact on your imaging system. Should consider that, right? That is the most important. How you can isolate different variable to the experiment tells me about the performance of the system. So this is the toy I have when I work at the Toyota Technology Institute. We have the far infrared, near infrared, and thermal imaging. So once I got everything done, so unfortunately I left. So I have a lot of idea with this this system, but anyway. So summary. So I focus on what can be done, what should be done, and that's for perception. This is a image and the target. So when you're operating in multiple model, I do the fusion. You have to think about the different scenarios, how your system can adapt to that. That's the most important. And the performance should be evaluated in the context of application, not just say, I have the data set, totally ignore the context of application, and just claim your credit by comparing with your little brothers and sisters. Okay, so I think this is a acknowledgement, research collaborator, and my students, and I work with a company in Kelowna. And thanks for your attention, and looking forward to working with you. So any questions? Thank you.
Thank you very much for the presentation. I liked it a lot. We take questions from the audience. Yes, please.
Yeah, thanks a lot for the presentation. I have a question about this leak detection of LNG. So is this mostly the information given by the temperature of the gas or by the spectral composition of the chemical composition? And in general, in this object detection experiments, so how much should we be worried about things like water, for example, where the OH bond is vibrating in the IR? Is this a problem or not? Does it create a domain shift?
Okay, thanks for the question. So the most important thing, as we mentioned, that the thermal imaging system is sensitive to the emissivity of the target. So the challenge for that application is the complex background. So if they have the bird fly over, they have the wave of your tree, the people passing by, that will disturb and mislead your thermal system. So yeah, we say, okay, yes, temperature, that is important. Actually, if you go deeper, that is the emissivity of the target. That is a problem. So our first work is with the thermal imaging detection, and at the same time, we're also looking at the combination with the visible imaging video and thermal video. So working on that. A paper is currently under revision, and hopefully we can publish shortly.
So if it's emissivity, then if my target is wet, then it's changing a little bit the response, right? Because the OH vibration will change the.
Yes, so I think that is why we also detect the change of the image, because we keep a background. Something change, we detect the change, then we look at the, okay, the change of the area, that is the target we're looking for now. Yeah.
Thank you very much.
Okay, thank you.
we take one more question. Has there been one more question over there before? No? So I probably missed that. So yes, please.
Thank you for your talk. I actually have two questions. My first question is, you've explained about colorization of thermal images, but I'd like to hear your views on the opposite side, where you translate RGB images into thermal imaging. And my second question is, most of the images used for thermal nowadays is based on 8-bit images, but we all know that 8-bit thermal images suffer a lot from problems such as automatic gain control and image degradations when hot and cold objects come into play. So what are some possible get arounds to cope with those kind of degradations?
Okay, so the first one is, I just want to clarify that. So we do the translation of thermal image to color image, not a color image back to the thermal image. So I think the motivation is because people's eye favor a color image, right? So that is why we want the thermal image transfer to a format people's eye feel comfortable with. So this is when I see a color image, I can quickly capture what I'm looking for. So this is the motivation. And yeah, as mentioned, that is two-step. First goes grayscale to the color. So we use some people from the grayscale to color. It's well-established research, but we propose some solution how we can from thermal image to the grayscale image. This is our contribution. For the second one, we'll talk about the quality of the thermal imaging. That is, I think that is the issue. Because when we talk about the system, that is the hardware. The other is the algorithm, right? So that's a combination of the two. So when you talk about the algorithm, you're totally ignore the hardware. So that is, I would say, two of them, right? So for your question, I think we should look at the solutions which can further improve the quality of thermal imaging, right? Say enhancement, super resolution, denoising, and many things. But again, all these efforts should be justified by your targeted application, how it benefit from your effort on that. So that's my comment. Okay.
Okay, we have to continue, unfortunately. I have some more questions, but I might ask them later or something in a direct discussion. So thanks, speaker, again, please. Thank you.
Yeah, so you're welcome to Corona with your questions. Thank you.
Okay, so as I mentioned before, we will now continue with session 2 as planned, which means that we will have, I think, 5 presentations, if I remember correctly, and the first presentation should be remote. Is the speaker of the presentation spectral transfer guided active domain adaptation for thermal energy present? I ask again, is the speaker of the spectral transfer guided active domain adaptation for thermal energy paper present? If this is not the case, we will show a video because we have a pre-recorded.
Can we check the chat?
Maybe? Yeah, I'm already checking the chat, but I haven't seen the name of this guy in the chat, unfortunately. So this is a different author.
Yeah.
So I think that the person is not present, unfortunately. So therefore, we have asked the authors to record pre-recorded videos so that we can show at least the presentation in case something goes wrong. And today many things go wrong. So we may want to have a look at the video. I start the video and I hope that we will be able to see it Sorry. We didn't activate the sound forwarding for the remote attendees after we changed the laptop, so we have to now do it now. There's a chat box, I think, right? Yeah. Okay, cool. So, okay, for the remote attendees, you hopefully should have sound now. We continue with the presentation if I can. How can I minimize that? Maybe move it to the top.
Adaptation methods assumes that we do not have access to the labels of the target domain. These methods are called unsupervised domain adaptation. However, in real life, we can label some data. Even if we can label a really small portion of data, that will boost our performance because we deliver knowledge from an unknown domain. Regarding this fact, which portion of the data should be labeled is a very interesting question. When we consider the domain shift between our labeled and unlabeled data, we pass to the active domain adaptation. At this point, we saw a room for improvement. When the domain gap is considerably large, as in the visible to thermal task, we may conclude that the methods without explicit domain adaptation cannot achieve their full potential. With this in mind, we propose a spectral transfer guided active domain adaptation method in order to achieve higher performance in thermal domain while reducing the domain gap between visible and thermal spectra. Our proposed spectral transfer guided active domain adaptation method is illustrated in the figure. First, we change the low frequency components of the labeled source samples with those of unlabeled target samples. The transformed source samples are then fed to the feature extractor. A linear classifier is trained along with the extractor. We sample from the target dataset according to a query function. Once the selected target samples are labeled by Oracle, we utilize the selected target samples in the training of the extractor and the classifier with their labels. In the inference, target samples pass through the only backbone network. Thus, inference with our proposed method is remarkably simple. The Fourier transform of an image can be described as the equation 1. A mask can be defined as whose value is 0 except for the region in the center. Beta is a value between 0 and 1. It controls the mask region. We can define a spectral transfer as in the equation 3. The low frequency component of the amplitude of the source sample is replaced by that of the target sample. The phase component of the source image is unchanged. This altered spectral signal is then mapped back to the image domain. The output has the same content as source sample while it constitutes the style and appearance of the target sample from target domain. Using all of the data arises the bias towards areas in the source domain where the data samples are densely placed. Class imbalance problem in real-world applications amplifies this bias. Moreover, this bias prevents the query function from selecting informative target samples. Rising from this fact, a categorical wise margin loss with its selector property can be employed to supervise the network. Hence, considering the spectral transfer, the overall loss function can be denoted as equation 4. M is a hyperparameter to control the margin width. Here, only the uncertain samples contribute to the backward gradient. We can focus on the target samples that are placed near smaller gaps between categorical clusters in the feature space. Furthermore, ensuring the gradient from loss term and the margin sampling term present similar orientations in the feature space will guarantee fast conversion to a robust state. Considering these, we can define the query function as in the equation 7. In the query function, lambda is a hyperparameter and pointer bases define the cosine similarity. Since we do not have access to the labels of the target samples, the gradient from the loss term can be estimated. We employed the RGB to thermal domain adaptation setting, which is recently proposed by Akka et al. The setting consists of two datasets, namely FLIR IDICE as a thermal dataset and MS-COPO as an RGB dataset. The images in both datasets originate from the square bounding box annotations of the object, i.e. bicycle, car, and third person. The per-class classification accuracy results are reported in Table 1. The results show that our proposed method outperforms the state-of-the-art models. According to per-class accuracy, our method achieves the best performances on classes bicycle and car. Although S3 performs well for the person class, the accuracy of that class on other classes shows that the model overfits to person class, which is an abandoned class in the source domain. On the other hand, our approach achieves more balanced performance for all classes despite the fact that the source dataset is imbalanced. Our method also increases the performance of the base method STM in the bicycle class, which is a very few samples in the source dataset. It's important to underline this situation because real-world applications usually include imbalanced classes. Table 2 shows the expected calibration error results. If a classifier's observed accuracy matches with its mean confidence, the classifier is considered to be calibrated. From the results, we can conclude that the source-only model has the highest ECE, which states that the source-only model is not calibrated well. In terms of calibration, our model and STM outperforms TQS by obtaining much less ECE. In parallel to ECE results, reliability graphs demonstrates how far the source-only model is from the perfect calibration line. TQS also exhibits unbounded peaks and gaps, stating that the model is not calibrated enough. On the other hand, our model and STM are calibrated that the gaps in the reliability diagram are smaller. Since the calibration of STM is better than that of TQS, we have chosen the STM as our base approach. Consequently, our model is more calibrated than TQS and comparable with STM in addition to achieving higher accuracy. We present visualization of the feature representation on the thermal domain with TSNE for qualitative analysis in the figure. The features originating from the source-only model cannot be discriminated, while the STM and TQS discriminate samples from different classes. On the other hand, our model can isolate the samples from the bicycle better than those models. Furthermore, we visualize one select sample from each class, bicycle, car, and person in the figure. We can see that the samples from the classes bicycle and car contains a person object, and the sample from the class person contains a bicycle object. This situation makes those samples ambiguous for the trained network, hence the query function select those samples. In the study, we propose a spectral transfer guided active domain adaptation method in order to examine the efficiency of combining visible spectrum and thermal image modalities by taking advantage of the active domain adaptation. Experiments demonstrate that our proposed approach better than state-of-the-art active domain adaptation methods by reducing the domain gap between RGB and thermal domain.
Okay, that's it. Unfortunately, we cannot take any questions because the author is not present, not in person and not remotely. So, but of course, in the paper, you will find the contact details to contact the author if you have any questions. What we will do now is we will continue with our session 2. And while I ask Miriam to come to the front for the second presentation, I also want to ask if the authors of the third and the fourth presentation are present. Is this the case? The third one? Awesome. So when after this presentation finished, please come to the front and bring your slides on a USB stick with you so you can directly start the slides from the USB stick. And the fourth presenter, is he present? No. So I'm asking for Aditya Kasliwal. No. Okay, so we will double check later. Okay. In the meantime, now we have to go to the non-presenter mode. Yeah, but the thing is the screen sharing is failing with Zoom today. We cannot use this presenter mode, so we have to go to the duplicate mode. It will not. Otherwise, you see this is what the remote attendees see.
Oh,
So they will see your notes and all this stuff. Then, well, we all have to do some improvisation today. Unfortunately.
Can I bring my own laptop?
Oh yes, of course. No, she will bring her own laptop to see her notes. That's of course fine. Okay. You have two options. You can put it here, or if you like, I can also hold it for you.
No, so.
Well, okay.
So good morning, everyone. I'm so thrilled to be here. I'm Mariam, and I will be presenting our research paper on object detection in infrared thermal imagery. The paper called IR Reasoner Real-Time Infrared Object Detection by Visual Reasoning. Let's start with addressing the challenges we encountered in object detection using thermal imagery. Actually, traditional CNN often couldn't extract high quality features because of some challenges like small size target objects, image noise, background clutter, and also relying on only CNN-based methods is not may result in unreasonable predictions. And current real-time state-of-the-art methods are generally CNN-based detectors. On the other hand, there are transformers-based detectors which outperform CNN ones, but they do not have real-time inference speeds, which is actually critical for autonomous driving like applications. Hence, in this research, we propose a visual reasoning-based one-stage IR object detection architecture for real-time critical applications. So let's continue with the proposed reasoner model. In this model plays a crucial role in enhancing the performance of object detection models while maintaining the inference speed. The reasoning model takes as input the feature maps extracted from. Can I red dots?
Wait a second. We'll move it here.
Okay.
Is it better?
But I cannot see the red dot. But you can see my mouse, right?
You want to have a laser pointer or something?
Oh, okay, no problem.
Okay.
The reasoning layer takes feature maps extracted from convolutional layers, and it actually enriches the representation of extracted feature maps, and then we concatenate and fuse feature maps and reasoning layer output. We use multi-thread attention to capture relationship between image regions. So by incorporating this model, we can capture semantic and spatial relations between image regions in real-time inference speed for speed critical applications. Let's continue with our experimental setup. We use a FLIR-ADAS dataset, which is a widely used dataset for thermal object detection. This dataset provides us both visible image, 8-bit enhanced infrared images, and 14-bit raw thermal images. It consists more than 25,000 fully annotated frames with 15 different object categories. We use only car, people, sign, light, and bike classes. And we use 14-bit raw infrared images, and we normalize them into the range of 0 to 1 by dividing. This was our pre-process method. And we use 4 NVIDIA Tesla V100 GPUs to train. The batch size is 8 images per GPU, and we trained from scratch all models. We use default hyperparameter and augmentations, except color augmentation. So let's move on to exciting part, our results. We use average precision for evaluation. So as you can see, there is a consistent increase in average precision for all models, and the highest impact observed on small objects. Furthermore, reasoner variance maintained real-time performance with slightly lower FPS values when compared to baseline models. So let's move on to the analysis part. I will show you the what actually reasoning model is capable of. The leftmost image is ground truth. The middle one is our baseline in YOLO V4, and the rightmost one is our reasoner model. So as you can see, baseline could not detect the signs because the sign is not that obvious in infrared. But our reasoner model incorporates the successfully detect the signs by using semantic and spatial properties of image. Here are another example. In this one, it's a YOLO P6 baseline in the middle one. As you can see, there is a false prediction as a traffic sign on building exterior. But actually, our reasoner model compares the sizes of traffic lights, and actually it reasons that there shouldn't be a traffic light on building exterior. So in our last figure, we can see that there is a group of people which is occluded, and the IR signature is not that obvious. So baseline mispredicts them. But the reasoner model actually correctly predicts and distinguish the persons. So reasoner model is enable us to get more accurate object detections even in challenging situations. So as a conclusion, this rich research paper introduced a novel reasoning model for object detection in thermal infrared imagery. The proposed reasoner variant significantly improves the detection performance, particularly for small objects. Our model maintains real-time operation, making them suitable for practical applications. We believe that our findings contribute to the field of object detection in thermal infrared imagery, opening new possibilities for improved performance in challenging scenarios. We hope our research inspires further advancement and applications in this area. Thank you for your attention.
Thank you very much. Nice work.
Thank
Do
you.
we have questions in the audience? Yes, please.
Quick one.
Yeah.
Maybe I missed it. Can you comment a little bit more on the change in the architecture you proposed? You introduced a self-attention model, but why this includes a speed up and not fully?
Actually, the transformer model is not currently in real-time operation speed, but we need the reasoning ability from transformer to enhance the CNN extracted features. So we used one reasoning model to actually get the more enhanced feature maps from CNN. And we introduced just one reasoning model layer, and it's actually increases the performance, but there's a slight FPS drop.
Oh, okay, there is an FPS because I was surprised. So I misunderstood. So
yeah,
okay. So
there is. It's not speeding up, but it can maintain still real-time operation speed.
Yeah, sure. Thank you.
Okay, a quick one.
It's a good question. You said you used you normalized 14-bit images for data. Did you normalize them yourself, or did you use?
We didn't use any other. Like we just divide them into like 2 power of 14. Like we just normalize them by dividing. No, we didn't do any preprocess because we actually analyzed the preprocess methods, and actually the CNNs can do preprocess without.
Clear already comes with 8-bit.
Yeah, we didn't use it because we want to use the whole information that captured in image.
So why did you consider using transfer line?
We didn't. We just only used YOLO baseline. It's from scratch.
So we have one last question from a remote attendee. He is asking, how do you handle the challenge of to differentiate persons from other very similar classes in the context of thermal imagery, such as dogs from a distance, for example? So that with a similar appearance, how do you differentiate between these object classes?
So we didn't use dog class and other classes. We just use 5 class. We only use car, people, sign, light, and bike class.
And you assume that they have like they do not really look similar, right? So I think that somehow answers the question, I guess.
Yeah, we just ignored these classes because the number was insignificant.
Okay, got you. I see. Omar, I hope we somehow answered your question. Okay, we have to stop here and to continue. Thank you, Mariam, again for your presentation. So we will now head on with our third speaker of this second session. It's Jingjing Zhang. That's me. Perfect. Yes, of course. It sounds good. Yep, here we are. And this one I did, right? Yeah, cool. So again, we have to go back on this. Oh, yes, that should do it. Okay, so Jingjing, the floor is yours. I appreciate it.
Good morning, everyone. My name is Jingjing Zhang, and I'm from University of North Carolina at Charlotte. Today, I'll be talking about our paper on photometric correction for infrared sensors, especially for thermal infrared sensors. Despite of the many advantages of thermal cameras, but the performance of traditional computer algorithms that were designed for electro-optical imagery does not directly translate to the thermal domain. This is primarily because thermal cameras, surprised that some images block the part of the text here, but never mind.
Is it pointer or something? Or what
no, it's this image. I guess the PowerPoint version. This image is kind of blocking part of the text.
Yeah, maybe that can happen with the formatting sometimes.
But yeah, it doesn't matter. Where was I? Yeah, the performance of traditional computer algorithms that were designed for the electro-optical imagery does not directly translate to thermal domain. This is because for thermal cameras or thermal sensors, they have different characterized than that are very challenging for those computer vision algorithms. And one of the biggest challenges is this photometric inconsistency due to the rapid automatic gain control of those thermal sensors. That is saying, as the hot object move in and out of the field of view of the camera, large region of the pixel saturate, and those thermal cameras adjust the automatic gain to darken the image to attempt to avoid the saturation. So this invalidates the resulting change can be very dramatic from one frame to the next. Just as shown in this example, we see the side of this vehicle and also the tree behind it. The color of the or temperature of them are very inconsistent in the subsequent frames. So this behavior invalidates the photometric brightness consistency assumption that are enforced in many traditional computer algorithms. So the good thing is the behaviors of this of the uncooled microbolometer devices or the thermal cameras are known in the literature. So we can provide a solution to correct those photometric inconsistency. So there are typically 2 stages in when a microbolometer generates a pixel value. One is the heating process, and another one is a cooling process. During the heating process, an uncooled microbolometer it requires a certain portion of each frame time to integrate signals. So that means for high speed temperature measurement with short frame time, usually a microbolometer does not have sufficient time to converge to the actual scene temperature to be measured. And another stage is the cooling time, which is when the shutter is closed. So the microbolometer does not have a reset mechanism to reset the integrated signal from the previous frame. that is saying that when the next frame starts, yeah, you can see the mouse. When the next frame starts, the sensor, there is a hit residual, or there is a memory from a signal memory from the previous frame left on the sensor. This residual will offset the measurement in the subsequent frames. So to correct such behaviors, to get a correct measurement of this of the thermal temperature or the pixel values, we propose a novel photometric correction model for those microbolometer sensors. And then our model, corresponding to the two stages mentioned in the previous slide, our model contains two different submodels. One is heating model, another is cooling model. So the heating model characterized IR pixel response during the frame exposure. So it's basically the general idea is we're trying to estimate the steady state pixel value if the sensor were given to sufficient time to absorb the heat and convert to a steady state pixel value. So here we use a first order system. We use a first order system to simulate this process. The IMT here is the pixel value that measured by the sensor, and the ISS here is the steady state pixel value if the sensor were given sufficient time to converge. And tau h here is a heating parameter or heating consistent if we use the terminology of the RC circuit. So the heating model is trying to solve for the steady state pixel value. And another submodel is the cooling model. Cooling models characterize IR pixel response when the sensor is not exposed, it's closed. Similarly, we're using another first order system to simulate the process. The goal here is to estimate when the next frame starts, what is the heat residual on the sensor. IMT still is the pixel value to be measured by the sensor. The I naught here is the I naught here is the initial condition, which is the pixel value measured by the previous frame. Oh my god, I need my coffee. Tau c here is the cooling consistent. So combining this heating and cooling model, we have this combined model here, which gives us at any time in this frame sequence what the correct pixel value should be at any time in this frequency in this video sequence. Oh, I really need a coffee. Here we're providing a virtual example of a virtual evidence of the improvement brought by our photometric correction model. So this is an example I showed in the previous slide. So the correction result is at the last row. You see, after applying the correction model, the side of the vehicle and the tree behind it, the pixel value of those areas are more consistent in the subsequent frames. Contrast to the raw IR image or the non-corrected IR thermal infrared images. We also apply our correction model to object tracking problem. So here we're trying to track this person, the trajectory of this person, and the statistical result. We compared the trajectory estimated from different algorithms using different approaches, and the statistical results are shown in this table. Here is this table indicates that after applying the correction model, we compare the similarity between the trajectory and the ground truth. So the table here is saying that after applying the correction model, the trajectory estimate the estimated trajectory is more closer to the ground truth than other algorithms or than without applying the correction model. We also apply this model to a structure for motion problem. Here we try to reconstruct the scene as the car is driving along this road, and the figure on the right is showing that after applying the correction model, the photometric correction model allows more points to be tracked in this structure from motion problem. That is saying that the solution can generate a denser point cloud. The structure from motion can generate a denser point cloud, which means we have more details in our point cloud reconstruction. We also show here's a visual example of the after applying the model, the structure from motion solution is able to maintain more details, not only to provide more details in the point cloud, also generates less noise than only use the RGB images. Well, I'm not showing here, but without also less noise and more details than without using our IR images, but without the photometric correction model. So this figure here is a statistical visualization that is saying that after applying the model, the structure from motion solution can generate less noise because it achieves the smallest noise error, mean value error, and the smallest variance. So this wraps up my presentation here. Thank you very much.
Thank you very much. We can take a quick question. Yes, please.
Yes. Thank you for.
You were the first. I'm sorry for that. Yeah.
Just a quick. Is it a real time?
No, that's kind of out of scope of this project. No, well, so it's not the focus. It could be real time, but it's not the focus of this. But we're just trying to correct the pixel value. So the real time performance is not a consideration of this project. Yeah.
Sorry, we have to continue.
Oh,
here.
yeah, no
So
problem.
thank you very much again.
Yeah. Can I take
Yes, we do. Yes, after we close the presentation. Otherwise, there will be an issue here. In the meantime, I discovered that for the next presentation, where the speaker is missing, thank you very much.
Thank you very much.
They uploaded a video in CMT that I just downloaded, and so we have the chance to now hear a video of the presentation of the fourth presentation of the second session here. I will get it started immediately. So here we go.
Hello, my name is Aditya Kasliwal, and I'm going to present a paper titled Core Fusion, Contrastive Regularized Fusion for Guided Thermal Super Resolution. The authors of this paper are Pratina Seth, Sanchit Singhal, Shriya Ralabandi, and myself. We all are undergrad students of Manipal Institute of Technology, India. We present a novel data fusion framework and regularization technique for guided super resolution of thermal images. The main motivation is to enhance the visual quality of thermal images captured by low-cost thermal cameras using thermal image super resolution techniques. This approach aims to reduce the reliance on high-quality hardware and offer a more accessible and equitable solution. Thermal image super resolution is particularly useful when original thermal image has low spatial resolution or is pixelated. RGB images have been imported for years as a primary means of capturing and displaying visual information, but their inability to capture information relevant to infrared radiation has made thermal image preferable to capture objects beyond the human spectrum. Thermal images are captured by thermal cameras, which are passive sensors that detect infrared light at temperatures greater than absolute zero and don't need any external illumination. They are also not affected by environmental conditions such as snow, fog, or haze, as a result of which they are useful in detecting sources of heat or other applications in such conditions. But the cost of good quality thermal cameras are quite high, because of which software-based approaches of single image super resolution has emerged as a viable option to enhance image resolution in thermal imaging, and especially for thermal images with low quality. Guided thermal image super resolution enhances the image resolution by utilizing low resolution thermal images and high resolution RGB images as inputs to generate a high quality thermal image. Visible image super resolution has been a popular research topic for over a decade. Deep learning techniques such as CNN-based methods provided high performance in this domain, which led to further research in thermal image super resolution. GAN-based and channel splitting-based CNN architectures were introduced for this, as well as in guided thermal super resolution. Contrastive learning, a self-supervised learning technique that improves the performance of models by using the principle of contrasting samples against each other to learn attributes that are common between data classes and attributes that set apart a data class from another. having frameworks such as SimCLR, a simple framework for contrastive learning of visual representations, which outperform previous methods for self-supervised and semi-supervised learning on ImageNet, as well as SIP-SRNet for low-resolution thermal image enhancement. Multimodal learning has risen over the past decade, which involves the development of models capable of processing and analyzing multimodal information uniformly. The missing modality problem, a frequently occurring problem in real-world scenario, has seen some work done in the form of action MAE, but little work has been done in super resolution using contrastive learning and providing a promising solution to the missing modality problem. We use a new dataset provided by the 4th Thermal Image Super Resolution Challenge, Track 2. The dataset consists of registered pairs of high-resolution visible and low-resolution thermal images of the same scene in 640 x 480 resolution, captured using cross-spectral sensors. We use 190 pairs of such images provided to conduct our experiments, with 160 used for training and 30 for validation, and the remaining 10 were used for the testing phase by the organizers. We conducted all of our experiments on validation dataset only due to the non-availability of the test dataset. We propose Core Fusion, a unit-based architecture with 2 encoders and a lightweight and novel data fusion model that is robust and computationally efficient, and a promising solution for dealing with missing modalities. Similar to the unit architecture, the encoders work independently to downsample the input image and extract features at different levels of abstraction. The first encoder is designed to receive the high-resolution RGB image, while the second encoder receives the low-resolution thermal image that has been upsampled using bilinear interpolation to a size comparable to that of the high-resolution RGB image. The architecture consists of 2 parts, a unit-based model architecture incorporating 2 ResNet34 encoders, and 2 contrastive modules that receive the final features F1 and F2 from both the encoders. The resulting outputs Z1 and Z2 from the contrastive modules are utilized to compute contrastive loss, which is scaled using hyperparameter beta and is then added to our final loss. Features of the proposed architecture include multimodal fusion using element-wise maximization while encoding, contrastive regularization, resilient in case of missing modality during inference, multi-objective loss, effective multimodal contrastive learning with small size dataset. We proposed a multi-objective loss function, which is a combination of various losses such as mean squared error loss, peak to signal noise ratio, the structural similarity index, contrastive loss. The final loss in our paper is determined through meticulous testing of a combination of various hyperparameters. During our experimentation, we analyzed various activation functions such as sigmoid, relu, and tanh for the output layer of the model. Our observations revealed that sigmoid was ineffective as it significantly impacted the extreme values. We observed that ReLU produced favorable outcomes, but we encountered a significant issue when transforming the model's output image from float to integer ranging from 0 to 255, resulting in a noticeable performance decline. The best results were observed using tanh activation function for the output layer. The proposed model is trained with Adam optimizer with the set learning rate of 10 to the power minus 4. During training, only horizontal and vertical flip augmentations were applied due to the given thermal image's low resolution, as more complex augmentation result in a significant loss of thermal information. The model is trained with different beta values ranging from 0 to 1 over the course of 500 epochs to explore the impact on the model's performance. We conducted experiments by varying the hyperparameter beta using a single modality, that is the low resolution thermal image or the high resolution RGB image as input for the model. Our observations reveal that higher beta values lead to better regularization and improved results during training. However, this trend is inconsistent when a modality is missing. We noted that as the beta value increases, the model's ability to tolerate missing modality decreases, indicating a trade-off between regularization and missing modality robustness. Therefore, selecting appropriate beta values to maximize the objective while carefully considering the trade-off is crucial. Our experimentation shows that using beta equals 1 results in most favorable outcomes as demonstrated in table 1 with a validation SSIM score of 0.8322 and PSNR score of 28.039, resulting in a noteworthy improvement compared to the outcomes obtained with beta equals 0. However, in the absence of a modality, table 3 shows that the model's performance using only the low resolution thermal images input decreases when beta equals 1 is utilized. Figures 3 and 4 on the next slide display the regularization effect of adding contrastive loss, where we have logged the training and validation metrics for the model with beta equals 0 and 1 for 500 epochs. As observed in the results, our proposed model delivers promising solution even when low resolution thermal image is the only input, achieving an SSIM score of 0.75. With the addition of high resolution RGB image, the score increases up to 0.83. This indicates that the model is using the features from RGB image as guidance and not overfitting on it. This paper presents a novel framework for data fusion and regularization technique for guided thermal image super resolution using two encoders in a unit-based architecture. This is a simple, lightweight architecture and is resilient to missing modality with minimum trade-off. Our architecture gives the best result of 0.8322 SSIM and 28.039 PSNR score with the validation dataset when beta equals 1. The model possesses the ability to be robust in the presence of missing data and maintain performance despite missing modalities, that is high resolution RGB image or low resolution thermal image. Thank you for listening.
All right. Just like before, I kindly ask you to contact you also directly in case you have any questions. Unfortunately, it seems that nobody from the paper is present either here or remotely. So we directly continue with the last presentation of this second session, which will be given remotely by my colleague, Fabian Erlenbusch. Fabian, can you hear us?
Yes, I can hear you. Can you hear me?
Yep, this sounds really good. So feel free to share your screen.
Yes, you have to enable it for me.
I have to stop sharing, okay. This is in Spanish. How can I change it? This is all Spanish to me. It should be good already, isn't it? No?
Now I can share it.
Perfect. Yeah. Okay. Great. Thank you, Fabian. The floor is yours. Yep.
Okay, thank you. Hello, my name is Fabian Erlenbusch. I will present you our work on thermal infrared, single image dehazing and blind image quality assessment, which was done at Hensoldt Optronics. First, let's discuss the research background. On the left picture, as you can see, the visibility in the pictures is clearly decreased. This is a natural phenomenon. It is caused by hydrated aerosol particles suspended in the air. This is called haze. You can see this. This references the visible light spectrum, and TIR, this is the thermal infrared spectrum. While the impact on visibility is generally less problematic in the TIR spectrum, dependent on the particle size, haze can significantly decrease the visibility in the TIR spectrum, as can be seen in the pictures. In the right picture, you can see our motivation. It is to reduce the effects of haze, which is called dehazing. Our main objective was to use the existing research on dehazing in the VIS spectrum and applying it then to the TIR spectrum to hopefully gain valuable insights. This leads to our contribution being to provide insights and further enabling the research into dehazing in the TIR spectrum. Concerning the TIR spectrum, we did survey-like analysis of traditional and machine learning-based dehazing methods. We designed an approach for creating a synthetic haze, and we did an analysis of the applicability of blind IQA measures. Regarding our methodology, you can see here that we used 4 datasets. All datasets contain VIS images. One additionally contains TIR images. They differ in properties such as the haze type, meaning real or synthetic haze, and the homogeneity of the haze. The M3FD dataset does not contain haze at all. We used it to create synthetic haze ourselves. And we used the VIS datasets to do experiments in this spectrum to establish a baseline to then later approach the analysis in the TIR spectrum. As mentioned, we created synthetic haze in the infrared spectrum. On the left here, you can see the so-called atmospheric scattering model, which can be used to model the decrease in visibility of the scene by the particles in the air which attenuate the signal and add air light. Li et al. Proposed an approach which exploits this model to create synthetic haze images in the VIS spectrum. We build upon their model, which can be seen on the right. For our approach, we need a registered VIS and TIR image pair. The depth is then calculated from the VIS image, and we use this later on to calculate the hazy TIR image. Additionally, we add noise to the hazy image. Here in the top row, you can see the ground truth haze-free images. On the bottom row, you can see the corresponding hazy images that we created from the haze-free images. You can observe that the visibility is clearly decreased in both spectra by the attenuation of the scene and an added veil from the airlight. We also did the analysis of the blind image quality assessment measures in the TIR and the VIS spectrum, with the purpose being to test the transferability of the measurements to the TIR spectrum. These measures do not require the ground truth haze-free reference image to then evaluate the quality of the dehazed image. We assessed the usefulness of the blind IQA measures by calculating the difference of the measure on the hazy and the haze-free ground truth image. All tested blind IQAs, they follow the principle, the lower, the better. So you can assume that if the measure works as expected, a hazy image should produce a higher value than a clear image. And on the right diagrams, you can see that the mean delta in the TIR spectrum, the M3FD TIR data set, was the only one which was higher than 0. For fade, this was the case, meaning fade shows some promise for the TIR spectrum. Onto the results in the VIS spectrum. We included various traditional image enhancement, prior-based and learning-based dehazing methods. As you can see, there is no clear picture as to which method or kind of method performs best. In all cases, the performance highly depends on the properties of the data sets, such as haze homogeneity. Additionally, you can observe that the generalizability of the learning-based methods is limited and that some results of fade are unexpected. Finally, we come to the conducted dehazing experiments in the TIR spectrum. On the left, on the table, you can see that the fine-tuned dehaze former clearly outperforms all other methods by far. On the right is a hazy image sample, which has been dehazed by the various dehazing methods. The fine-tuned dehaze former arguably delivers the most similar image compared to the ground truth, the non-hazy ground truth, with also a good subjective perceptual quality. The results of MSRCP also seem interesting from a subjective point of view. We also conducted a task-driven evaluation. We trained an object detector on the haze-free ground truth images. You can see the performance here as the upper baseline in the diagram, the black line. The lower baseline marks the performance of the object detector on hazy images, the red line. We then applied the dehazing methods on the hazy images as a pre-processing step to the object detector. And it can be assumed that if a dehazing method decreases the effect of haze successfully, the performance of the object detector should show that by performing closer to the upper baseline, the black line. And it can be clearly observed that most methods perform between both baselines, but the fine-tuned dehaze former performs best as a pre-processing step. Now on to the conclusion. We showed in a survey-like evaluation that the transformer-based method dehaze former performs best in dehazing TIR images from multiple evaluations. We proposed an approach to generate synthetic haze in the TIR spectrum, and we demonstrated that the blind IQA measure fade originating from the VIS spectrum has some potential to be applied to the TIR images. Thank you for your attention.
Thank you, Fabian. We may take a quick question.
Michael, there are some messages.
Oh, I see.
It's just for my session, Michael.
So it's not a question for the author, right?
Yeah, but maybe for you.
This is my message. Okay. So
It seems that there's no question here, so I think we're good. Fabian, everything was so clearly explained that there are no questions here.
Good.
So thank you very much for
Thank
attending
you
this
also.
session virtually and remotely. So see you soon again back in Germany.
See you soon. Bye.
Have a good time. Bye. Thank you. Okay, so this concludes actually the second session. And now, during the lunch break, for all the people who are not really hungry, like me, we may want to continue with session 1 that we missed in the first block of this workshop because we had some technical issues. So now I want to kindly ask Jasmine to come to the front of the stage here so that we can give her the floor for her presentation. I will open the slides. This is the wrong folder. This is also the wrong folder. Again, have to open it. Sorry for that. Yes, here we are. So this is session 1, and this is your presentation. So let me double check if we can see that. Unfortunately, we have to leave the presenter mode. Sorry for that.
Okay.
So we should be good to go. Yes. So, and if you would like to use a pointer, I realized that the other persons wanted to use it, so I just opened the pointer for you, and you can maneuver with these nice cursors. Okay. So thank you. So Jasmine, the floor is yours.
Thank you. Great. Good afternoon, everyone. I'm Jasmine from the Stanford Computation and Cognition Lab, and today I'm excited to be presenting our work on multispectral contrastive learning with VMaker networks. I'll start with an overview of the motivation for the project. So contrastive learning enables semi-supervised representation learning.
To start screen sharing again. It didn't work.
Okay.
I apologize for that. Here we are. Huh? Again? Oh, is this awful? Zoom is not really our friend today. What will we do here? Did it work? Now it's working. Okay. Yeah, it's working. How great is that? Okay. Thank you. I'm sorry for the interruption.
Okay. So I'll present a little bit of motivation for the project. Contrastive learning enables semi-supervised representation learning for RGB images, and this technique is quite powerful in settings where labeled data is scarce or unavailable. So this figure on the right here depicts learned representations on CFAR 10 that are colored by class. And the graphic shows that samples representations can be roughly grouped by class, which is a remarkable property as the class labels are unknown during training, and yet the representations can discriminate between them. So contrastive learning methods achieve very strong performance on many benchmark image classification tasks, even outperforming supervised methods. However, it's challenging to apply these methods to multispectral satellite images for reasons which I'll describe later. In this project, we show that domain-agnostic contrastive learning techniques can outperform simple hand-designed learning methods on multispectral images. In the next few slides, I'll give a short description of contrastive learning and introduce some terminology. On a high level, contrastive learning is a technique to learn representations by contrasting similar samples with dissimilar ones without using labels. In practice, this involves training an encoder network to map input images to representations from the image to the representation. And then these representations can be used for downstream tasks like classification, object detection, segmentation, etc. So the aim is for the encoder to learn to map the embeddings for semantically similar inputs close to each other. And to do this, it's natural to consider the question of what actually makes inputs semantically similar. The nature of views defines the notion of semantic similarity. A view is a data transformation, which targets invariances that are thought to be useful for transfer tasks. These views are typically human-defined transformations like random cropping or reflections. And here I have a few examples. So in the left, we have a simple input image, In the middle is a sample expert view, which is just the reflection of the original input. And then we have a random sample from the same data set, which is not a view for the input image and is completely unrelated. And this is one popular objective function that's designed to maximize the mutual information between views of the same image. So it works by essentially we want to minimize the sum of the loss terms over all the pairs of views. And this is equivalent to taking the maximization of the negative of this quantity inside. So this means that we want to maximize the numerator and minimize the denominator. And here the numerator represents the similarity between two views of the same image, and the denominator represents the similarity between the current view and all the other samples in the data set. So hence this objective encourages high similarity between views and low similarity with all the other samples. So the choice of view transformation is quite influential in contrastive learning outcomes, and so their design is important. For RGB images, expert views are generated via data augmentation, such as horizontal flipping and color jitter. However, in multispectral images, each channel has different numerical ranges and semantics, so it's impossible to perform some of the standard RGB image augmentations like color jitter. In some cases, it may be possible to extensively search for useful data augmentations for a specific remote sensor and task. However, this requires a lot of time and can be complex. So instead, we propose learning how to generate useful views that work with little customization. ViewMaker networks are one such existing approach, which can learn to generate useful views for inputs across many different domains. The network outputs a bounded perturbation, this one, which is added to the input view to produce a view. And then these views are used in the contrastive learning process, and they're designed to be challenging, stochastic, and relatively faithful to the original input. To ensure that the views are challenging, this ViewMaker network is trained adversarially with the encoder. And this means that the ViewMaker can only be used with differentiable encoder objectives. These networks have been shown to boost contrastive learning performance on less common modalities like speech recordings and wearable sensor data, but they haven't been applied to multispectral images yet. We introduce a complementary approach called the DivMaker network to optimize views for diversity rather than for difficulty. And this is advantageous because the encoder objective no longer has to be differentiable to learn to generate these views. For instance, here we have an input image, and the DivMaker generates these two different views, which are clearly quite different from each other. The objective function is given here. Once again, minimizing this loss is equivalent to maximizing the numerator and then minimizing the denominator. And in this case, the numerator represents the similarity between the current view and the input, and the denominator measures the aggregate similarity between the current view and the other views. So this objective optimizes the original to view similarity and minimizes the view to other view similarity as we desire. In our experiments, we apply ViewMaker and DivMaker to generate views for contrastive learning during training. And we apply these methods to these three multispectral problems, which are classifying land use, local climate zones, and everyday scenes. So here we have a few sample perturbations and corresponding views for input images from two different data sets. The perturbations on the bottom of these two samples are generated by the ViewMaker and then added to the original input to produce these views, which are on the top row. And effectively, you can see that we're learning useful noising strategies to supply new and different information during the representation learning process. And here we have some views generated using the ViewMaker and the DivMaker. The ViewMaker is on the top and then the DivMaker is on the bottom. And notice that the DivMaker also manages to generate diverse views here. So overall, we see that ViewMaker and DivMaker methods perform well on our selected tasks. And just to note that this data set, the RESS data set, is RGB. And so it's expected that training with the expert views here outperforms any of the other kind of more domain agnostic methods. However, we see that for the rest of these tasks, which are fully multispectral, the DivMaker and ViewMaker outperform baseline handcrafted augmentations. And also the DivMaker performance is fairly similar to the VMaker in these last two columns here, except it does not require a differentiable encoder. And this widens the range of DivMaker's applicability because some of the more recently proposed encoder objectives are not differentiable. So we hope that this lays the foundation for broader future work on generating views for contrastive learning and for multispectral learning. Thank you very much.
Very much, Jasmine. Do we have questions in the audience? Yes, please.
Maybe a quick question on the contrastive objective. So there you have the similarity between the view that you generated and the initial image you started from, and then you have to do the similarity with all the other images in the data. So first of all, isn't this expensive? And second of all, second question is, I mean, are you sure that there are not other similar tiles in your data set that are similar to the image you are showing? Like, for example, you know, like a land field, and then you have another land field in your data set, and you are actually putting these apart. So
yeah, that's a very good question. So the contrastive learning assumption is that we don't have any labels available, so we can't compare the labels to find out other similar data samples in the data set. So the supposition is that each instance is its own class, and so that's why we only compare with augmentations of the same. Exactly. But that's also what makes it quite scalable. And then regarding your question on computation and expensiveness, you're right, it can be expensive. You just have to do it in a smart way. And there's been a lot of research into this. I think some methods keep a memory bank, so they don't go over the entire data set here. This is just like a subset of some running window in the denominator. Some actually don't even need to have this denominator. It just depends on what kind of objective function you want to use.
So just a little follow-up. Can I ask you, like, what's the size of the batches you use, and this is fully unsupervised.
Yeah, well, so the representation learning part is fully unsupervised, but then when we come to evaluate the classification accuracy, that's
sure.
Yeah,
Depending on top of
exactly.
And how is the size of the batches?
The batches are 256. Oh, tiles. 32 by 32, I think.
32 by 32 on a pixel resolution of roughly.
That I'm not sure. I don't remember. I think it depends on the data set. So I do have, this is more information on the data sets, but I don't think I have the resolution here. No. It's in the paper. Yeah.
Thank you.
A quick one,
Yeah.
So here, the focus is more on the contrastive approach. So how do you see the other approaches, like maybe master autoencoders or things more like generative? Would they also help in some sense with this problem?
Yeah, that's quite likely. In this project, we really focus on the contrastive learning approach because it's been so successful for RGB image domains that it makes sense that it should be applicable and useful for the multispectral domain. I don't know enough to say about those other domains, but I'm sure there's something out there that would be useful as well.
All right, Jasmine, thank you very much.
Thank you.
Thank you, speaker again. Okay, we continue now with the remote presentation. The presenter is present. It's Abel. Abel, can you hear us?
Yes, I can hear you. Can you hear me?
Well, yes, we can hear you. I stopped sharing the screen, so now you should be able to share your screen.
Okay.
If so, then please do so.
Yes. A second, and I am. No. Okay. Can you see my screen now?
We see your screen. Yes, looks good.
Perfect.
And I think you can start. Yes, feel free to start.
Okay. So, hi everybody. Thanks for attending this presentation. My name is Abel Reyes, and today I'm presenting CPLES, Contextual Progressive Layer Expansion with Self-Attention for Multi-Class Landslide Segmentation on Mars using multimodal satellite imagery. The research team is also integrated by Dr. Said Pahidin, Ryan S., Dr. Sajin Kumar, and Dr. Thomas Omne. So let's start. So this is the outline. I'm gonna go through a brief introduction. Then I'm gonna provide some details about the datasets that we are introducing in this presentation. Also, we are going to give some insight behind the methodology itself, the C+ architecture proposed. Then we will go through the training protocols, experimental results, and ablation studies, and final conclusions. So let's start. So the main purpose of this research is to provide an end-to-end deep learning architecture to facilitate the task of identify different types of landslides from the Mars surface, in particular from the Valles Marineris region, which is, I mean, we picked this area because there is a vast number of landslides, different kinds of landslides in that region. As a matter of fact, landslides occurs when the terrain moves due to natural factors, like for instance, earthquakes, volcanic activity, or heavy rainfalls. Understanding the nature that triggers the landslide will help us to understand actually the morphological transformation of the planet. And since Mars has shown evidence that presumes a similar path to the current conditions of Earth, the study of the Martian terrain could have a potential contribution to estimating the transition related to the climate change that could face the Earth in the near future. So let's start with the dataset. As I mentioned before, we are introducing the multimodal multi-class landslide segmentation dataset. This is composed by the following modalities: the RGB channels, grayscales, the digital elevation models, also slope as a derivation of the DEM model, and a thermal data. Details about how we retrieve all of those modalities, and also how the sources are providing in the paper. In figure 2, you can see a few samples of different patches with all of the modalities and the respective segmentation mask. Regarding to the landslide annotation, so for the annotation, they were actually manually annotated by using visual inspection, by using GIS environment. So this interpretation was based on typical morphological features, like, for instance, flow direction, shape of scars, or area of depletion, and such. The landslides were digitalized as polygons, and then we were using a total of, I mean, at the end, we were compiling a total of 682 landslides, different types of landslides that are actually, it can be breakdown in 130 debris flow, 275 rocks avalanche, and 274 slumps. In addition, what we actually providing as a data set is, so we actually aligned all of the different modalities, and then from the image, from the total image with the 7 channels, with the 7 bands, what we did is to split in different size, patch size actually. We are providing 3 different versions. Each version is represented by the different patch size, and we will make sure that actually each of the patches for each of the different versions is actually having a decent amount of information from landslide. So at least 5% of the pixels will be information from the landslide. So all of the patches that are actually having just background are actually discarded from the final version of the dataset. At the end, what we were having is a total of 122, 240, and 955 patches, corresponding for 256 by 256, 128 by 128, and 64 by 64 pixel size. Regarding to the proposed methodology, so the C+ architecture is actually strongly inspired by the encoder decoding framework, since this is a popular approach and actually a very effective approach for segmentation tasks. But because of the limitation, actually, we want to improve the performance by using this model named the C+. So in the C+, actually, what we are doing is actually imputing like a plug and play model within the encoder decoding architecture. The simplest is composed actually by two different techniques. The first technique is the progression errors expansion. The progression errors expansion is a concept in which each neuron is taken from the input and is progressively expanded following a Maclaurin-Serial expansion of a nonlinear function. In this case, we were using as a nonlinear function in an inverse tangent function. In this one, every node is denoted as SU, in which U means the number of expansions that we are using actually to compile, to compose this term. And then at the end, this term, this final term, is produced by the expansion of, by the addition of each U subsequent component in the expansion. So in equation 1, you can see the mathematical expression for the progressive nervous expansion. In figure 6, actually, you can see illustrated the output, giving an input, the output of, giving an input, the output, the comparison output from the Cples and from the traditional convolution and convolution 3D. And you can see actually how by using the Cples, we can actually leverage the use of the progressive nervous expansion for feature representation, to enhance the feature representation of the multimodality input. In addition, in the proposed methodology, we were using attention mechanisms. The attention mechanisms were actually used right after the output from the progressive nervous expansion. The input is actually the expanded term for each of the attention mechanisms. Actually, we were testing two different attention mechanisms. The one was the first one was the dot product attention, which is one that is involving the global attention and considering all of the sources in the input. In this case, all of the expansion. And also we were using the multi-herself attention, in which we were actually using as a query the key and the value, the different expansion, different terms of expansion, expansion 1, expansion 2, and expansion 4. At the end, the Cples, as I told you before, is strongly inspired by this encoder decoding framework. So what we do is to plug the Cples block between the skip connection for each of the each of the encoder and decoder blocks. And also we change the encoders in order to capture more information, more valuable local representation. We were using dilated convolution instead of regular convolution. Continuing with the training protocols, actually, as a loss function, what we're using is combined loss function, in which we were using two different terms. One for was the dice loss coefficient, and the other one was the focal loss coefficient, as you can see here, representing in equation 4, 5, and 6. Continue with the training protocols. What we did is actually all of the dataset, as I mentioned before, all of the different types of dataset, versions of the dataset, we split the data in training, 80% iteration, 80%, 20% for testing, and 10% all of the training split. We were taking for validation. We run all of the experiments in one NVIDIA A100 with 40G of dedicated GPU. We use actually that documentation, so we use actually rotation, horizontal, or vertical flick with zoom, reflect field mode. We use different numbers of, we flick the number of epochs for all of the training, so it was 150. We monitoring the best performance actually, and then also we change actually the batch size according to the batch size. So we use batch size 4 when we were using the 256 or 256 patches, batch size 8, and batch size of 16 when we were using 128 and 64 by 64 patches respectively. We were using learning scale rate, starting with 10 to the -3 and then reducing by a factor 0.01. We use evaluation metrics as mean IOU, as one score, recurrent precision.
I better just let you know you have 1 more minute.
Okay, thank you. In the qualitative results, so we can see we tested all of the different batches, and we were using we were comparing with the state-of-the-art unit architecture base, and as you can see here, the C-Place actually perform all of the competing models in terms of mean IU and S1 score. This is a promising indicator that our C-Place model has the ability to effectively balance precision and recurrence across all of the classes. In addition, what we were using also qualitative results, and as you can see, the C-Place achieves a slightly lower precision compared to the state-of-the-art, but we are going to be working on that in the future while maintaining a high recall rate to achieve more accurate and complete implementation of the study. Another important point is in the quantitative results, actually, all of the classes were having a good score. The highest IUU was achieved by the slumps. And then in the evaluation study, actually, we did two different evaluation studies. One in order to analyze the importance of the model component, in which we actually, the results support the idea that actually all of the components helps to the C-Place to perform better than the other competing architectures, as you can see in table 2. And the other one was that by using all of the modalities actually helps to the model to achieve that the best performance. In conclusion, this research were into in this work, we introduced the C+ architecture as a solution for effectively segmenting multi-class Martian landslide. Our research not only examines the analysis of Martian landslide, but also opens up the possibility for similar tasks on Earth. The C+ block, which combines progressing expansion errors and attention mechanisms, serves as a plug-and-play model that leverages the representative advantage. We introduced a unique dataset specifically designed for evaluating the performance of our proposed methods, providing valuable resources for future research in the field. The Martial multimodal landslide dataset used in this research will be, it's actually available for the research community, promoting collaboration of advancement in the field. Thank you so much. If you have any questions, please let us know. Don't hesitate to contact us. Thank you.
Abel, thank you very much. Since we are still running out of time, I kindly ask the people who would like to ask questions to Abel to do it via email after or during maybe the workshop, but we will continue now with the next presentation. Abel, thank you again very much for your presentation.
Okay, thank you so much.
Okay, and the next presenter is not here with us, so we will play again a video. I will start screen sharing again so that we can see this video. Yes, this is working. Okay, we will close this one. And it's a paper called three-stage framework. Three-stage framework with reliable sample pool for long-tail classification. Feng Kai is the main author. He was with us before. I saw him in the chat, but I don't know what is the time now in China. I expected he went to sleep, which is quite understandable. Okay, let's get started with the video.
Hello everyone, I'm Sai Fong from Fudan University. Today I'm going to present our work for PBVS 2023 Multimodal Aerial View Object Classification Challenge. Synthetic Aperture Radar, which I will abbreviate it as SAR later, provides all-day all-weather Earth observation and presents a promising solution for aerial view object classification. The task of Track 1 of the PBVS 2023 Multimodal Aerial View Object Classification Challenge is to train a classifier that maximizes classification accuracy in 10 categories of transportation in the aerial view images. This task poses several challenges. The first is the long-tail distribution of the data set. In the training set, Class 0 accounts for 80% of the entire dataset, while Class 9 accounts for only 0.16%, the ratio of samples between the head and tail classes exceeding 500 to 1. The second is out-of-distribution samples interference. I will refer to this as OOD, samples for short. The test set contains about 5800 images, but about 65% of the images are negative samples that do not belong to any of the 10 classes. The third is the unique characteristic of SAR image. The SAR image has a pretty low resolution and contain a significant amount of noise. It is challenging to distinguish targets from clutter. Moreover, some classes exhibit high similarity and features prone to confusion. To address these challenges, we proposed a three-stage framework with reliable sample pool. Specifically, we propose a three-stage training strategy to learn from diverse dataset distributions in model transfer. The first stage is supervised training, which aims to provide a pre-trained model for the later semi-supervised training. The second and third stages are semi-supervised training, generating pseudo-labels to reduce the model's dependence on labeled data and facilitate knowledge transfer from the labeled set domain to the unlabeled set domain. And ResNet 101 is used as the backbone for feature extraction. In the first stage, the model is trained on the entire long-tail dataset to provide a pre-trained model that has learned rich feature representations. To mitigate the long-tail distribution, we use class-balanced focal loss as the loss function, which reweights the loss for each class based on its effective number of samples. In the second stage, first, we use the first-stage trained model to predict the labels of unlabeled data. Because the model acquires feature-abundant representations, which enables high-confidence samples to perform better in terms of reliability. Such samples match the training set's features and are easier to classify correctly. Then, we select a subset of high-confidence samples and clustered them with the remaining unlabeled samples. Specifically, we utilize the pre-trained VGG16 to extract the features and integrate the same clustering results from DBSCAN and K-means. Additionally, DBSCAN is used to discard certain outlier clusters, which help to filter the OOD samples. Next, a class-balanced dataset was created by combining these pseudo-labeled samples with randomly selected samples from the labeled set. Finally, the first-stage model is trained on this class-balanced dataset. In the third stage, we propose a flow-state reliable sample pool, RSP, and the samples in it will update at every round. So, the RSP serves as a trustworthy pseudo-label source, and we combine samples from RSP and training set to obtain a class-balanced dataset and fine-tune the model with a few epochs. Next, let me introduce RSP in detail. In our task, there are numerous OOD samples in the test set. To address this issue, we propose a RSP to enhance the model's robustness against distribution shift between training and test sets and boosts confidence in in-distribution samples. During the third stage training, we maintain a reliable and dynamically changing sample pool that is updated at every round to ensure that the included samples are always the most representative test samples that fit the distribution of training set. Specifically, at each round, we leverage the previous epoch's model predictions on the test set. And the RSP stores the top-end samples with the highest confidence scores in each class. And the capacity of RSP is a hyperparameter that can be dynamically adjusted based on factors such as the dataset size, model complexity, and changing rate of prediction results between rounds. We conducted ablation studies to evaluate the effectiveness of each stage of the proposed architecture, and investigated the effect of different loss functions. In the first stage, the CB focal loss improved top 1 accuracy by 1.43% and AUROC by 2% over using CE loss. In the second stage, a balanced dataset was created by generating pseudo-labeled samples, leading to a significant improvement in model performance. In the third stage, the top 1 accuracy and AUROC improved by 0.13% and 3% respectively in development phase, 2% and 1% respectively in test phase. As shown in the first table, there are the top 4 results during the test phase of this challenge. Our method ranks first in terms of total score and achieves a competitive top 1 accuracy of 63.20%, and exceeds the second place by 3.35% in top 1 accuracy and achieves comparable performance in AUROC. Additionally, during the development phase, we compared our method with 2 other approaches. a two-stage shake-shake network and bilateral branch network, BBN. The former is a top-performing method of this challenge in 2022, and the latter is one of the state-of-the-art methods for addressing long-tailed distribution. As shown in the second table, our method achieved higher total score, top 1 accuracy, and AUROC than these two methods. That's all. Thank you and welcome to see our paper for more details.
All right. So we have to speed up. So the last speaker of this session, he's already with us. I will stop screen sharing. Perfect. So I kindly ask, Raival, you are with us, right? Can you open the mic? Raival, are you here?
Hello.
Perfect. So feel free to share your screen and start with the presentation. I kindly ask you to stay in time because our next session starts at 3 p.m. and we still have to do some slide transfer before the session starts. So feel free to share your screen and start.
Okay. Yeah. Thank you. Are the slides visible?
Yes, it's not in presentation yet. Now it's in presentation mode. So now we can, you can get started. Thank you.
All right. Good morning, everybody. This is Prajwal from Artificial Intelligence and Robotics Lab, and I'll present our recent work, DeepMao, a multi-scale aware over-complete network for building segmentation in satellite imagery. Humans have been expressing creativity in architecture for centuries. Each building in a dense urban environment is likely to have varied sizes and complex shaped geometrical footprints. And through various remote sensing methods such as electro-optical imagery, synthetic aperture radar systems, we are able to observe these complex building footprints. Remote sensing has more prominent applications such as disaster response in case of floods, earthquakes, and change monitoring for forest and urban cover. A data-driven machine learning approach to monitor urban buildings where the size and shape of each building is taken into account is through semantic segmentation with deep neural networks. Semantic segmentation, pixel-wise classification of a dense, cluttered environment, has proven to be a challenge given the diversity in the strength of the signals provided to neural networks. Deep learning techniques tend to generalize to buildings with high pixel numbers. Here we can see a small crop of an input image, ground truth labels, and their corresponding predictions. This trained model of a unit can predict medium-sized buildings down to the pixel fairly well, but misses out on buildings with small footprints due to the low pixel representation. Small building segmentation is rendered a challenge in such a situation. And I say medium-sized buildings because there are much larger buildings in a full-size remote sensing image. This is a picture from SpaceNet 6 challenge dataset, our primary dataset for this paper, and here is the ground truth label. Tiling of such an image can only go so far before semantic context of large buildings is lost. Feature extraction in convolutional neural networks happen through multiple layers. In an encoder, low-level features are captured in the initial layers, and as the layers deeper, the receptive field increases, making the last layer focus on high-level semantic features. Layer 3's receptive field is denoted by the color yellow, whereas the receptive field of layer 2 is denoted by the color green. Layer 3 therefore has a higher receptive field than layer 2. In a unit, this encoder structure is then followed by a decoder, and this has been the norm for many segmentation models. On the flip side, to solve the problem of missing small buildings, we look to decrease the receptive field deeper through the layers. This is possible through over-complete architectures, a relatively underexplored method for semantic segmentation. Over-complete architectures basically consist of layers in a network that have more neurons than the previous layer. These architectures have been historically proposed to work in the presence of noise. In a convolutional neural network, it would look something like this. Layer 3 has a smaller receptive field than layer 2. This is an architecture proposed recently wherein An input is separately passed to an overcomplete branch and an uncomplete branch that concatenate to provide a prediction. The authors focus on segmenting small features more accurately in an already small medical image. The same cannot be directly applied to remote sensing due to the size of images that are input to the network. Overcompleteness also has harsh memory penalties followed by magnitude slower training and inference time. Hence, we propose DeepMAU, a network that is aware of both small and big buildings when performing semantic segmentation. It consists of an overcomplete and undercomplete unit and an overcomplete branch. The overcomplete branch takes output of the first layer of the undercomplete branch. This layer is passed through subsequently larger layers in a spatial sense through bilinear upsampling. The output of the OC branch is then added to the output of the last decoder layer and passed to the segmentation head. From the GradCam visualizations above, we can see that as the receptive field decreases through the layers, the model focuses on smaller features and is supplementary to the main unit. This modification has about 1% of the parameters of the main unit and is comparable in terms of memory usage and training, and in terms of training time. Our training loss, LSEG, is a combination of dice loss and focal loss that is computed on the final prediction of the network with its corresponding pixel ground truth labels. To increase the pixel representation of smaller buildings in the dataset, we introduce a novel augmentation scheme called loss mix that is self-regulative in nature. We tile the training pairs into a number of patches and compute the L1 loss for each, and pick the patch with the highest loss for augmentation. This learning scheme is introduced after the model has been trained well enough to segment larger buildings, and so the assumption is that we pick patches where more often than not there are smaller buildings that are being missed, and hence increase the number of instances of harder samples. Another visualization of the layers of the encoder of the unit and OC branches where unit shifts focus from low-level features to global features. The OC branch, due to its decreasing receptive field, focuses on low-level features, which is basically small buildings and intricate geometries of larger buildings. For this work, we have used three aerial imaging datasets, namely the SpaceNet 6 electro-optical dataset, along with its synthetic aperture radar counterpart, and India aerial imaging labeling dataset. Here are the results of different models on the SpaceNet 6 dataset. We have provided the F1 scores of varying building size brackets. The first column is for the smallest building footprint size of 10 to 56 meters square, medium to larger building sizes of 56 meters square, and an overall F1 score with all the building sizes considered. DeepMAU outperforms all the models in all building size brackets with an increase of 4.5% for buildings and an increase of 2.5% in the overall F1 score. In the speckle-ridden SAR modality, we observed an increase in overall F1 score of 1%. We also have an increase of around 1% in the intersection over union scores for the India aerial imaging dataset. This is a of performance over various building sizes. Due to DeepMAU's nature of focusing on small buildings and integrate geometric footprints of larger buildings, a bump in F1 score is observed in the smallest and largest building footprint sizes. Here is an example of segmentation predictions of UNet and DeepMAU, where smaller buildings are successfully segmented. Here is an ablation study table where it is observed that loss mix augmentation scheme is beneficial to other state-of-the-art models as well, but DeepMAU's capability to focus on smaller buildings, it is able to make the most out of loss mix and evidently has the largest relative increase in F1 scores. Here are some selective crops of segmentation of the SAR modality, where DeepMAU was able to outperform UNet. And here are a few more examples of DeepMAU segmenting smaller buildings in SpaceNet 6 and the INRIA dataset. In conclusion, this is the first work to focus on small building segmentation, where we propose a novel architecture which consists of an overcomplete branch tasked to focus on small and integrated building footprints. We also propose a novel self-regulative learning scheme termed loss mix, where the hardest to segment patches are used as an augmentation. We have achieved a 2.5% and a 1% increase in overall segmentation performance of EO and SAR modalities. We also achieved a 4% increase in small building segmentation. Thank you.
All right, thank you very much. Since we are behind schedule, as I mentioned before, we cannot take any questions at this time. We apologize for that. And we have to continue now to prepare the next session that starts at 1 p.m. So I kindly thank you for the presentation. And yeah, so thank you again. And I hope to see you again in
Thank
next PBVS. Bye-bye. See you. Thank you.
Sure thing. Bye-bye.
How are you?
Good, thank you. How are you? Well, it could be better, but
Yeah, it's gonna be fine. So I put the slides on the stick, right?
Yep.
That's the way we.
yeah, exactly. So we can transfer the
try.
slides now. That's something.
Here, what is should
We are fine. Yeah,
emit?
this is correct.
It should be both in emit, no?
No. Yeah.
Emit. Emit two.
Maybe better go to this one again because it worked before, so we should not
Okay,
change.
Rafael, can you please confirm us, or someone can confirm you can listen up?
It's clear.
Okay, that's
I'm
it.
good.
Okay, good.
Great. So let's minimize that one, and we can start. Yes. Close that one. We'll go to this one.
That's
it. See it here.
it.
And so, okay, perfect. This is the second slide, right? Is it? This is the second. Okay, yeah, here we are. I will also activate the laser pointer for you. And now we can start with the next session of the PBVS workshop. It's my honor to introduce to you Mr. Jonathan Hu. He's the president of Pleura Technologies, a company located in Canada. And he will provide a keynote on the topic of solving the deployment challenge, moving AI from research to the factory floor. Jonathan Hu is president of Pleura Technologies, a leading supplier for AI and sensor networking solutions for the industrial automation, security and defense, and medical imaging markets. In this role, Jonathan oversees Pleura's research and development efforts and leads the company's long-term technology vision. Jonathan joined Pleura as Chief Technology Officer in 2018. Previously, he was Director of Technology with Global Vision, where he helped develop new automated quality inspection solutions for print inspection applications. He has held positions in software and engineering management, applications engineering, software development, and machine vision, video, graphics, and networking industries. Jonathan has a Bachelor of Applied Sciences, Computer Engineering from the University of Waterloo in Waterloo, Canada, and a Master of Engineering from McGill University in Montreal, Canada. So, Jonathan, thank you very much for being here with us. And I kindly ask you to join me here on the floor to get your presentation started. So you feel free to use this for the pointer and then just the cursors for moving through your slides. Okay, so, thanks so much. Thank you very much for being here. Thank you.
Right. The session after lunch is always the toughest one because everyone just finished eating, very tired. You're gonna fall asleep maybe. So what I chose to do with this session here is really focus on something that is often overlooked in the AI and the machine vision space in terms of all this great research. How do you actually move the research from research to production and the practical viewpoints of that user aspect when we're talking about AI? So less on the technical front, so hopefully a more engaging and fun presentation so that you don't fall asleep, and I'll kind of ramp you guys back up for the technical sessions later this afternoon. So AI hype versus reality. So technologies go through this hype cycle, and I'll go through what that means, the Gartner hype cycles, and AI itself is no exception. Users are typically interested in technology, but they don't know necessarily how to use it. They have these overinflated expectations of how that technology is supposed to work. And what you end up with is a situation where you have users where they think they know how they would like to use the technology. Then on the engineering side, you have the engineers, the researchers who think that they know how the users should be using that technology. And then when you put those two together, that's where you have a gap in terms of, if you look at this image here, how the customer explained it, how the user explains, this is how I would use it. The middle image is how we designed it. And then in reality, what did the customer actually need from a implementation standpoint? So the challenge that we're going to be talking about today is how do you take that hype and turn it into reality for real users? So hype cycle, what does that mean? This is the Gartner hype cycle. You may or may not have seen this graphic here. It applies to different types of technologies and something that Gartner applies And it's always that same curve. So it's a graphical representation of life cycle of new technologies from that initial development phase to commercial availability, as well as the eventual decline. And if you look at how this graph is divided, there are 5 key regions. One is what we call the innovation trigger, the peak of inflated expectations, the trough of disillusionment. It sounds a bit terrible, but that's what they call it. The slope of enlightenment, and the plateau of productivity. So we're actually going to go through those 5 cycles and what those mean in a practical perspective from AI. So when you walk into a factory today, what do you think about? Like how do you think a factory looks like today in modern society? So when I go and ask people and talk to people out there who don't know anything about the manufacturing space, the automatic picture that they have in their minds is this vision here of, well, if I'm getting my laptop today, if I'm getting that projector or any goods that I'm using today, my expectation is that, oh, this should be all robots, computer vision, AI, whether it's regular vision, thermal imaging, sensors for quality control, that's fully deployed in a fully automated environment in the factory. But when you actually go, and I challenge you to go visit a manufacturer, right? There exists a lot of manufacturers where this is the reality. You have people who are manually doing these tasks. They are putting stuff together. They're using their eyes. They're not using their cameras to do the checking and the quality. So you can see already that there is that gap between this is what people think, but this is the reality. And how do you close in between those 2 images right here? Give you another example in terms of autonomous driving. So autonomous driving was really hyped up. Again, lots of interesting technologies around autonomous driving. If you look around today, how many cars are driving themselves? That's still not the reality where we're at, right? So take that and break that down. What have the car manufacturers done in reality in terms of how do you integrate that into my day-to-day? So you come up with technologies where you reposition it in terms of driver assistance. So you're helping the driver do their job better. So that's where you have technologies like lane assist, where all these sensors come together. In terms of it actually still delivers an improvement to the end user, but it's not that full automation that we expected when we started working on that technology. There's still a roadmap to there. So it's really around taking where you want to be, break that down into these phases, and then come up with your different levels and roadmap to where you want to be. So that's one of the approaches and techniques that you can think of from a research perspective. So example here, level 0, no automation. Level 1, driver assistance. Level 2, partial automation. Then you start getting to more and more automation, conditional automation, high automation to full automation. But you never want to jump from level 0 to level 5 right away. And you want to think of what does my roadmap look like when I'm looking to deploy AI for my project. So let's go through a bit the different innovation triggers in that hype cycles, that graph that I showed in a couple slides before. The innovation trigger, talking about AI, it's a relatively new concept for users. It's introduced to the public, especially when you're talking about the customers that we deal with. They're in industrial manufacturing. So they are less about technology adoption. They're very comfortable with your manual processes. So this is an entirely new concept for them in terms of now we can be using vision and AI to help automate their tasks. So then what happens if you get a lot of hype, you have a lot of prototyping, you have a lot of researching to try to figure out, well, how do I use this technology? And actually, when we were working with one of the larger manufacturers out there, one of the largest consumer packaged goods companies out there, they have lots of these AI experiments going on that's happening. But the key question that we asked them is, well, how many of these projects made it to production? And it's astonishing. It's less than 5% of that make it to production environments. So that is a real problem that we need to be looking at and solving from how to get from that experimentation to production. So the natural evolution afterwards is what I call that peak of inflated expectations. So we have lots of the media hype, industry hype around this is what the technology can do, lots of ideal applications, ideal use cases. This is how it would work in a perfect world. Of course, it's not a perfect world, but we keep hearing this technology will replace humans, kind of like autonomous driving again, right? You don't need that human aspect in there. When we're talking about manufacturing, again, people are scared of losing their jobs, being replaced by robots. That's that hype and expectations that the media is actually creating out there. And vendors also are contributing to that because they're really marketing that future versus what is that reality. And the hype around AI factories being all lights out automation, fully robotic, and that AI will be able to find any type of defect. So defects that you're trying to find that are traditionally just visible to the human eyes, they're saying, well, AI can transform all that using vision and the algorithms to make that fully automated. So an example of that defect finding, right? You're taking that manual task, and then now people are really hyped up around this fully automated workflow where they don't need a human involved. But then you get to that point where, well, lots of demos going on. People are looking at what can actually be done with the AI models, with the research, and then it falls into that trough of disillusionment. So that reality sinks in terms of, well, it's not that miracle that's solving all my problems, but it does solve specific tasks very well. But then because it's kind of that shock that the user actually starts decreasing in terms of that enthusiasm level, and then they stick to their old ways. So now that they've learned about the technology, they're asking questions like, what do you mean by I need to collect data to find these defects? Where am I going to find these images of defects? So that reality sinks in terms of, doesn't seem like a practical approach. That is the workflow that we follow when we're doing these AI models, but that's not what the user actually expects when you put it into that actual use case. Then once they realize that, that's where it's bottomed out, and you kind of have that slope that's going back up again in terms of that aha moment that, oh, maybe there's this use case that I could be using the AI for. This is how, now that I understand the technology, I have my user needs, then that bridge between the product design and the user experience aspect is important, because now you start looking at, well, this is what we thought we could do. This is what it actually does. This is my problem that I can actually solve. And you start pulling that together where you can actually see a path of, this is how I can be using it, and take a look at what it can and can't do. And is there enough that it's going to make that improvement in the day-to-day lives of users, versus having to go to that full automated autonomous driving where it's going to completely change? Are there incremental changes that we can apply that are going to benefit that user, even with pieces of that technology? So think of complementary versus revolutionary, and take that roadmap approach in that deployment. So a bit about our journey at Clara. So we are a company that's over 20 years old, and we've been in machine vision space. We supply technologies for cameras, and we entered the AI space a couple of years ago. And the angle that we started off with was the technology angle. So the problem with that approach, again, it was around, here's new technology that can automate everything. The actual users don't understand what that means or how I can apply the AI. And then they get scared, and then they realize, well, I can't do that full automation. So we modified our approach in terms of, well, think digitization versus automation. So your digitization is the process of taking things like Excel spreadsheets that people are doing manually, or Word documents, or all these manual tasks, and you convert that to a digital process. So once it's digital, you can capture that data. Once you have data, then you can take that next step in terms of training an AI model and going further ahead in that AI deployment. So we developed this digital manufacturing maturity model where on the left-hand side, you've got that pre-digital manual process. You're skipping to a next step. It's an incremental step in terms of digitization. The next level 3 is around connecting the factory. To level 4 is that full lights out AI, full automation. So again, you're taking step by step. You're not jumping straight to that automation approach. And we've seen with manufacturers, that's something that's much easier to implement and something that they understand much better than going straight to the full automation path here. And what problem are we trying to solve then? So you kind of think back in terms of, well, how can I use AI to solve a problem that exists out there? And when we're talking about manufacturing, a lot of it is around quality inspection, where manual quality inspections are very subjective. So the problem that we're trying to solve is that, well, humans are well suited for many manufacturing tasks, but the reality is that humans get tired, they get distracted, and that process of digitization and AI actually can help them with processes like these, right? If I ask you to count the number of black dots, this is a trick, but a machine can do it more consistently. And we see in the manufacturing space that manual inspections are 20 to 30% error rates. And then when people are trying to manually assemble products, they make mistakes, and that can contribute to 62% of errors. And by applying AI in those types of steps, then we can actually improve the performance of humans through that digitization process. So as humans, we excel at visual inspection. And it's really around how do you replicate that technology around what we do. So looking at process-wise, what does a human do? And how can AI mimic what that human does in their day-to-day workflow versus trying to introduce this really big change that people don't understand in the first place? And then still have that link in terms of there's still a human involved in that process where it's human assistive technology. So you think of that, again, the driver assistance versus the autonomous vehicle. Think of it as how does my technology help the user to make a decision? And that's typically a much easier first step from a deployment perspective. So I'll go through some case studies in terms of high value electronics inspection. So again, a real world case of how we implemented this approach for the project. So we created this app around visual inspection using computer vision and AI, using sensors to detect defects. These are things, components that are commonly missed by humans. So components that are misoriented, damaged components, solder issues, components that are manually soldered, and labeling issues in that process. The challenge is how do you make, in that case, that human process of manual inspection something that AI can actually help improve. But the challenges here are you want to do it in a way where you're not introducing extra work to the operator, because you're going to get a technical resistance from the operator if you're adding more to their existing workload. So that's a key thing, right? People don't want to do more work, but they want better results and better technology. So you've got to find that right balance. You have to do it in a way where it enhances and speeds up the quality of life for the user. You have to do it in a way that improves the process for the business and allows a way for users to retain control versus the computer taking over completely. So they have to build that level of trust, just like humans to humans. You have to build that level of trust before you say, I'm going to go all in, right? So how we solved it from a labeling issue. So if you think of the traditional AI approach of I've got to capture all my images of defects, I've got to label the data. From a user perspective, they're thinking, well, that's creating way too much work for me. That's extra work over my day-to-day job. So how do we take that process and incorporate it to an actual task that they do? So we looked at how they inspect components. It's a manual process. They're using cameras, microscopes to look at the components in there. So we developed this tool that provides computer vision-based comparison. So that's based on traditional machine vision techniques. And we actually highlight potential areas of defects for the user. So in that way, it's already helping the user perform their job better, because in the past, they would just look at a board and look for components and take 5-10 minutes looking for errors on the board. We provide a tool that actually highlights, here's the potential areas that are wrong with that board. So that provides an immediate benefit to the user. And how did we incorporate that data workflow and the AI process in there? Is that as I'm going through the differences, the user has that ability to say, well, I accept this difference, I reject that difference. But what we're actually doing in the background is they're actually labeling the data for us, but we're actually not telling them to label the data. We're actually telling them, tell me if this is a defect or not. So we've already sped up their current manual inspection process, but we're building that data set at the same time. So the outcome is the same, but the process of getting to that outcome is vastly different in this case, because we've built something that actually thinks about the user in mind and how we incorporate into their day-to-day workflow. So in this case, the AI initially becomes a decision support tool, not something that replaces a human. And it's very similar to that debate of autonomous self-driving versus driver assistance.
Start the video.
Yeah, we're good.
Go to the next slide.
Yeah, it's perfect. So this is just that process, right? So this is a manual inspection of a board. It highlights the areas of where we think those defects are. And then the user just clicks yes or no. Is this a defect, right? Again, you don't have to go through that labeling process, but we're actually doing that labeling process in the background. And then as we say, yes, this is a defect, no, it's not, you're building that data set. The AI can happen. It's digital. It's a digital process now, so they don't have to worry about manual inspection errors. And you've got that added benefit of analytics in terms of how many defects are going through in your factory. Similar use case, so different industry, mixing AI with vodka. So back to having something fun after lunch. It's always fun to talk about vodka. We have a local distillery in Ottawa named the Dairy Distillery. They produce a vodka. It's an interesting product. It's actually made from milk byproduct, and they turn that into alcohol. Kind of sounds a bit weird, but actually tastes pretty good. What's important with them is brands. So it's positioned as a premium product. So they want to make sure that the product, the look of the product reflects that premium brand out there in the market. And they also did manual inspections in terms of how to inspect the product. And what they saw here, and the challenge that we were having with them that we're trying to solve, is those two labels have to be perfectly aligned. And they have a human checking every single bottle, but then it's very subjective. So this is where AI excels in terms of taking something that is subjective from a human and making it a more objective, repeatable approach that, rather than kind of someone guessing, is this right or wrong, the computer can help. So we implemented the system where, again, you're looking at it, how do I put it into the workflow of the user? We're not asking them to label data for training. We're asking them, well, use the system, and then we can start capturing some data around how those labels are aligned. They use it for spot checking that final inspection. So the benefit, again, is you're helping an existing manual process, and they see that time savings, and that's how you get that buy-in in terms of AI can come after. Same approach, they do a pass or fail. We use computer vision to help them make that decision on pass and fail. But in the background, we're capturing that data in terms of training, being able to train a model of what's good and bad moving forward. So really the highlights of today's session and the recommendations is really around think outside of that traditional process, right? When you're developing those technologies, you also have to keep that user consideration and the human consideration in mind in terms of this may be that workflow that we're all used to in terms of you've got to label the data, you've got to train the model, then you get to your AI automation. Break that down into a roadmap in terms of the success is really following the current user workflow of the problem that you're trying to solve. How the tools will be seen by the user in terms of how that's going to enhance their day-to-day activities versus an extra burden. And really think digitization before automation. And then you can plan out that roadmap from level 1, level 2, level 3 to level 4. I'll finish off with some information about Clara. We were founded in 2000, so we're 20 years old. We are a leader in global machine vision standards. We provide hardware and software in different industries. And of course, our new digitization for manufacturing solutions where we incorporate that AI. And hopefully this was a good lesson for everyone and something to lead into some of the greater discussions this afternoon. Thank you.
Tanum, thank you very much for the presentation. Do we have questions in the audience? Yes, please.
Did you measure like how much of an improvement there was between just humans doing it and then humans plus AI? And also, along with that, how do customers perceive trust in the overall system they get and all those things?
Yep. So back to human assistance versus full automation, right? So the first step, I'll answer the second question first in terms of how do you build trust with the user. So as long as the user sees that they control that decision, they're clicking the pass and fail. So the ultimate decision is still with them. The system is just helping them pinpoint areas to look after. That's how you build the trust over time. So by saying that AI is not taking over control of your decision, because as humans, people don't like it when control is taken away from them. So the positioning around here's a tool that helps you make that decision and you still have control over that full process. Then as you train the model and as we incorporate the AI, they see what the actual results coming from AI, what they actually get. So that's how you build that trust in terms of, yeah, the AI actually seems to match what I would say in terms of that decision, but it varies between customers, right? Some may want always to have that full control, that final say on the pass versus fail. And some may say, hey, I've built enough trust and I trust that AI model enough that I'm comfortable with having this fully automated. In terms of the savings for customers, so I'll give you an example. One customer in the electronic space that we work with, so their manual process, they had a manual process where they're doing the quality inspection of components that are coming in. So they build electronic boards. They're a contract manufacturer for PCBs and they do that assembly. So they receive lots of these different parts. And people don't realize, like when you get the parts, you have to check does the part match? Does the quantity match? Are they in good quality? And that's a very tedious task for a human to do, but it is a human that does it for the most part because it hasn't gotten to that stage of automation. So they take this batch of components from their suppliers and they spend 15 minutes, 50, just looking through, checking off these forms, making sure it's the right count, it's the right component, that there aren't any defects. And we took this approach and we digitized their incoming QC process, their quality control process. Using AI, that dropped it down to 5 minutes. So there's still human intervention in terms of, I have these checks that I need to do, but now that AI is helping me with some of these decisions, I'm really shortening those cycles. So there's a key benefit there. And there's also a cost benefit because what's the cost of a quality issue? Something that gets manufactured with a defect in there, that's easily $10,000, $100,000, $1 million in terms of cost.
Okay, we have another question at our deck.
Thank you, great talks. I'm assuming this is real-time application and probably you're on the edge, Jackson or something. Regarding the deployment and also some of the models that you often when you how do you manage that problem? Because if it's just one deployment, that's fine, but
yeah,
if it's
maintenance and you have to put it off, and then that is a system or another procedure.
Yeah.
Yeah. Well,
Good question. So we do actually support Jetson devices on the edge. And the deployment approach is, again, you don't want to start deploying this on the factory with a bunch of Python scripts, because that's something that is not maintainable on the factory floor. So what we did is we built a whole platform. It's a low-code platform, which has some built-in tools for AI training. So if people want to improve the models over time, it's easy enough for the factory IT people to go in and retrain the models. But the low code aspect allows us to abstract the models and the business logic. So you think of a lot of these low code tools that are available today, there isn't something that's specific to AI for manufacturing. This is what we developed with our platform in terms of we have these Lego blocks in an interface, and then you can call different AI models. You can retrain those AI models and glue that together to create your business logic. And we deploy as applications in manufacturing and not scripts.
So you're not using NVIDIA microservices in this using that off-the-shelf really.
We're not using those because when you think of technologies like that, they're still not final applications ready for manufacturing. And that's where there's a big gap in terms of it's a deployment tool, but then you still need the app level, right? We're not trying to build better AI models with our platform. We're trying to build apps for manufacturers where they can leverage and use AI.
Do we have more questions? Yes, of course. Go ahead.
Is responsibility something that you've already considered? What does the customer say when you say, okay, when the AI does fail, who's going to be responsible for that?
Yeah, so that's a very good question. So again, starting with the human assisted approach, right? That's again building that trust in terms of they know that the model will work. In terms of responsibility, once they learn in terms of what are the limitations of AI, what they'll do typically is kind of provide different levels of protection. So they may say, I'm going to use AI for these types of defects specifically, and still implement a system where they're doing like spot checks afterwards so that you have multiple barriers. And that's something that they do already today, because manual inspection that happens on the shop floor, they have multiple checkpoints that they do because you want to be able to catch errors in different parts. Just like a DevOps process, right? When you're building something, you want to have tests at different parts along the way. So the recommendation there would be just continue with those spot checks so that if there are issues with the AI and it's not perfect, right? That you have some other spot checks that can help catch errors downstream.
But what about when you get to later stages of automation? It's complete automation.
So they will do a lot of testing before they deploy in production. So that level of trust has to be there. So they have to be confident that the AI model is performing to find the defects that they're looking for.
Okay, more questions? Yes, please, of course.
Thanks for your responses. A challenge I've seen is that oftentimes manual inspectors, like if they're inspecting this pen, they like do this.
Yeah.
They move it around, but like we try to automate that. It's very difficult. So it's still we need to optimize not only our anomaly detection, but also some type of mechanism for capturing the data. I wonder if you've seen that.
Yep.
Other people might solve that.
Yeah, so that's part of like thinking from a overall system perspective. So AI, obviously we're dealing with the models and kind of that processing, but you do also have to think about that data acquisition and image acquisition. So an example, we're working with a company who's doing spark plugs, and they have to look at the 360 of the spark plug. So the mechanical handling of those parts is part of that system approach. Is that from a usability perspective, you definitely don't want a user taking a spark plug and then rotating that under the camera. So we worked with them in terms of the automation of how do we build in some sort of robotics where it's actually spinning that around. And this is not In industrial automation, there is a lot of these line scan cameras. So the line scan cameras allow you to take that 360 image, or if you're inspecting things like on the press, right, inline inspection, that's where you have the advantage with inline line scan type of cameras that can help solve those applications. So again, people think it's just an AI problem, but then when you actually talk to the user, there's a lot of different variables that come in to help and build the actual solution that's usable in the production environment. Yeah, quick question, please.
Yeah, so I have another question. So there are some, some ICs being manufactured, outside United States and used in some, military applications, I guess, and where basically you need some kind of non-destructive imaging, to inspect those circuits, because there are multiple layers.
Yeah.
And all what you are providing basically some kind of design of that circuit that's here on the input. So do you guys work on such problems, or you have customers in that space where literally we cannot label the data, the only images that design document basically of that circuit, and even the human cannot actually, take a look and say this is effective or not effective. But it's not the first layer of the IC. Not actually see it's multi-layer circuit.
Yeah.
And it's very expensive. We don't damage it. So in the context of this workshop where we have infrared and X-ray and other modalities, I wonder if you guys have some customers and whether you have some success stories to share with us.
Yeah, so you're exactly right. Like visible cameras, they're people naturally think because that's what humans see, that's the first choice in terms of the sensors. But more and more, there are more complex applications. So one of them being you want to see something that you can't see. So give you a few examples. You could use X-ray sensors for looking at the inside. There's hyperspectral imaging that is also becoming more popular as well. Again, you can't see what you can't see, right? And hyperspectral provides the ability for applications like food, where they actually want to look at the quality of the produce that's being in there. So at a generic level, the AI models can still be built based on the different sensor types, but inspection is beyond just the visible cameras. You've got X-ray, hyperspectral, and then thermal imaging. An example is looking at heat seals. So when you look at food packaging industry, they need to make sure food and pharma, right? When you're buying that bottle of medicine, that heat seal is properly sealed so that there hasn't been any tampering that has happened on these safety critical devices and products out there in the market. So definitely a very strong use case for sensors beyond just the ones that are the traditional 2D vision sensors.
So do you guys plan on releasing a database, certain, certain challenge next year in this workshop?
We always have use cases that we build. The challenge with manufacturing is that every product is different and every manufacturer works differently. So some of the things that we are seeing out there, right? Public data sets are hard to work with for manufacturers. So it does have to be proprietary custom data sets for manufacturing, but we are seeing commonalities in the types of problems that people are trying to solve, like exactly like using thermal imaging to look at heat seals. That is a common problem that is existing out there, but because every product that is being manufactured with those heat seals is completely different, this is where we're looking at something that it allows users to train to create the models themselves more easily. And there's always that reluctance to share images out there because manufacturers, that is their secret sauce, right? They don't want to share images of their product.
Okay, Jonathan, thank you very much.
Thank you
for the presentation. Thank you very much for the discussion. So this concludes this keynote. And we will now start with our session 3, which is on other modalities. We already had sessions on remote sensing, a session on thermal image, thermal infrared data processing. And now we would like to continue with session 3, other modalities. And I think the author of the first presentation of this session has not shared the slides yet. Is this correct?
And so I think the first presentation is rhythm voice.
Yeah, no, it's.
Oh, it's not. Are you on it? Mount. Yeah, it's the second one. So you are next after her.
Yeah.
No problem. Yep. Okay. Mhm.
You slide there.
The slides are already on the computer. Yeah. Yep. This one, right?
Yeah.
Yeah. No.
It's PowerPoint, right?
Yeah, it's PowerPoint.
Okay. So I will also activate the. Where's the laser pointer? Is this a different node? Did I do it? Did I do a mistake? Maybe I did a mistake here. No. It looks different from the presentation before. That's why I got confused. Is it broken? Okay. How do I activate the laser pointer here? Because usually I would be thinking that something is here, but it doesn't look like it. So in that case, we just use the mouse if it's okay for you. The mouse will be visible in the remote setting as well, so that should be good. Okay, great. So thank you very much. We are glad to welcome Pamela Senjalia with us. Yeah, I just leave the floor to you. We're looking forward to your presentation.
Thank you so much. Hello, everyone. I'm Pamela Senjalia from University of Victoria, and I'll be here talking about an exciting research that basically combines two domains: underwater environment monitoring and computer vision. Our paper is detecting underwater discrete scatterers and echograms with deep learning-based semantic segmentation. So it's quite different from what we have been looking at so far. Just a little bit of context. So underwater acoustic surveys basically provide high-resolution spatiotemporal data, which is then used by acousticians, environmentalists, and marine biologists to understand any physical or biological phenomena underwater. We can gather this data from a device called acoustic zooplankton fish profiler, or echo sounder, which basically emits acoustic multi-frequency signals, and these are upward looking. So these echoes then reflect back after hitting to any activity and is gathered as some data called backscatter data. So to make sense and visualize this data, what we do is we create 2D images out of that, where the height of the image is basically the depth of the water column, and the width of the image is a time frame for us. In our case, it's 1 hour. The amplitude of the reflected echoes are basically intensity of the pixel. So the primary goal of this paper is to focus upon deep learning methods to understand discrete scatterers present. So it's about understanding their abundance. We are not counting these scatterers. So what are these scatterers? These scatterers refer to these tiny individual organism as opposed to aggregations like school of herring, say, for example, any bubble cloud over here or air water interface. And the blue part is completely water. We can also see there are so much noise bands in all the echograms. So these, the images that we created out of backscatter data is called echogram. And for every hour, we have different frequency. And all the three frequencies shows same or different scatterers. Some reflects a particular frequency better than the other. So in our case, these tiny looking objects all over in the echograms are jellyfishes. We faced a lot of challenges due to the small size of the scatterers and density and distribution, because they are all over the image. And because of the contours of other schools of fishes, they sometimes get lost in those schools. And also because of these scatterers tend to exhibit almost same backscatter strength as of the noise. And that's why we cannot see a lot of scatterers in the noise band. So our contribution is divided into two parts. The first one is like we explore semantic segmentation methods for pixel level detection of discrete scatterers in noisy echograms and present a comparison between state-of-the-art real architectures and outlining the strength and weakness of those architecture in regards to our data. Another important thing is because this is a multi-frequency data, we had to take all three frequencies as important as each other. So we also understood the difference between early versus late fusion, which I can explain later on. So the Oki-Sawyer channel underwater discrete scatterer is a data set which is just comprised of 125 1-hour multi-frequency echograms, which makes it a really tiny, really small data set. So in order to visualize the echograms, the backscattering strength, which typically ranges from minus 125 decibels to 0 decibels, are converted into RGB integer, which is then mapped upon a color map. And for us, that's Perula. We did not use a color map like JET because this is not sensitive to color blindness, so Perula is better that way. And another thing is that it does not accentuate all the pixels which are in noise. So it just settles it down. And we did semi-automatic annotation for this. So to make sense of what is early fusion versus the late fusion, we can see the figure A, which is basically, we take the single frequency images and we simply feed that those images into the architectures, which are unit attention unit at Deep Lab V3 in our case. And then we fuse the results of those and we take one output echogram. The other method is we do the fusion initially in the backscattering strength, and we then create one final fused echogram, and we feed those echograms to the network to get the final result. Just to make note of this, the number of images fed into the network changes drastically. The first one has three times more than the second one. So we use three networks unit, which is built upon FCNs and is it's pretty famous for its encoder, decoder, and bottleneck architecture. Attention unit, which basically adds up attention mechanism to focus on some specific elements of interest. Deep Lab V3, which is again encoder, decoder architecture with ASPP module. And YOLO V7, which is quite different from the other ones because it uses bounding boxes. And in our case, because those scatterers are really, really tiny, this does not perform really well. So just to show some quantitative analysis, we can simply say that, late fusion is clearly the winner, and Deep Lab V3 tends to perform good with precision and IOU matrices, whereas attention unit performs better with recall. Now, this takes us back to the first question. We are not looking at the count of these scatterers. Instead, we are looking at the presence of those, abundance of those. And that's why we pay much attention to recall. But we also did some qualitative analysis where we can see the annotation, we can see the early fusion and late fusion results. And the annotations clearly are not that good because it was semi-automatically done and it was like near to impossible to do it manually. And we can see the late fusion results are really, really nice. Another example is like in a place where there are some fish schools over here, attention unit, especially with late fusion, tends to perform really well as it's not getting confused with the contours of those school of fishes. And it's also detecting fishes in the band, whereas it doesn't even exist in the annotation. So this takes us to conclusion that, interestingly, the networks appear to qualitatively outperform the annotations on several occasions. Like the network are able to detect some scatterers even in the noisy regions, and it's not detecting scatterers where they were falsely annotated, like the school of fish. So this problem that we are trying to solve here is an amazing example of the class of problems where perfect ground truth, which is expressed via annotations in all computer vision cases, cannot be reached due to multiple reasons. And that's all for the presentation. Thank you.
Thank you very much, Femina. Do we have a quick question from the audience? Seems not to be the case. So since we are already a little bit behind schedule, I kindly ask the next speaker to the floor. Thank you very much again, Femina.
Thank you.
And you will get your USB stick back. And Ahmed, you will be next. Okay.
The program with the present remote.
We still have it, yes. So you have to do the presentation in the slide mode, in the regular slide mode. Oh, you will use your laptop to get the idea. Yes, sure.
Thank you.
Okay. We'll start your presentation. I will also activate the pointer for you. So the slides use the cursors, and you can use the pointer if you like. So thank you, Ahmed, for being here. So the floor is yours.
Thank you. Hello, everyone. My name is Ahmed Zgarin. I am a PhD student at Concordia University, and my research focuses on machine learning and artificial intelligence. Today, I am presenting our last research paper entitled Mount Count, a detection-based approach for automatic counting of planting microsites on UAV images. Let me start by giving you some background of our work. Mechanical site preparation by mounding is a forestry technique to construct elevated planting spots, as you can see in the image. This image was taken from the ground, and the red circle represents a single mound. During planting operation, one of the main planning steps is to estimate the number of mechanically created mounds in each planting block. This is important in the inventory planification because inaccurate count causes important delays and huge loss of money. To estimate the number of mounds in each prepared block, forestry managers have used two methods. First method was a manual counting method, which where several more workers move through the plantation block and visually count the number of mounds in a specific portion, then extrapolate to neighboring regions. The second method rely on visual interpretation of UAV images through human photo interpretation. This method involves visual mount identification by human operators on UAV images. Both methods have limitations such as they are prone to human errors during mount identification, time-consuming, and assume constant density distribution across the block, which is often invalid. The objective of our works is to develop a novel method based on machine learning algorithms to automate the mount counting process on planting block. We aim by using cutting-edge machine learning algorithms to reduce counting errors while increasing precision and eliminate the time-consuming and expensive field survey. Now we move to introduce our proposed method, and let me start by motivations. First, I give idea about the challenges of mount detection tasks. As you can see, we show four different patches, UAV patches from different blocks. Patch A includes a similarity in appearance with background. Patch B shows variation in the shape between mounts. However, variability in appearance between planted blocks is easily remarkable in these patches. Secondly, the need for large amounts of labeled training data is a significant challenge under our application constraints. Finally, deep learning models are known to struggle with generalizing to new environments. This means that a deep learning model trained to count mounts in a given type of block or environmental condition may not be accurate when applied to different contexts. Now let's take an overview of our proposed method. We designed a system based on two complementary prediction models. First, we train an object detector using manually annotated images to detect visible mounts in a local patch. After estimating the preliminary number of mounts by detection, a global correction model is applied using global features extracted from each block. You can see the entire system design in the current slide. Starting from the left, the green box, the first stage was to collect overlapped images and then orthomodelic reconstruction. We use a subset in the top level. We have the training state. We use the subset of the data set to train both models. And in the blue box, we have once the system is trained, it can be used in a real world scenario by processing a new orthomosaic. Turning our attention now to the mount detection in local patches. In our approach, we use a supervised deep learning object detector to perform mount detection in a single block. The reconstructed orthomosaic was divided into small patches to feed the model input size. Given the requirement of a large annotated dataset for training deep neural networks, transfer learning is implemented utilizing pre-trained weights. In addition, we use data augmentation to overcome the lack of annotated data. During training phase, we generate new images by applying modifications to bounding boxes, including scale change, and translation. An example of detection results of our trained model applied to a sample patch is shown in this slide, where red boxes are detected mounts. In this slide, I will focus on the second module of our method, the final count estimation using global features. As I said in the beginning, the final estimated number of mounts should be equal to the planted seedlings in a given block. It is important to note that the number of visible mounts is generally different from the final number of seedlings to be planted due to several factors. We define a global count estimator that maps between the global information of the planting block and the final number of planted seedlings on the considered block. We train the model using global features extracted from planted blocks, such as the number of detected mounts, block area, density, and the ground truth, which is equal to the number of planted seedlings. Here, two sample patches that show the difference between visible mounts and detections. Orange boxes are partially destroyed mounts by water flow. Yellow boxes are invisible mounts that are occluded due to debris. Blue boxes are detected mounts. However, red boxes are missed detection of visible mounts. We could observe that totally and partially occluded mounts hadn't been detected in the detection example, and this increases error rate of the model. Now we move to present our results in our constructed dataset. Totally, we have 18 blocks. We used 5 blocks for training, validation, and the remaining 13 blocks to test our model. Table 1 shows a comparison of our model with the state-of-the-art methods, including detection-based models, yellow and faster RCNN, and density-based count methods, namely MCCNN and CSRNet. Results include final count and relative precisions. First, our proposed method outperforms visual detection methods on 12 over 13 test blocks, which confirms that our global estimation module improves the detection count performance. We observe that the proposed global estimation module improves the final count by 70% in block 12 to achieve a 92% precision. Secondly, the comparison with the density estimation-based methods shows that our framework achieved the best overall performance. Now let's move to table 2, which shows the overall performance of various counting methods on the test set. Here we show the mean relative precision, the mean absolute error, and the mean squared error results. Notably, our approach ranked first in MRP with 88%. On the other hand, our method outperformed the others in terms of MAE and MSE, achieving the best results of 608 and 703 respectively. Now we will introduce results of the human level performance experiment that we conducted to evaluate the human level in mount identification task. Our protocol includes to ask two trained participants to identify and annotate mounts on two different blocks. Results of this experiment is shown in the table on the top. We can see that the human error varied between blocks A and B with rates of 3.9 and 11.9 respectively. One possible explanation of this performance degradation between blocks is the challenging environmental factors that were present during visual recognition and may have affected the participants' ability to accurately identify mounts in images. Additionally, there may have been variation in the block property, contributing to the differences in performance. A deep analysis of possible explanation, we observe that visual recognition in patches with irregular patterns is more accurate than patches within an irregular pattern. And this irregularity led to misannotated mounts. The main reason for the irregularity are occlusion, water overslopes, and mechanical preparation difficulties.
1 minute left.
Yeah, it's my last. All right. In conclusion, let me sum up my main points. First, we propose a novel method for mount detection and counting on UAV images. Our method estimates the number of planting microsites through a combination of local object detection and global count estimation. Also, we conducted extensive experiments, including comparison with state-of-the-art methods and evaluation of human-level performance in recognizing mounts. Thank you for your attention.
Thank you very much for the presentation. Do we have questions, the audience? Seems not to be the case, so yes. Thank you very much again, and we continue with the next presentation.
So there's one more presentation left in this session. I want to ask Brian, I think. Yes? All right. So we received your slides. We will start presentation now. We have first to go to the slide mode, not to the presentation mode. Do you want to have a laser pointer?
No, I'm all right.
Yep. Okay. You sure? Okay.
No, I'm not sure now. Can I have this? Change my mind
Just double checking. No problem. Here is the laser pointer.
Lovely,
So
thank
Brian, thank you for being here with us, and the floor is yours.
All right, hi everybody. So I'm Brian. So today I'm going to present seeing through the data a statistical evaluation of prohibited item detection benchmark dataset for X-ray security screening. So basically, in this presentation, I'm going to show. Well, in Durham University, we actually have in our research group we have several publications related to threat item detection in X-ray images. So we decided to go through a evaluation of actually how are the distribution of the color and the objects in X-ray images, and how are they different from an actual normal data set such as COCO. So the actual motivation of this work is that there are coming some standards that they are gonna start actually making compulsory to have some kind of like AI aided system into object detection. So this ECAC standard actually is coming probably I think it's next year, and it's gonna make compulsory to have some kind of like AI aided model or something like that. So we want to move towards this kind of like AI implemented methods. However, there's only a limited number of X-ray benchmarks because they are really difficult to actually to get, like for security reasons, because it's all the companies tend to keep the secret on this kind of stuff. Since this is very difficult to get, we actually rely on normal, let's gonna call it normal, or actually in the visible spectrum data sets such as COCO, ImageNet, or this kind of stuff. So we rely on those data sets, we pre-train in those data sets, but we don't know if they actually are learning some biases that are not actually well implemented, or they're not valid for X-ray images, such as that. So in this work, as I was saying, we are going to present a statistical review of these benchmark data sets. And also we are going to see how are different colors and how are like the objects affected, and also how like standard detectors perform when compared with COCO dataset. And we are trying to see if the actual bias or there's a bias between kind of like the objects that are not recognized or something like that. So we are going to use 3 standard benchmark datasets. One of them is OP-X-ray, and the other is X-ray 10 and PID ray. So I think you can see from these images that even though those three are actually X-ray images that are from bags or for people luggage, the three of them are actually quite different. They have different colors, they have different kind of objects, they have different classes. So we want to see actually what's kind of like the difference, probably with another normal data set such as COCO. So let's gonna look first at the class imbalance. So let's gonna look at the OP-X-ray data set. We have different like objects, folding knife, multi-tool, scissor. It kind of looks balanced. It does look like probably the straight knife is the less present class, but it looks all right. But there are classes like such as 6-ray-10, for example, in that data set. We have a way class imbalance between pliers, scissors, wrench, and this is a problem for any object detector, this kind of classes. But in the PID array, we have well, it's very like there are different kind of classes that are actually very different across like the distribution of this. And also you can see that in the PID array, we also have 3 test partitions. One of them is easy, the ones that are actually, let's gonna say, very visible, they're there. But they also have test hard that they are actually quite confusing even for security personnel, and hidden that are actually the ones that are trying, they were like purposely putting like hidden between other objects. So let's gonna look at a color analysis now. So you can see here how is the COCO data set. When we all know the COCO data set is for people, it's for natural images. But when we look at the color histograms between the X-ray images and the COCO data set, we can see, as expected probably, that there is a huge bias towards like high contrast and RGB in the 255 and this kind of stuff. If we look at the HSV histograms, we can also see, probably as well as expected, that the X-ray images are mostly between 2 or 3 kind of colors, apart from white, that are red, orange, blue, and this kind of stuff. So these kind of colors are different for different kind of like materials, like organic materials, metallic materials, and so on. And apart from these color images, we also do an object instant analysis. We want to see how is the distribution of the objects. So we are going to look at area of the bounding box, the aspect ratio, and where is the center located in the image. So if we look at the distribution, and in the right, you can see the COCO data set, we can see some clear like trends going on here. So the objects in area, in the size of the objects of the X-ray data set, they're basically across 1,000 pixels, 10,000 pixels, something like that, and they are not that they have peaks over these kind of values. But in the COCO data set, we have a tendency to go for smaller objects. So this could be a problem, as we are going to see later, that object detectors actually tend to recognize small objects more, and probably there's a bias over there. They are actually trying to detect smaller objects that they are not in the X-ray images data set or in the security images. Also about the location, in the COCO data set, we have a broader area. Basically, the objects appear everywhere in the image. But for the X-ray data set, they don't appear everywhere. We have a prior that they appear probably where an object can actually go. They can be, I don't know, at the bottom because of gravity, or they can actually be in the center because they are where these are the areas where people actually try to hide stuff. For the aspect ratio, we actually didn't observe any kind of like particular difference. All of them are biased, or not biased, but they are distributed around a 1:1 aspect ratio. Also, we test 6 different like paradigm detectors: Cascade RCNN, FSAF, the formal detector transformer. We try to see if there's a bias towards these kind of detectors. First of all, you can see here, swing transformer is the best one for these data sets in almost all of the benchmarks. This is not a surprise. I mean, swing transformer is really nice with faster CNN benchmark. Framework. It's kind of like really impressive, and even in COCO dataset, and it's also confirmed in these benchmark datasets. Also, the formal detector transformer is quite nice, and we all know that. Yeah. And if we look at the detection bias, so let's gonna see in these kind of like red boxes, you can see the false positives, and in the gray, we can see the false negatives. The false negatives are the ones that we miss, and the false positives are the ones that we we say, okay, there's something here, but there wasn't something there. So false positives actually is quite important. We try to decrease that because probably a 1% of false positive, it doesn't sound that bad. But imagine that probably an X-ray scanner or in an airport, we are scanning millions of bags probably a day or a week. And we have a 1%, that's thousands of images, and we don't want to stop for, I don't know, 100 images, 100,000 images every week or something like that. So we observe that there is in fact a trend here to observe that the lower or the small objects are a problem for X-ray images. And this is related, as I was saying earlier in the presentation, that in COCO dataset, we have really, really small objects that are actually not the case in the X-ray. So we have, what's the takeaway with all of this? We have to design probably detectors that actually don't focus a lot in detecting small objects, because all the detectors are trying to go and check all the metrics with the COCO dataset, but that might not be the case in certain applications. We also observe bias in location. We didn't observe a lot of trends, neither for aspect ratio, but I think the most important case is the size of the actual objects. Finally, as a conclusion, we observed 3 different X-ray security datasets, OP-X-ray, 6-ray, PIG-ray, and the objects in these datasets show a different distribution, even among them, but they are also very different from a COCO dataset. So I think that should be the takeaway. If you are gonna that's the whole idea of this event workshop. If you are going to design for a different, I don't know, class modalities like probably infrared or X-ray or whatever, we have to make sure that we are actually using detectors that are suitable for that, all right? Other remark, vision transformers, base detectors are the most reliable ones. And also one-stage anchor-free detectors, which I think was CenterNet, was the worst performance in detection. Probably this is because CenterNet is focusing on the key points or the triplet of key points of an object, but probably those 3 key points are very difficult in X-ray dataset because of the actual overlapping nature of the X-ray dataset. Finally, a bias towards smaller mismatches and undetected distance is also observed. Thank you very much. I'm happy to take any questions.
Well, thank you very much. Do we have questions? Yes, please.
Just for curiosity, you were speaking about color in X-ray datasets. This color is a standard from the different machines, or there are different type of color, and the color is related with the material. Can you please tell us?
Yeah, sure. Yeah. Well, actually, that's a manufacturer kind of like secret or like, idea. But usually they decide the idea of the formation of X-ray images in this that I forgot to mention, some of them are dual energy, like you have 2 different kind of energies to detect the material. So you get an effective set, which is the atomic number. And depending on the atomic number, metals tend to have like higher atomic numbers. So something like that. So I think, if I'm not wrong, in general, orange is organic, blue is a metal, and green, I don't remember, sorry, but it's something like that. Yeah.
Hey, any more questions? If not, then please thank Brian again.
Thank you.
And this completes the session on other modalities. So now we have one more session to go before we have the afternoon coffee break. The next session will be on the results of the 3 challenges that we run during the workshop this year. I will, before I hand over to Rafael, I will open the slides that will give us a presentation of the results of the thermal infrared super resolution challenge. So this should be the slides, I guess.
Yeah, I was wondering.
Does it? Let's see the slides. It's okay. Okay. I'm not sure if this is working correctly. I have a feeling that it's the sharing again has an issue. Yeah, we don't see the update in the remote session. Yeah, this is a recurring issue today. Yeah. Okay, we will restart Zoom. Can you help us, Engel? This looks good. And now we are hopefully able to share the screen. That's really works. Yes.
Yes.
Yeah. Yes, it's okay. So we will close this one. We will start the presentation. We will go to the slide mode. And okay. And something went wrong. No luck. No luck. Okay. Looks okay. Can you please work this time? Yeah, we made it. So, Rafael, the floor is yours. Okay, thank you, Michael.
Hello, everyone. My name is Rafael Rivadeneira. I am one of the organizers of the Thermal Image Super Resolution Challenge. And this is the outline of my presentation, a quick introduction, an overview of the challenge, a summary of the architecture proposed by the winners, and conclusions. And conclusions. Okay, in a fourth year in a row, super resolution challenge of thermal images has been done. This time it has 2 tracks. For track 1, the goal is to generate an X4 and X2 super resolution image from the given low resolution images using the same dataset as previous edition. In this track, 2 evaluations are proposed. In track 2, the object is to generate an X8 super resolution image from a given low resolution image, but this time using high resolution visual spectrum image as a guidance. In this track, a new computation, a new dataset is considered. This dataset has registered stereo images, and this is a new competition. And for this challenge this year, we have over 150 teams registered and participate in the 2 tracks of the challenge. This is an image of the evolution of the metrics across all track 1 challenge since 2020. As you can see, the results of this year are a little bit higher. This somehow shows the interest of the community, of the research community. Here we have a little an illustration of the dataset used in track 1. This dataset was acquired with using 3 different camera resolutions, referred as low, mid, and high images. For track 1, just mid and high resolution is used. This was acquired with an axis and a FLIR camera. As you can appreciate, the images acquired with these cameras are not quite registered due to the misrepresentation of the optical axis of the camera. In evaluation 1 of this track, the objective is to generate a X4 super resolution image. We get the round 2 image, the high resolution image, noised and downsampled with bicubic downsampling. Then 10 downsampled images are shared with all the teams, and their generated super resolution image are compared with the round 2 image. For evaluation 2, no artificial are used to downsample the image because the mid-resolution images acquired with the mid camera is used, and the team have to generate a super resolution image, and it is compared with the corresponding high resolution image. Here we have the average results of the top teams in the track 1. The bold results highlight the best results. As you can see, Estaya and TSR team get the higher results in evaluation 1 in PSNR and structure similarity. Meanwhile, in evaluation 2, AC team reached the best result in both metrics. Track 2, as I mentioned, is a new competition and make use of a new acquired dataset with a registered thermal and visible image of the same SIM. It used a Tau2 camera and a baseline camera. Worth to mention that these both images are registered. And the object of this track is to generate a X2 super resolution image. But the main idea of this track is mainly use the high resolution visible image to help the low resolution thermal image to generate a super resolution thermal image. These are the top results on this track 2. You can see guided super resolution get the highest results in both metrics. Now I will present the summary of the architectures proposed by the WINS in both tracks. For track 1, a STIA team by Dai Bing et al. Get the first place in evaluation 1 in metric PSNR. This team directly used the model structure proposed by Chen et al. As referred as HAT, Hybrid Attention Transformer. HAT network combines channel attention and self-attention schemes to activate more output pixel for the reconstruction. This team initialized the network using ImageNet pre-trained model. They use data augmentation strategies and trained the model for about 60,000 iterations for about 27 hours using a 4NV Tesla V GPUs and 20 cores in GPUs. They are the results in each metric of them. Next, a short video by each winner of the.
Hello everyone. Our team is TSR team from Harbin Institute of Technology. Our team member includes Siwei Zhang, Xianming Lu and Zhenjun Jiang. Here I will present our solution for the thermal image super resolution challenge. The pipeline of our solution consists of 3 steps. First, we upsample the low-resolution images by big interpolation. Then, we feed the upsampled results into the network. Finally, the output of the network is added to the upsampled low-resolution images. The network of our solution is comprised of 3 components, including shallow feature extraction, feature enhancement and high-resolution image reconstruction. To be specific, we first feed the LR image into the shallow feature extraction to extract informative features for the deep layers, and then the extracted features are fed into the feature enhancement to be enhanced. Finally, the enhanced features are fed into the high-resolution image reconstruction to reconstruct high-resolution images. The key component of our feature enhancement is the NavPlex, which is proposed by the reference 1. Specifically, the NavPlex is comprised of layer normalization, standard convolutional layer, depthwise convolutional layer, simple gate, and simplified channel attention. Simplified channel attention directly uses pooling followed by a convolutional layer to generate channel attention, which is computational efficiency and brings global information to the feature map. And simple gate directly divides the feature map into 2 parts in the channel dimension and multiplies them, which can replace the complicated GELU. After that, we introduce the training strategy. To improve performance, the model is first pre-trained using LRHR pairs for scale 2 and then fine-tuned using LRHR pairs for scale 4. The team conducted experiments using the PyTorch framework on 2 NVIDIA 3090 GPUs for 3 days. The batch size and batch size are set to 8 and 32, respectively. The quantitative results show that the TSR team achieved 32.46 PSNR and 0.9292 SSIM, the highest SSIM, on evaluation 1 for track 1. Thank you for your attention.
Okay, thanks for the team. They reached the first place in structure similarity in evaluation 1 in track 1. Then the presentation of the team, IC team, who reached the best result in evaluation 2.
Hello everyone, I'm Chen Yang Wang from Harbin Institute of Technology. Our team is AC team, mainly including Professor Junjun Jiang and Professor Xianbing Liu. We are delighted to have the opportunity to make this presentation. The subject of our presentation is our technical solution for thermal image super resolution challenge. Trick 1, Evaluation 2. For this task, the key problem is that MR and HR are unaligned. One solution is to align HR with MR, then use the aligned HR image as label to train the model. However, HR belongs to high-resolution space, while MR belongs to low-resolution space. They belong to different resolution spaces. Direct alignment between them is inaccurate and challenging. Therefore, we first recover MR to SR, which is in the similar resolution space to the HR, and then align HR with SR. Finally, we use the aligned HR image as the label to train the model. This is our solution. We present our framework in the figure, which draws on the reference 1. To be specific, we first fit the coordinate map of MR, and HR into the model 1, M1, to recover a cos super-resolution result. Then the HR image and the cos super-resolution result are fed into the PWCnet, which is a pre-trained optical flow estimation model. With the estimated optical flow, we can align HR with the cos super-resolution results, generating the aligned high-resolution result. Then we use the warped high-resolution result as ground truth to supervise the final super-resolution model M2. The whole framework is jointly trained with the combination of two pixel-wise loss functions, and M denotes the mask, indicating valid positions of the optical flow. The M is generated by the equation. Finally, we introduce the experimental details. To be specific, we directly use GCMnet as M1, like reference 1, and use an autoencoder as M2. The whole model is trained on two NVIDIA GPUs for 60 epochs. The optimizer is ADAM, and the learning rate is set as 0.0005. Our method achieves the best performance for thermal image super-resolution challenge, track 1 and evaluation 2. Thank you for your attention.
Okay, thank you for the team. Finally, for track 2, guided super-resolution team, is the same team that participated in the track 1?
Hello everyone. We are guided senior team and our team member includes Siwei Zhong, Xianming Lu, Zhengzhen Jiang. Here I will present our solution for the thermal image super resolution challenge track 2. The pipeline of our solution consists of 3 steps. First, we upsample the low resolution images by bicubic interpolation. Then, we feed the upsampled results into the network. Finally, the output of the network is added to the upsampled low-resolution images. Considering that the RGB and thermal images are captured by different imaging pipelines, the team proposes a 2-stream network to enhance the LR thermal image. Specifically, the team first feeds the LR and RGB images into a shallow feature extraction layer to extract shallow features respectively. Then, the extracted features are concatenated and fed into feature fusion layers to fuse multimodal information. The key component of our feature enhancement is the NavBlock, which is proposed by the reference 1. Specifically, simplified channel attention directly uses pooling followed by convolutional layer to generate channel attention, which is computational efficiency and brings global information to the feature map. Here we introduce the training strategy. In the first step, the network is guided by using L1 loss. In the second step, the network, pre-trained in the first step, is fine-tuned by adopting MSE loss. The team conducted experiments using the PyTorch framework on 2 NVIDIA 3090 GPUs for 3 days. The batch size and batch size were set to 8 and 32, respectively. The quantitative results show that the guided SR team achieves 31.04 PSNR and 0.9294 SSIM for track 2. Thank you for your attention.
Okay, thank you for the team. In resume, the winners of this year challenge are for track 1, evaluation 1 on PSNR metric is the STIA team, and instructor similarity is the TSR team. In evaluation 2, in both metric, we have AC team. On track 2, and in the evaluation, both metrics guided super SR team get the best results. Congratulations to the winners. They will receive their certification in the following days. And to conclude, in this challenge, 2 tracks are proposed. Track 1 with 2 evaluation. Track 2 is a new competition that made use of a new acquired cross-spectral data set for guided approach. Even the results are higher in the track 1. Performance are limited, reaching in track 1. While guided approaches enhance results in track 2 are large super resolution scale like A4. Challenging dataset will be used as benchmark for future edition, advanced thermal image resolution, and challenge further collaboration, ideas exchange, and significant advances in the field. Thanks for your attention.
Thank you, Rafael, for the presentation. Do we have any questions or comments? Actually, maybe do you want to give us a little outlook on what will await for us next year in the challenge? Do we have a 5th challenge? Will it be like an extension or something?
For next year, we want to use the track 2, but this time making a super resolution on 8x16 using the guidance of the visual spectrum.
Cool.
Yes.
Looking forward to that. Yes, one more question.
So the guided image is pixel registered with software.
Yes.
But we have created a track where they are not precisely registered. So in reality, right, most of the time they are not necessarily precisely registered. That would be more interesting.
Okay.
Right. So it's like your thermal versus EO kind of. I mean, they have imageries. Maybe use SIFT to register, but not precise. That would be more realistic, more challenging.
Okay. Thanks for the contribution.
Thank you for the comment. Yes.
Yeah.
Okay. So, Rafael, thank you again.
Thank you.
And we will continue with the presentations for the 2 remaining challenges that we have. We have Oliver Nina with us today. Hey, Oliver, nice to see you again. The presentation will be done by Spencer Lowe, who was like the person who really in depth conducted the challenge. As far as I understood, Oliver is not with us today, unfortunately. So, but he prepared a video to show us and to present to us what has been done in these 2 challenges. The MAVOC is the first one, right? Yeah. Okay, so we'll get this video started, and he will present to us the results of the how's it called?
Multimodal aerial view object classification.
Awesome, thank you very much, yeah. Of the challenge. Okay, so we're gonna get started, and here we go.
I'm Spencer Lowe, and I'll be presenting on the Multimodal Aerial View Object Classification Challenge results held with PBVS in 2023. For the overview, the primary goal of this challenge is to inspire research into methods for building recognition models that use both SAR and EO. The 2023 challenge introduces and uses the new and improved Unicorn V2 dataset, which includes improved alignment and more examples. The challenge focuses on 2 main tasks. The first one is SAR classification, and the second one is a combined SAR and EO classification. This year we saw all top teams outperform the 2022 submissions, with the SAR class outperforming the top team from last year by 173%, and the SAR and EO combined task, we saw the top team outperforming the 2022 top team by 175%. We also introduce out-of-distribution scoring, and we do this using the AUROC. And we saw a top AUROC score of 0.85 for the SAR-only task, and the for the SAR and EO test, we saw 0.97 maximum AUROC. And this is a large improvement over our baselines, which are seen here. So this challenge is very similar to automatic target recognition in that we're trying to accurately recognize, identify, classify, and target signatures in a remotely sensed image. And then we have out of distribution detection goals, which is to produce calibrated networks. And this means the output logics of the network correspond with the network's confidence in a predicted label. We do look at the SAR modality, and there's multiple benefits in looking at these remote sensing modalities. Some of the examples are, like for SAR, it's self-illuminated and can penetrate clouds. Other sensors can measure temperature. Others are specially tuned at finding man-made objects, and even some can infer wind speed. The majority of remote sensing systems are single modality, though. Our challenge is divided into two main tasks, and we call them tracks. There's track 1, which is SAR only, and so this is, in this task, classifiers have EO and SAR data at train time, but at test time or inference time, only SAR data is available. And this is done to encourage the development of accurate SAR classifiers that can combine the information in EO images as well. And then for our track 2, we have SAR and EO, which is classifiers have EO and SAR data available at both training and testing time. And this is again to encourage development of accurate combined SAR and EO classifiers. And then our performance is mainly measured by accuracy and AUROC on a sequestered test set. So moving on to the actual challenge. The challenge was held jointly with the Perception Beyond the Visible Spectrum, or PBVS workshop. And this challenge again was designed to facilitate innovative approaches in multimodal classifiers. The SAR imagery that we used from the Unicorn dataset presented some interesting challenges in that it's like a coherent signal with SAR shadows and a tilted perspective. And then all the submissions were evaluated on a weighted average of the top 1% accuracy and AUROC. And the formula we used was it was weighted 75% towards accuracy and 25% towards AUROC. We chose to use the AUROC, or area under the receiving operating characteristic, because the metric is used to evaluate performance and calibration of a model. As a quick background, the score of 1 with an AUROC of 1 corresponds to a perfect model with perfect separability. Any score of 0.5 corresponds to a model with no separability, and a score of 0 corresponds to a perfectly reciprocal model. Our Mavic challenge uses a multi-class AUROC to assign that score. The dataset used is based on Unicorn version 2. It is a public SAR and EO aligned dataset. The second version is updated to contain many more examples than the first version and has improved alignment. The images are rectified and aligned via in-house homography algorithms, and the competition dataset consists of small chips. These chips are small 32 or 55 pixel by square images that contain one of the 10 object classes. And the validation and test set are uniformly distributed across all classes and contain out of distribution samples. This slide here shows examples of the classes from the dataset. The top shows the EO and the bottom shows the corresponding SAR. This table shows the distribution of the examples. The validation and test set, again, are uniformly distributed, but the train set is a long-tailed distribution, meaning we have far more examples in class 0 and 1 than we do in 8 and 9. We also have the out of distribution classes as shown here. This is 5 other classes that we use. It is uniformly distributed through the validation set, but the test set matches a long tail distribution. We don't include any examples in the train data to avoid classifiers essentially having another class. So rather than a 10 class classifier being an 11 class classifier. The challenge began on January 11th of 2023 with the test data being released on March 13th, 2023 and the testing phase ending on March 16th, 2023. For the challenge results, in track 1, we had 119 teams participate, and of those teams, 44 submitted algorithms during the development phase and 43 submitted algorithms during the test phase. For track 2, we saw 105 teams participate, with 32 submitting during the development phase and 47 submitting during the testing phase. And again, we saw 173% improvement in accuracy over track 1 from 2022 and 175% over 2022. Here shows a breakdown of how the top teams from each year performed, so we can see a significant year-over-year performance increase. And here shows the breakdown of the total scores. This shows the accuracy and the AUROC combined scores. So for track 1, we can see the top score of 0.65, which corresponded to a 63% accuracy and a 0.7 AUROC. For track 2, we saw a total score of 0.84, and this corresponds to an 89.6% accuracy with a 0.68 AUROC. And so our track results, track 1 results are our ranks here are shown. For rank 1, we had Fasai 21. For rank 2, we had the team running. And for 3rd place was our 4th ranked team, which is Ragnuth 19. And for track 2, we had Overfitting as our rank 1 team. In 2nd place, we have the Doggy, and in 3rd place, we have the Ragnuth 19 again. So we're going to briefly highlight the challenge methods of these teams. For track 1, our first ranked team used a 3-stage approach. They used supervised training on the entire data set using a ResNet 101 backbone during the first set, and they used a class balance loss to address the long tail distribution and the data imbalance. In stage 2, they predict samples in the test set using a high confidence model and a clustering algorithm based off of DB scan and k-means. And then this is done, and then they take special consideration in the differing resolution of the images. And in stage 3, they introduce a novel, reliable sample pool to enhance the model's confidence in predicting in-distribution and out-of-distribution detection. They additionally fine-tune the model using the RSP. For rank 2, they propose a novel domain alignment embedded semi-supervised contrastive learning network, or DC-SEMNet. They design a keyframe extraction strategy to clean the data, and this is again done to accommodate the data imbalance. And then they propose a 2-stage training process. The first step, they use contrastive learning to learn the feature representations, and in stage 2, they utilized a high-confidence pseudo-labeled generation-based semi-supervised optimization strategy. Here shows an outline of the second of Team Running's model overview. And so we can see that they both take special consideration for the long tail distribution on the left and the OOD samples as well. Our rank 3 team uses novel data augmentation techniques to address the data imbalance of the data set, and they built their base model on ResNet 34. They fine-tuned using a triplet loss and a cross-entropy loss. And to reduce the dimensionality of the feature space, they performed principal analysis and KD tree analysis on the resulting features to obtain the to reduce that dimensionality. And they use the same architecture for both their track 1 and track 2 submissions. For track 2, the rank 1 team overfitting used a two-stage approach. The first one was a supervised training of multiple classifiers, and then they averaged the output of each classifier. And in stage 2, they added a classification model that focused on the easily confused classes. What they noticed is class 0 through 3 were easily confused, and they used a perceptual hash algorithm to cluster the samples that were classified as 0 to 3, and then fine-tuned on those classes. To fuse SAR and EO, they extract features using a convolution-based backbone model. Our rank 3 team, Doggy, proposed a balanced contrastive learning semi-supervised network for the multimodal aerial view object classification. They proposed keyframe extraction to clean the data and thereby reduce the similar samples of specific images in the data set, and this was done to help address the long-tail distribution. The two stages used were they first use a balanced contrastive learning feature network, and they stitch the data according to the channels. The data is input into this network to increase the inter-class gap and reduce the intra-class difference. For stage 2, they propose a high-confidence pseudo-label generation-based semi-supervised strategy, and they use the train classification network in the first stage to generate pseudo-labels of the testing data. And the winners are here. We'd like to congratulate everyone who participated. Our best paper award is going to go to a 3-stage framework with reliable sample pool for long-tail classification. And our running up paper will be appearance label balanced triplet loss for multimodal aerial view object classification.
So this concludes the presentation of the second challenge, the multimodal area view object classification challenge. And we have one more video to go before we can have a coffee, which is the presentation again from Spencer Lowe of the results of the multimodal. Oliver, can you again help me with this abbreviation?
So it's the aerial view image challenge, which is the translation task.
Yep, the image translation from SAR to EO, right?
Yeah.
Okay, cool. So let's get the video started.
I'm Spencer Lowe, and I'll be presenting on the multimodal area view image challenge. This one is the translation from synthetic aperture radar to electro-optical domain, and these are the results from our challenge in 2023. The primary goal of this challenge is to facilitate the development of reliable translation models that are capable of producing explainable, interpretable, and trustworthy outputs. The 2023 challenge introduces a translation-focused version of the Unicorn V2 dataset, and the challenge again is focused on aperture radar to electro-optical translation. Submissions are evaluated using a combination of mean squared error, perceptual loss, and Frechet inception distance. We are focused on producing, again, explainable and high-quality results, and this image here on the bottom shows an example of a failed translation. On the input SAR image on the left, we can see a brief outline, a small outline of an aircraft. In the middle, we can see the failed translation where the model hallucinates and doesn't quite get the translation done, and on the right, we can see the ground truth image that it is supposed to have translated the image to. For sensor translation goals, we would focus on, or what we hope to achieve, is to combine information from multiple sensors to enable a more comprehensive understanding of an environment or system. A data conversion approach aims to leverage the unique advantage of both SAR and EO sensors while mitigating their limitations. The Mavic challenge focuses on SAR and EO translation. The SAR's strengths include it is self-illuminated and can penetrate many clouds and vegetation. However, it does have weaknesses such as data scarcity and reduced human interpretability. This challenge was held jointly with the Perception Beyond the Visible Spectrum workshop, and it was designed to facilitate innovative approaches in multimodal translation. Participating teams were provided with a collection of image pairs consisting of SAR and EO modalities and are evaluated on their ability to translate from a SAR input to an EO output. These submissions are evaluated using a weighted average of mean squared error, perceptual loss, and Fichet inception distance. And here we can see our weighting. They're all equally weighted as 1/3 of the final score. For the metrics, we chose the Fichet inception distance as it provides a measure of similarity between the probability distributions of the deep feature representations of an image. This is done using this formula here, where we compare the means and the standard deviations of the probability distribution. What we did is we used layer 64 of the Inception v3 net as the deep feature layer, and the score had to be normalized to be between 0 and 1. And we did this by using the arctangent activation function, and we scaled that by 2/pi. We also use the Learn Perceptual Image Patch Similarity, or LPIPS metric, which again leverages deep feature representation to measure the similarity of two images, and it closely mimics how humans are able to perceive and distinguish between images. And our metric was based on VGG16. We then also used a vanilla mean squared error, which provides the Euclidean distance between the two images in pixel space. The dataset was based on the Unicorn V2 dataset, which is a SAR and EO aligned dataset. This updated dataset provides improved alignment between the two images. As this dataset is focused on sensor translation rather than having small chips that focus on specific classes, the SAR and EO images are first rectified and aligned via homography algorithms, and then subdivided into larger chips that are 256 by 256 pixels square. And these chips are not actually focused on specific examples, but are taken uniformly through the whole data set. The validation and test sets are also uniformly sampled from the full data set. This slide here shows examples of the data set. On the left, we have the EO image, and on the right, we have the SAR image that corresponds with that EO image. And these are very indicative of the training, test, and validation sets. The challenge began January 11th, 2023, and the testing data was released March 13th, 2023, with the testing phase ending March 16th, 2023. For the challenge results, we had 52 teams participate during the development phase, with 8 teams participating during the test phase. And our winners are shown here. We selected 2 top performers, and we are going to view their methods briefly. For our rank 1 team, the USTC IAT United team used an approach based on Pix-to-Pix HD. However, they used multiple generators and discriminators. Also, the original Pix-to-Pix HD is based on the UNet architecture. However, this team, for their generators, introduced a multi-level network, and for the discriminators, used a multi-scale network. They used matching loss and content loss to optimize the model, and they developed a SAR pre-processing module to help clean up that SAR data. Here shows an overview and outline of the approach that they used. As we can see, they actually used 2 generators and 2 discriminators, one set focusing on low resolution and one set focusing on high resolution data. For our rank 3 team and our second place team, the Wangzhou 918 Their approach is based on pix to pix, and they used a binary cross entropy and an L1 loss, and they built it on a unit as well. So in addition to the discriminator loss, they use these pixel space losses as well to achieve very good results. And here we can see an overview of the translation results from all of these top teams. So on the far left, we can see the SAR input. On the second column, we can see the ground truth, and then the following 3 columns are individual team submissions. And so we can see that, for example, USTC had very good results with very high fidelity translations. And in some of these we can see some hallucinations, but they're very minimal, and so we are very impressed with the overall quality of these teams' translations.
Okay. Do we have any questions on these 2 presentations? Oliver Nina is with us. He was also participating, or he was organizing this challenge. So you now have the chance to ask questions to Oliver, if you like.
You guys have any questions? I just want to thank everyone who participated in these 2 challenges. It's been a great opportunity, and thank you especially to Dr. Shaba and Dr. Tush, who's being organized in this. There's a lot of work involved, and Spencer did a great job. So please reach out if you have any feedback. Next year, we want to try to improve the data sets, bring newer challenges. So we're always collecting feedback. So please,
Yeah, can we have a complex SAR images? I mean, and we'll track it with complex SAR. Yeah.
So with complex numbers?
Yeah, with complex.
Yeah. So that's a great suggestion. We'll look into that. I know data is hard to come by sometimes. We have some raw data. We'll see what we can do. That's a great.
Yes, so actually we work with the AFR reduced team. I believe they have some.
Okay.
Yeah, so on their side, they are interested in complex SAR kind of image compression, but I would imagine we should have data set.
Yeah. Sometimes, I work for the government, so sometimes it's hard to get everything released. So so anyways, we'll see what we can do, but that's a great suggestion. Okay, thank you.
Yeah, so thank you to all actually the people who organized these challenges, Oliver and Spencer in particular here. And so this concludes the session on the challenges. We now will have a coffee break. We will come back again at 3:30, yes. And we will have our 4th keynote speaker there, Rikke Garde from Aalborg University, Denmark. So please come back at 3:30. We're looking forward to your participation. See you then.
Hey, we were in communication for a while. I used to work with Steve. He there head up and anyway, so this actually I was working at the data. Oh, yeah, pretty much. Very
And not much, not mostly gathering data for example, that in part perspective, side the work perspective, the actual work on this. Because my time complex to be user and I want to say. So I think that we got
We'll double check if we can also see it in the remote session.
by this year and also in the competition. It's good.
So yeah, here said you the presentation about 30 minutes, and then we would have 10 minutes for question and answer. That's fine.
Yeah, I'll go for that.
I will let you know so like 2 or 3 minutes before. And know that then you can slowly start.
Yeah. Oh yeah, we don't have it up here. Yes, that's the problem. But if you have the presenter mode, you can see it.
Right. I love the presenter mode.
Yeah.
So I would have loved to also provide it today.
Maybe
Today, but yeah.
I'll actually put the phone here just for the time.
It could help, yes. Mhm.
Special yeah.
But you actually like you can also put it here, just a little bit of space or some of the presenter.
Yeah.
Let's see.
I really got to give the one.
And maybe we can give people 1 or 2 more minutes to return. I think it's a quite long way to get coffee from here. So
It is a very long way.
Might be the reason why it takes people some time to go there and return, right?
I almost got lost when I was trying to get here because I missed the stairs.
Yes, same here. We have
And I just continued.
correct. We also had to ask to find our way.
Yes.
Okay, so I hope that people attending remotely are again seeing and hearing us. At least they can see us because I double checked. I hope they will also be able to hear us. Otherwise, they will write notice to the chat or something. So we return now for the last time block of our workshop, which is again introduced by a keynote. It's my sincere honor to have Professor Rikke Garde here with us from the Aalborg University in Denmark. She's actually the only speaker today who's not a keynote speaker who's not coming from Canada. And she will give a keynote presentation on thermal imaging for privacy-preserving surveillance applications. Rikke Garde is currently employed as Associate Professor at Aalborg University, Denmark in the Visual Analysis of People Lab. She received her Master of Science and her PhD degrees from Aalborg University in 2011 and 15, respectively. During her studies, she also visited the University of Auckland, New Zealand, and the University of Adelaide, Australia. The PhD thesis in computer vision focused on analysis of activities in sport arenas, mainly occupancy analysis, activity recognition, and tracking of players. Most of her work revolves around the use of thermal video to preserve privacy in public sports facilities. This has led to publications in top journals and international conferences within computer vision, and she has been co-organizing workshops at CVPR, ICCD, and ACCD. Her research interests include computer vision analysis of human activities, applied both for analysis of human behavior at public spaces as well as for analyzing sports activities. She also works with robot vision. So, Rikke, it's great to have you here today, and the floor is yours.
Yes. So what I will talk about today, besides the surveillance aspect, is also about the use of thermal imaging in real-world long-term applications. So I'll show some examples of some of these projects here today. So shortly, the agenda is start with a short introduction to thermal cameras and some of the data sets we have from our lab. Then I'll go into some of the sports projects I've worked on myself, and we've had another PhD student working on that. A more current project on what's called the Safe Harbor project and a new data set from that. And I'll also quickly touch upon a little bit of a different project called the Thermal Adaptive Architecture project. And then end with a brief slide on some takeaway points. So yeah, why am I here? We already had a nice introduction. So I just want to highlight that all of our work started about thermal cameras started with this PhD project on occupancy analysis in sports arenas, where we decided to go with thermal cameras only, because what I state here, we wanted to have the feeling of privacy, because I'm not saying that it is completely privacy preserving to have thermal cameras, but if you have a certain distance, at least you have some privacy preserving feature in that. And also it is much easier to convince people what we're doing here. You're only capturing a picture like this and not capturing a regular color image. So I call it the feeling of privacy, and we are losing on purpose a lot of these features that could otherwise recognize people in these arenas. So during my PhD, I also wrote this survey paper on thermal cameras and applications, which is still highly cited. And I think it's because I went a little bit into how thermal cameras actually work. So that described that. And that's also where I will start in this talk. But yeah, a note here. Some of these data sets are, of course, captured in Denmark, where we are from. We are in Northern Europe. So right now we are over here. And Denmark is here in Northern Europe. Specifically, Aalborg University is in the northern part of Denmark. If you know about the capital of Denmark, that's Copenhagen here. And we are in the northern part of the year there. And I wanted to highlight this because it influences the weather conditions and so on for the data sets that we're doing.
You may want to use the laser pointer power point, then also remote attach.
Yes. Good. Yep. So we are up here. Thanks. So now we'll go in a little bit into the thermal cameras. Probably many of you who are here already know about it, but still I find that many people know how the images look, but may not know exactly why it does look like that or how it's working. And then also the data sets that we've captured from our lab. So thermal camera, if you saw some of the previous speak, may have seen this. So we are in the infrared spectrum, but that's quite large. So we are specifically either capturing in the mid wavelength or the long wavelength infrared spectrum. And these two are kind of separated for a specific reason. The mid wavelength, as you see over here, the radiation is usually from 3 to 5 micrometers. And there's no reason to capture between around 5 and 8, or 5.5 and 7.5, because the radiation in this range is absorbed by the atmosphere. So either we're working down in the mid wavelength range, or we're working up in the long wavelength range. And the applications we're working here in long wavelengths. So that's also, these two spectra are also what's referred to often as thermal infrared, because the radiation comes from the thermal activity or the temperature of objects. So I think it's a nice thing to be aware of when people refer to infrared cameras. It can be anything. So they really need to specify where are we in the spectrum. Are we in the near infrared, which has similar properties to the regular RGB cameras, or are we further up in what we call the thermal infrared spectrum? Here's just a short video clip we produced just to compare the two modalities of RGB and thermal. So this showcases some of the nice properties of thermal imaging when we are trying to do human detection, that they usually stand out quite clear compared to in an RGB image because of the heat signatures. But there are also some properties we need to be aware of. For example, when this person gets close to the floor, we will start seeing reflections. So down here, yeah. So you have reflections of the thermal radiation from the camera, from the person into the camera. And of course, there can be other objects in the scene that are hot, like you have some heaters in the background, and there can be other things. So mostly we went for this modality for many of the first projects because of the privacy preserving property, and also because it eases the detection task of humans often. A little bit more on how this works. So where does this radiation come from? So as you may know, thermal cameras are passive sensors. So we don't need any illumination. You can record in complete darkness, and we don't have any illumination source. The radiation comes from the objects themselves, and it comes from the energy of the molecules. So what we see to the left here is just an illustration of the different energy states. I don't need to go too much into details because I'm not an expert in that, but specifically we have the electronic energy states, rotational and vibrational, and there's also something called translational energy states. And specifically rotation and vibration of the molecules is what translates into emission of thermal radiation. So if an object receives heat, it will rise in energy levels, or it may give this energy level to the surroundings and lose heat. So this is basically the physical property that we are using here, that any object above the absolute zero will emit thermal radiation. And then the exact temperature and intensity depends on firstly the temperature, and then also the material, of course. So the graph here to the right, here you see a graph of this is from a perfect emitter, so the same material. The lower graph here is an object of -20 degrees Celsius, and the top one, the blue one, is 100 degrees Celsius. So this shows the change in intensity and also in the dominating wavelength depending on the temperature. So the dominating wavelength shifts to shorter wavelengths closer to the visible spectrum, and also higher intensity depending on the temperature. So that's the properties that we use when capturing things with a thermal camera. And then there's some special things about the camera itself. Thermal radiation does not pass through glass, so you need to have a special lens, usually made of the metal called germanium. You need to have a special sensor. Some of these are called microbolometers. There are different types. Cameras can be cooled or uncooled, and can be calibrated or uncalibrated, meaning that they can either give you an absolute temperature or they can give you a relative temperature if you just need that. The thermal cameras still have a relatively low resolution, and at least the highest resolution are still very expensive. So we are not at the level of RGB cameras yet. And they were first used in the military and later adapted in various applications as we see today. So when working with something on computer vision, we know that we really need data. So we've also worked on a lot of data sets in our lab. We have the reverse timeline here, so starting from the top. It was when I was doing a PhD, focusing on the sports applications, capturing data sets from a sports arena. In the beginning, we were focusing only on thermal, but then we quickly went into what if we want to combine this and learn from different modalities. So we have a couple of data sets where we combined RGB, depth, and thermal modalities, both on face recognition and pain, but also the trimodal people segmentation data set. So that's what we see examples of in the bottom here. And then again, we have some more soccer and sports data sets. And we have a new data set, which I'll come back to later, which is called a long-term thermal drift data set from an outdoor harbor environment. So all of these data sets are the ones that we have public. And sometimes we have, of course, published, captured others for just some research purposes. But these ones are public and available on this link. So when we capture data sets with multiple modalities, it can be a little bit of an issue. This is one of the first multimodal data sets we captured, and we were working quite a lot on the different issues for this. So first of all, we went for RGB depth and thermal, and RGB and depth you can get in devices like this one is the Kinect. Today you could get many different devices where RGB and depth is integrated and calibrated and works out of the box. But then you want to add a thermal camera. So we need to work on, first of all, the spatial alignment, and we need to fix these two in relation to each other. So we build a very simple thing here to fix this and try to keep them on the same vertical axis. Then you need to fix the temporal alignment as well. So you need to align the clock, synchronize the clock between these devices. We have to create our own recording software using the SDKs of these different devices to try to synchronize it and capture frames at the same time. Then the calibration, of course, is also a little bit challenging when you're working with thermal cameras. For the RGB and depth, that comes out of the box. So when you choose a device where it's already calibrated, but then you want to add the calibration with the thermal. So what we did here was to use this 2 layers of cardboard, where on the top one, the blue one in the pictures, we've cut holes in this one. And then we heated the back layer, the white layer, and cooled the blue layer. And then it becomes looking like this in the thermal image. And you only had a few minutes to calibrate this before the hot one cooled down and the other one warmed up. Then you had to repeat this procedure. But that was the best thing we could come up with to get a similarly looking image in both RGB and thermal. So we had to do something about the temperature of these different plates. And then, of course, the registration. When we're doing this calibration procedure, moving this checkerboard thing around, then we are doing the calibration, generating multiple homographies. Because we're working in a 3D space, it's not just one simple registration. But then we generate multiple homographies for each of the views. And then later on, when doing a registration of a point, we need to find the nearby homographies of that specific point, referring through the RGB and depth image, and then do the transformation between the images. So there's a little bit of a workaround when doing multimodal data sets like this. But what came out of this was this trimodal people segmentation data set with annotations for detection and segmentation from 3 different indoor scenes. It's available on Kaggle. I have an example of it here. So in the thermal mode, we made sure that we had a couple of hot objects. And here we have a toaster. There are some pipes and some heater here. And at some point, this person will also leave. We have a laptop coming in now, which will generate some heat at some point. So there's some different things going on. Yeah, as I just talked to you just before that about this residual heat that we have when he leaves the chair. So there are many different challenging things still in a data set like this. So now I'll move on to one of the big projects we have been running with thermal imaging, so sports projects, work done by myself some years ago and our PhD student Noel Huda. So the main purpose of these projects were to do occupancy analysis in public sports arenas, because most of the sports arenas in our local area are owned by a municipality and then just rented by the hour by the local clubs. And it's very cheap for them to rent it, so they just block it in the entire evening, but they may not use it. So of course, the municipality want to do an occupancy analysis to see if they can optimize the use of these facilities. And the old way to do this was to send a person, note down how many people are in this arena right now. But that's, of course, that does not give the full picture. So we could put up a camera and we could do this surveillance task over 24 hours a day, over a long time. And here we really needed to care about the privacy because it's used by everyone from small kids to elderly people, and they don't want it to be like a surveillance camera. So we went for the thermal camera to say that we are able to preserve most of the privacy at least. But we have seen that some people are able to recognize themselves from the way they walk or the way they run. But you need to have some prior knowledge about a person for that. So in the beginning, we started in the indoor sports arenas. Being able to cover this required 3 cameras. So we had to build a custom box like this one with 3 thermal cameras and then stitch the images like we see in the top video here. So that required both a bit of manual work to get the box aligned as good as possible, and then a little bit of image processing later to do the best possible stitching of the images. Then back then, worked with classic image processing. So meaning that the first step was to do a thresholding of the image to get this binary image, and then try to do a detection of single persons. And that was quite a challenge when you just have this binary image to work on. And that was before the neural networks really started to kick in. So I worked with many different creative solutions to get the bounding boxes of individual people. So they're not, as you see, they're not actual bounding boxes. They're a representation of where their feet are and then an average height of the boxes. But of course, with occlusions and everything and non-ideal segmentations, there are a lot of problems to handle here. So we got a decent result on this and got the results as this was visualized in this table. So the colors in these columns means how many people we found in the arena. And then they could compare to the booking. So if they're green, it means that there were 0 people. So probably there could have been an activity here, but then no one was here. But besides that, we wanted to move a little bit further on what can we do when we then have these detections. And this video shows some of it. So this is also when we put location on the people. It's not running too well, but it's just trying to visualize where are people, and if people like gather together, then the peak becomes higher. Analyzing that led to some activity recognitions. So either based on heat maps to the left here, we could, over some, I think it's this 10-minute periods, we could recognize the sports type that they were performing based on the heat maps from the location in the room. And I'll also work with tracklets. I was not going for full trajectories because it was not really possible to track a single person over a long time when you only have this thermal information. So we were happy with tracklets and then analyzing on those. And we can easily see from this that we can see some different sports types: handball, badminton, basketball, football, and volleyball are the examples we saw in this arena. After this, we wanted to move to outdoor sports fields because there's a huge potential also for the same purpose on these ones. So can we optimize the use of these public sports facilities? And then we start facing lots of new challenges. Because what about in the indoor, the climate was more or less stable. Of course, the temperature could vary a little bit, but other than that, it was quite stable. People were wearing the same short sleeves and so on. Playing outdoors, especially in Denmark maybe, and similar countries, I guess also here and in Canada, weather will change quite a lot. So what we saw was changes in weather. So that could be rain, snow, fog, frost, sunny days, and so on. Temperature. What you see in the bottom pictures, so these are shadows. And that's not, in thermal domain, it's not like regular shadows. It's because the sun is not hitting the ground in these places that are dark here. So the sun heats the ground where it's bright, and it does not hit the ground here in the other areas. And then, of course, these are large fields. The humans, the appearance vary, but also because they are wearing different clothing. So if they're wearing jackets and clothing with more insulation, it will look a little bit different. So the detection task is not that easy anymore. And that was the main task that this PC tried to solve. So here we try to kind of map what are the different problems that we face, and how can we train a detector to handle these different problems and be stable over all these different weather conditions. So we have a lot of data from different sports arenas, outdoor arenas, and also different times of the year. So here you see we are covering different viewpoints, different heat effects. So what's called here the opposite temperature, that means when the ground is hotter than the person, because what we call the usual one, the person will be hotter than the ground. And of course, things like shadows, snow, wind in the here. So what we did here was just to try to train a YOLO V3 model with transfer learning on this new data, and then see what happens if we add each of these categories. Will the accuracy actually go up? And yes, it does help to add these different categories when they are in the test set as well. And it matters more with the actual categories than the numbers of images. But we also need to be careful with what we add here, because at some point it may learn that everything could be a human, because it may look like that. And so we really need to be careful with what are we looking for, what do we expect to have in the test set, and then only add these categories to try to not induce too many false positives. In this project, we also tried to look at, okay, what if we actually went for the easier or cheaper solution with a fisheye RGB camera that can cover the entire arena here. This is still relatively privacy preserving because of the large distance, meaning the low resolution of the people here. I'll not cover the work on only this modality, but what was interesting was that we tried to combine this with a thermal camera to get the best from both worlds. So here in the center, we had a thermal camera covering this part, and we tried only with one thermal camera because they are relatively expensive. So what if we could use one thermal camera and then one fisheye to cover the rest of the field here? So the idea was to use the detector on the thermal camera as a teacher. We kind of expected that to be of high accuracy, so we could use that as the ground truth, and then take the detections from the thermal camera and use that as annotations on the fisheye camera. And then we did some extra work to add these detections on the other parts of the fisheye camera. I think that was an interesting proposal to do a relatively cheap and interesting setup for long-term monitoring on outdoor arenas. So I'll move on now to what we call the Safe Harbor project. Work mainly done by our recent PC, Yincheng Liu and Ivan Nicola. So this project is about monitoring the harbor area in Aalborg. So the thing is that the city has a large harbor area which is very popular to just walk here, and there's no fence or anything. So especially during night, sometimes people fall into the water. Luckily, most of the time, someone sees that and they get up, or maybe they are able to find a ladder themselves and then climb back up. But sometimes, especially because there are some bars nearby, drunk people go here, they fall into the water, and sometimes they do disappear. So of course, there's a big demand for some systems here to find these people and help them. This is a short video here of what happens most of the time during the night. We did a compilation of what happens near the water front here, and this is what happens most of the time. So this is what happens during night, and then sometimes they do happen to fall into the water. We have an operational system now which actually gives an alarm when people pass this red line. So this is what we call the safety line. If anyone passes this line, they will fall into the water. So if people pass this line, and we see that by analyzing the optical flow, then an alarm will actually sound at the rescue department in the city. But they need to check the images before then they go and rescue people. Because it may be that a bird or something is flying close to the camera and may look similar to the human. So this is in operation now and has actually helped some people by saving them from the water. Because the problem is, if no one is around, if no one sees this, and they are not able to get up themselves, what to do? So this camera system is really worth some lives now. But of course, we want to improve on this, and we want to reduce the number of false positives. So what could we do? The first problem is that we have rare data of people falling into the water. So this paper worked on generating more data with a human-like doll. And what they did was to kind of fill it with hot water. It has some system under the clothing, so you could fill it with hot water. And as you see in these 4 images, it will appear pretty much like a human. So that generated some training data without pushing real people into the cold water. A second problem is that this system needs to work across all seasons and conditions. And that's also very difficult. So that started the recording of the new data set. So you see examples of that here from this surveillance camera. Some details of the data set is that we captured during 8 months, have many hours of video, but they have been cut down to 2-minute clips and a total of 298 hours during the months from February to August. So it covers day and it records 24 hours a day, and we have selected clips to represent all conditions, day, night, all weather conditions, and 8 different months. So this has also been used in this last project of the Safe Harbor project. So the problem is that when people enters the waters, that's what we are mainly able to detect right now. It may be too late because it does take some time for the rescue people to reach the harbor. So even though they have a pan-tilt camera, they can try to follow the person, they may lose track of it. So what if we could actually predict that this person may have some behavior that may make that person fall into the water later? 2 papers came out of this. First, the one on supervised versus self-supervised assistant for surveillance and harbor fronts, a little bit general. And then the last one specifically on detecting anomaly reliable in this long-term surveillance systems. So what if we could tell that all the activities that are going on in this area, and that's quite a lot, during a sunny day, it's really busy, people walking here. But what if we could detect the anomalies? And it is especially during night. That's also one of the reasons that a thermal camera is really nice in this application. So analyzing this long-term data set led to a few findings. First of all, that we do probably as expected see a clear performance degradation when training on data from 1 month and then testing on different seasons. So we need to be aware of that and handle that. The main factors are the temperature and the humidity in the environment. And then the proposed solutions that came up in this latest paper was to try to use autoencoders as for anomaly detection. And then it helps to do a foreground background segmentation, either with some like a mixed Gaussian model or a human detection, and then mainly weigh the foreground objects higher than the background, because then you downweigh the influence of the environmental factors a little bit. And we still have ongoing works on this one, especially on the anomaly detection part. Then the last project I'll talk just a little bit about is a little bit different because now we zoom in on a single person or a few persons. So here we are talking about thermal comfort. And this is the cross-disciplinary project. So the aim is to optimize the human well-being by adapting the microclimate in offices. So you have a lot of systems that can control the temperature and everything, but how does the person actually feel? Can we do something about that? And we aim for a non-invasive solution, so meaning that we will not take into account different wearable devices that could monitor skin temperature, heartbeat rate, and such things. So we want to have a computer vision solution. The factors that influence this microclimate is some environmental factors: air temperature, mean radiant temperature, air velocity, and relative humidity. We are not working on these. We are working on the personal factors, the clothing insulation rate, metabolic rate. So these two things. So we're trying to come up with a computer vision solution for estimating these two different factors. So in this paper, before we worked mainly with a thermal camera giving us relative temperatures. Now we're working with one giving us absolute temperatures because we need the actual temperature of the human skin and the clothing parts. So we're trying to estimate these two factors. So that also led to two data sets. First, just working on one person, which was fully visible, either standing, sitting, or walking, because that affects the metabolic rate. And then 5 different clothing types: t-shirt, long sleeves, roll-up sleeves, long sleeves with unzipped zipper, and roll-up sleeves with unzipped zipper, because that says something about your thermal comfort. If you start unzipping your zipper or rolling up your sleeves, you may feel a little bit hot. So that was the first data set, and the second one is a little bit more realistic for an office environment. So here we have 2 people. And they are sometimes blocked by either a laptop or a chair, and they are more free in their movement in this environment. So the solution for the single person, the idea is to estimate both the clothing type and the activity of that person, basically standing, sitting, walking. And that is handled by CNN. And also open pose will give the different joints of the body, because we can then use that to choose the right places to measure the skin temperature. So if the classifier says that you're wearing a t-shirt, and then you can use the pose estimator to say where should we sample the temperature from the thermal camera to get the skin temperature and the clothing temperature. So all these things goes into the estimation of the clothing type and also the metabolic rate.
Please finish in 2 minutes.
Yes. And then for the multiple person data set, it's almost the same idea, but now we just need to add a tracking module to track the individual people here. But we still do human detection and pose estimation and tracking to estimate clothing insulation and metabolic rate. Yes, so I'll finish with the last slide here. There are many things that we could keep discussing in this area, and I think we see a lot of interesting new work. So one I want to say here is just that for processing thermal images, it's pretty easy to get started. We have many student projects working on this, and they can basically take a pre-trained CNN. It just have a single input layer like a grayscale image, and then do some transfer learning with a relatively small data set. So it's not a big problem to do a little bit on the thermal camera or thermal imaging. But when you start applying this in the real world outdoor applications, we need to care about a few things. So first of all, if we want to do a long-term application, we need these long-term diverse training data sets. And also for thermal cameras, you need to be aware of these special properties like reflections, emissivity, and the surface temperature. So you should not always care about that. The temperature is 20 degrees Celsius today. You should care about how does the sun and the the weather actually affect the surfaces. So that might turn out to give you some some different properties in the image. Yes, I think that was it.
Thank you very much. We have a few minutes of time for questions. Do we have questions? Yes, please.
Thanks for the talk. I'm wondering, in the long-term outdoor application, do you think it would be possible somehow kind of normalize the events of the image with some kind of neural networks so that you think it would be possible something like
In this normalize the appearance?
To help for detection?
Yeah. I think so. Also now you can actually convert between RGB and thermal images. So I think you can also relatively easily recognize one of these different parts of the image and then kind of normalize the appearance of these things. I think so. The problem is just that when we're looking for anomalies, we don't want to normalize these things. We want to be sure that we get these things while just normalizing the normal appearance.
Yes, please.
Thermal cameras have usually wider dynamic range, 12 bits, 14 bits, something like that. Did you pre-process your images or videos, or just mapped to the, I don't know, the range of 256 levels?
Yeah, usually we have just worked with the 8-bit representation of the images. Yeah.
I think you were first, right?
I was just curious about how you measured like more specifically the metabolism of the video.
Yeah, so there are some standard tables for the average metabolic rate for different activities. So we simply wanted to estimate the activity based on sitting, standing, walking. And in the latest work with several people, we also used optical flow to see how much do they move. So the activity is simply mapped through these standard tables. Yeah, so you categorize into the activity, and then you have a lookup table that this in average corresponds to a metabolic rate of this value.
Yes.
It seems like you worked a lot with thermal data sets that involve humans. So did you have to get like IRBs for every data set you made, or?
Only the ones where we are taking close-up pictures, like we have the pain data set, where we were pretty close up the face. And for that one, we have some procedures. They signed some documents and so on. For these ones where it's more surveillance-like, the general opinion is that we're not able to recognize people from that, so we do not obtain any permission for that.
And I actually have a question, if I may ask one question as well. You were mentioning this human-like doll that you threw into the water to simulate humans falling into the water.
Yeah.
Did you ever consider to use, instead of this doll, the modern data augmentation techniques like copy-paste augmentation, for example? Because the doll is quite rigid, but I mean, using like human silhouettes with copy-paste augmentation, this might give a more variation of the data.
Yeah. But we have some ongoing work now with synthetic data, where we are trying to add some synthetic, both humans and other objects into the image.
Right. I mean, using like real objects from real images, but like just like copy pasting them.
Yeah.
We made some good experience with that. That's why I was asking. And I think it's easier than doing it more and more times.
Yeah. So we started with a real data set. The first data set was real people jumping into the water. Okay. Yeah, and then it was hard to get volunteers for that. And then it's all yeah.
Okay, there was one more question.
Is it me?
No, sorry. You will be next. Okay.
So you did for this did you fine-tune your open code, or did you just generalize from Coco? And the second one regarding your data set, how you sampled it? Did you have some strategy? Because it's a huge amount of data.
Yeah. I'm actually not sure. I'm not sure about that part. Sorry.
So we have a question from a remote attendee. Please open the mic and ask the question.
Yes, hello, Professor. Thank you so much for a very interesting presentation. I have a question about the thermal RGB registration process. It's a problem that we've been working on a lot. And if I understood correctly, the way you were able to achieve excellent pixel-wise registration between thermal and RGB is by utilizing a RGBD camera. And then based on the distance to the sensor pixel, we were able to reproject based on different tomography matrices depending on the distance of the object. My question is, would you have any ideas over how we could do that for maybe outdoor scenes, for autonomous cars, for example, where we don't have access to an RGBD camera because of environmental limitations, distance to the sensitivity to light, and the range of RGBD sensor. Would you be able to maybe give us insights over ways to do this, given only RGB and thermal cameras perform registration that works for objects at different distances from the setup?
So if they're all on the same plane, then it can work still. But if you have different height of them.
Distances, like you have a pedestrian that's very close, and then a pedestrian that's quite far.
Yeah, and I know there'll be some issues. But what we did in the sports project was to do a homography to the plane, which is the floor. So if they're all on the same floor, then you can get a relatively good precision on that plane. But of course, when they have different heights, then you'll have some problems with that.
Yeah.
I don't have a solution for that.
Yeah, I had in the paper that I'll be presenting in a bit, we were able to do that registration, but the objects were all rather far away from the sensor. But when we attempted to do something similar where we have pedestrians that are close to the sensor and then pedestrians that are very far, then it was quite difficult to do it.
So if you have calibrated rectified images and then and you can map to the same plane, and you make sure, of course, during the calibration that you do calibration throughout the entire scene, then you should be able to calculate the calibration between the image plane and the ground plane.
Yeah. All right. Thank you so much.
Thank you.
Okay. So I think it's time to move on. Thank you very much, Rikke, for the presentation. Thank you very much. I will do that. Okay, so this was the last keynote for today, and now we have one final session consisting of, I think 7 papers, where we will have different presentations, and I think we did the grouping for this session. Yes. Yes, I think we will do it on the fly if it's okay for you. Do you have a PowerPoint presentation there? So we will just plug the USB stick later, and you will do it from the USB stick. This worked out before, so it will work out again, I guess. Okay, so we have this last session on multimodal fusion, and we will start with the first speaker. It's Shitish. You hear? Great, fantastic. I will open the slides, and then I will, feel free to come to the floor. We will start immediately. So I need to go to this mode. Okay, seems to work. I will set on your laser pointer. So feel free to leave the laser pointer over there. And I click here. And well, the floor is yours. Thank you for being here with us.
So good afternoon, everyone. Today I will be presenting an unsupervised attention-based framework for cross-spectrum facial recognition and how it could mitigate some effects of catastrophic interference or forgetting. This work was done at the University of Nebraska-Lincoln with collaboration with Blue Halo. So facial recognition has seen tremendous progress, as we all know, from unlocking your smartphone to like airport security. But as we are aware that in security applications, that have cameras placed outdoors, they are sensitive to illumination changes, making it difficult to recognize in lightly dimmed environments. So instead, infrared or thermal imagery, to be specific, has been deployed that still retain some discriminative features for biometrics. But as most of the enrollment or the gallery databases consist of RGB images, it creates this huge challenge of matching an IR image, like a query, to a pool of gallery of visible images. And so this is the cross-spectrum recognition problem that we address in this paper. There are three broad challenges to solve this problem. First is the lack of data sets that have both RGB and IR images captured of the same identity to perform any kind of deep learning or machine learning technique, even though it's getting better now. Second is the lack of labeled paired RGB and IR images and the significant amount of time it takes to actually curate and label these images, especially pairs of images. And third is the learning a representation that is invariant to both the domains, that it is difficult to bridge the gap between the two RGB and IR images for recognition because of the obvious lack of color and texture details. And so supervised methods have addressed this problem using a spectral transform that builds kind of domain invariance, but it has risks of overfitting, and it needs and the lack of label data makes it difficult to build a robust model. Generative methods like so synthesize a visible image from an IR image, but again it creates a new domain which creates a domain gap between the synthesized and the real image, and so resulting in subpar performance. But recently, unsupervised methods have shown promise in RGB-based person re-identification using clustering, but hasn't been explored for cross-spectral clustering for recognition. So in this work, we propose an unsupervised cross-spectrum framework that learns spectral invariant representations for facial recognition without using any identity labels. First, we use a multi-part attention transform that promotes localized information to limit the spectral context between the two domains. We then use a pseudo labeling by clustering and matching strategies to optimize the network using a cross-memory bank. And finally, we evaluated on two large-scale data sets, the ARL-VTF and TUFS, and also show how unsupervised learning mitigates some effects of catastrophic forgetting or interference. In the multi-part attention model, we use a lightweight backbone efficient net that has fewer than 1 million parameters with a multi-part attention head that splits the feature maps and calculates the attention using a convolutional transform and a sigmoid activation. We also introduce a learnable weighting parameter called alpha here for each of the region to automatically learn the most discriminative local regions to focus on across the domains. And so this ranking of the spatial and channel regions then refines the original feature map, and the parts are concatenated together to generate the final representation. To optimize the network, we generate pseudo labels by first clustering the samples intra-domain, that is RGB and IR features are clustered separately using density-based spatial clustering. And then for each sample in the RGB cluster formed, each sample votes for a IR cluster like so, and the most common or the most voted cluster is selected as the pair. And so these pseudo labels are then used to optimize the memory bank, where it stores the average representation of each cluster. And so the detailed methodology can be found in the paper, but I'm just giving an overview here. So with this robust clustering and matching strategy, we are able to determine confident clusters that leads to performance comparable with state-of-the-art supervised methods on both the data sets. We know with the true positive rates as at 1% false acceptance rate as large as 98.55% compared to 96% for supervised methods. It's a huge gain in performance without using any identity labels. But we also find that this type of unsupervised learning helps mitigate some effects of catastrophic interference. So catastrophic forgetting or interference is a phenomenon where the model is fine-tuned on a data set, say data set 1, and then trained on data set 2, And then when it's tested it back on data set one, the performance is lower because the model forgot previously learned information upon learning new information. And to study the effects of catastrophic interference, we employ two settings, training and testing on the Tufts data set, testing on ARL, fine-tuning on ARL, and then testing it back on the Tufts data set. And as we can see, the performance drops from 54% to 34% when we test it back on the Tufts data set after training on another data set. But in the case of unsupervised learning, you see like the performance is 43%, which is lower than the supervised approach, which is expected, but it transfers better. And when it's tested back on the original data set, it retains the same performance, and in this case, kind of improves performance as well. We present the ranking results here, where the IR is the infrared image is the probe, and these are the ranking results of the gallery. And we see that supervised methods are consistently biased towards eyewear or skin color, whereas unsupervised methods mitigates those biases because we are not kind of trying to force a representation to match, but actually clustering using generic patterns and focusing on distinct features of the face. So in conclusion, we present an efficient attention-based model that helps limit spectral context and learns with few amounts of data without annotations. And the clustering and matching strategies generates robust pseudo labels where they are used by the cross-spectral memory bank to gravitate the identity representation to a single compact cluster center. And so this unsupervised learning helps learn generic visual patterns and achieves performance similar to like supervised methods while mitigating bias with low catastrophic interference. Thank you.
Thank you, Jitish. Do we have questions? I think you both had raised hands, and we have to figure out who was first. Sorry.
Maybe it's a detailed question. So for unsupervised clustering, you're using a perfect model, right?
Yeah.
So how does it handle these domain gap and then successfully puts them into the same bucket?
Right. So first we do like a intra-domain clustering approach. So with that, small variations can be clustered together. And then we use this kind of matching strategy. So for an RGB image, we then match to, like once you have a large number of samples in the RGB cluster, you kind of look for the most voted cluster. And this can be done in an iterative manner. So once you have like some amount of clusters, you can fine-tune your model and then go back to your clustering and matching strategy and then keep repeating that until you get a good representation.
Thanks for that. I'm just wondering, is there a case where it's absolutely impossible to match RGB with IR? I mean, someone had beer, glasses. I mean, is it always possible, or it's
right? Yeah.
Problem?
Yeah, for supervised learning, I think there has been some progress with like different poses and, like you said, like presentation attacks with like, sunglasses and hats. In unsupervised learning, it can be challenging, and we haven't really explored that. This is more, this had varying expressions and baseline, but it didn't, we haven't tested it on like different, presentation attacks, but it does work with sunglasses as well. So, yeah.
And vision glasses.
Right, yeah.
Because sunglasses, you see them in both modalities. When they're transparent.
Right, yeah. With sunglasses or vision glasses, yeah. But like very different poses can be a problem.
Okay, thank you, speaker again.
Okay. Thank you. We continued as, if I remember correctly, the next presentation will be done via, will be done remotely. I think it will be done remotely. We do have a video and as a backup, but I kindly asked one of the authors of the next paper, multi-sensor horizontal guided attention network, to open the mic and speak up.
Hello, yes, I'm here. Hi, I'm Alicia.
Hey, Alicia. Nice to meet you virtually.
Yes, yes, nice, thank you.
I will stop screen sharing so that you can take over.
Perfect. Thank you.
So at your convenience, just start sharing the screen and just give me a quick moment to double check if we can see here in the meeting room, can see your presentation. This
Yes.
looks
Can you see it?
pretty good already. Yes. So yeah, feel free to start.
Okay, thank you very much. Hello, my name is Alicja Kwaśniewska. I am an ML architect at SIMA.ai, and it's my pleasure to present you today our work on aerial vehicle perception that we worked on in collaboration with colleagues from General Atomics and Lockheed Martin. So I would like to start with introducing the background of our study. So we all know that efficient multitask perception beyond visual spectrum with AI and ML is needed, both for commercial industry and Department of Defense. But I would like to emphasize why AI is really important in this domain. Usually, when we have a human operator, it's impossible to process in real time huge amounts of data. With AI, we can actually perform decisions in real time. And in this way, we don't lose information about troops movement or some other critical information about our mission. But of course, there are some limitations of image data, especially of the visual spectrum data. So you can see some of the limitations on this slide. The images might be noisy, there might be a lost connection, the frames might be corrupted, or there are also some occlusions. So these issues could be solved by using fusion and also a model ensemble. But at the same time, the platforms that we are considering in our study, like unmanned aerial vehicles, UAVs, they have to meet SWaP requirements, so size, weight, and power requirements. So the model that we design cannot be huge. It cannot, use a lot of memory, use a lot of computation. So we have to really design efficient AI algorithms for these platforms. And the problem of sensor fusion and ensemble is a well-known problem. There are multiple solutions already proposed, and I would like to focus on two groups of solutions. So from the first one, from the sensor fusion solution, I would like to mention multi-level attention fusion network. This is a solution that was using a fusion of visible spectrum data and audio data for event classification. It was a really nice solution, and in this application, it was performing really well. But like the limitation that we noticed, it was that it was using a single feature-wise linear modulation layer. So it might not be efficient in challenging conditions, or it may not apply well to infrared data. From the second group, we'd like to mention a probabilistic deep learning method using film layer as well. So in this study, authors proposed implicit ensemble, and performance was similar to explicit ensemble solution at a fraction of the memory cost. However, the solution did not target sensor fusion multitask learning and was not tested with transformers or pre-trained models. So in our study, we wanted to look into these issues and see if they could be further addressed. So the model that we proposed was called MENSA. The modifications that we introduced are marked in blue. So this solution is used for aerial vehicle classification using audio and infrared data. And it works even if the samples are not synchronized. In the film block, we introduced this implicit ensemble that can modulate the audio feature maps that are conditioned by the infrared data. And in this way, we hope that scenarios that we want to address, like noisy data, could be handled much better than if the single layer is used, while keeping the memory of the entire model at the minimum to be able to meet the SWaP requirement. The proposed model was tested by us on the open source drone detection dataset. So we used two classes, drone and helicopter, in our study. And we performed two types of experiments. So we perform experiments on the original data set. So we performed grid search to find the best configuration and to find what number of ensembles would be best for our task. And then we wanted to verify if the model is really robust to noisy data. So we introduced random noise to both visual and audio channels. And then we tested previously trained models on such data. And on the slide, you can see results on the original data. So the bottom row is the original, the model from the previous work. So you can see that it was able to achieve 80% accuracy, while for ensemble-based methods, we are able to achieve higher accuracy. However, at some point, the accuracy may drop again. So you can see that for a number of ensembles, 8 and higher, the accuracy was dropping again. So it's important to really verify what number of ensembles work best for your data and for your solution. And after that, we performed experiments using the noisy data. So in this table, we present the percentage of the test accuracy decrease. So for the original, the state-of-the-art model, you can see that especially for the vision noise, the accuracy may drop by 30% for the noisy data. While when you use ensembles, like 5 ensembles here were the best, the accuracy decreased only by 4%. Okay, and to conclude, we are able to achieve higher accuracy in the task that we are addressing. And as I said, it's important to carefully select the number of ensembles, but we proved that it can help with restoring accuracy on noisy data. And of course, the results are promising, but further evaluation is needed. They are only preliminary. So we want to evaluate the model on other data sets. We want to use different backbones for feature extraction in the future. And then we also want to apply additional pre-processing, like, for example, increase the receptive field, which was already proved in the state-of-the-art work to work best with thermal data. And then the model was not compared with single modality solutions. So we want to perform that evaluation as well. Thank you.
Thank you very much. Do we have questions? This does not seem to be the case. So it seems that you clearly described everything. Since we are again a little bit behind schedule, in that case, I would like to go to the next speaker. Thank you very much, Alicia, for doing this presentation remotely. And
thank you.
See you. Bye.
Thanks. Bye.
Okay, so we go on to the third presentation. It's Eleni. See, I hope this will work now. No, it's not. We have again the same issue as we had it multiple times today. That screen sharing is not working, as that sharing the screen when Zoom is not working. You see the error code. Fantastic. I love it. Okay, we have to restart Zoom. Start them. Okay, so now we should be online again, and everybody remotely attending should be able to hear us again, hopefully. Now let's see if we are allowed to share the screen. And oops.
You should be like accepting.
If there's no agreement to PowerPoint. You should move that mouse over, I think.
What should I do? Sorry.
Yeah, except here.
Oh, okay. Okay.
And also except here.
And also accept here. That's perfect. And wait, so it means that the presentation is already.
Yeah, you can share the player. Maybe you can share it.
I'm already sharing, I think, but I'm just wondering why this presentation is already up when we are here, not still in PowerPoint. Oh, okay.
It's working.
Yeah, it's working. Cool.
Don't do that.
We have to do this because otherwise people remotely attending will only see the presentation mode and not the slide mode. So, okay, I will also switch on the laser pointer for you. And so feel free to get started.
So if I click, we have to click to go to the next.
You can use the cursors maybe.
Oh, all right. Okay. Good afternoon, everyone. My name is Eleni from Queen's University Belfast, and I will present you our work on domain generalization across visual modalities for the task of vehicle re-identification. So I'll go straight to the slides. First, just a brief introduction on what vehicle re-identification is about. So having a vehicle captured from one camera view, re-identification is to be able to identify the same vehicle among other vehicles that are captured from different cameras when the fields of view of the cameras do not overlap. So for example, here, having a query image on the left, the re-identification model should be able to say which of the images on the right show the same vehicle and which do not. And now a more accurate way to define re-identification is what we see here on the right. So having a query image of a vehicle, we need to search over numerous gallery images to find and retrieve the same vehicle captured by different cameras. So that means that in computer vision, re-identification is mainly modeled as a retrieval task. Now, for multimodal re-identification, we consider multiple sensor types. So here we have traditional visible light sensors that give the RGB data, and we also have infrared sensors, and in this data set we have near infrared images and also thermal infrared images. So apparently multimodal systems are able to address limitations of single modality systems, such as perform under low visibility conditions or at night time. So we would like to create models that can perform on multiple visual modalities. Now, to train those models, in the ideal scenario, we would like to have training data availability for all the visual modalities that are considered. But often this is not the case. So we would like to have re-identification models that can easily adapt to new modalities. Now, on the data side, we can see that the large differences in the ways of visualizing the different modalities induce high domain discrepancy, or in other words, the heterogeneity between the different modality input data translates into large domain gaps between their distributions in the embedding space. And that is a major challenge when training multimodal systems, as we would like to have systems that can generalize in multiple modalities, as I said. So in this work, we examined the ability of a re-identification model to perform on data that comes from a completely unseen visual modality at testing time. Say, for example, that we train our model on RGB and near-infrared images, and then at testing time, we evaluate it on thermal infrared data. Now, to this end, we propose our framework that is based on meta-learning training, which I will explain better in the next slide. So first, let me tell you that we separate the the domains, the different modalities into source and target domains in a leave one out way. So we have 2 source domains and 1 target domain. And then we apply the meta-learning training paradigm in a way to imitate the train testing domain shift. Now, let's have a closer look to the framework. So during training, we have 2 source domains, and we iteratively assign each one of them as meta-train and meta-test domains. As backbone, we use our ResNet 50. And for the loss computation, we have a combination of a metric learning loss function that is usually employed for similarity learning tasks, and also classification loss. Now, how the training works is that the model takes as input the meta-train domain data, which in this case is the RGB images, and we compute the meta-train loss. Then we use the meta-train loss to temporarily update the model's parameters, and we save this temporary model. Then we use this model and we put as input the meta-test domain data, which in this case is the near-infrared data, and we compute the meta-test loss. Then we sum the meta-train and the meta-test losses, and we finally update the initial model according to the summation of the 2 losses. So in this way, we expose the model to the domain shift through this 2-step backpropagation process. And we expect that this type of training will create a more generalizable model. And then we see that at testing time, the model is evaluated on a target domain, which is previously unseen during training. We evaluate our system against our baseline, which basically trains the model by just the summation of the losses from the source domains with conventional backpropagation, not with meta-learning. And if we have a look at the results table, we can see that the meta-learning training process provides a consistent improvement over the baseline under any source and target selection settings. And that means that it indeed increases the out-of-distribution generalization ability of the ReAD model. Then under the table, you can also see some qualitative results as they are provided by our model. And these are some preliminary results. So as future work, we would like to evaluate this system on more benchmarks. And also something else is that in these experiments, we were limited in the number of source domains because of the dataset construction, we just had 2 source domains. So the presence of more modalities, even synthetic ones, even generated ones, would allow us to do more meta-train, meta-test pair combinations. And this is a direction for this work because that would allow us to explore the full potential of applying meta-learning for cross-modality domain generalization. And that is the end. Thank you for your attention.
Do we have questions? Yes, please. Thanks a lot for the presentation. I was wondering, like, what is the intuition behind the, like, it's better than the baseline, but so is there any intuition why when you do this temporary updates, something useful happening there, right? So something like agnostic to the modality is stored somehow. Isn't the reason? Any idea on the intuition why it works?
Yeah. So when we do this type of training, we basically first update the model according to modality 1, let's say, and then see how this updated model performs on modality 2, that they are both available during training. And we kind of penalize the model to its ability to perform on modality 2 by being trained on modality 1. And we do that through the training backpropagation. That is why we expect that we see that the model is exposed to the domain shift during backpropagation, and that is supposed to create a model that has learned to handle domain shifts during training. Does that make sense?
I got it. So then maybe quick follow up. If that is the case, why not like something like contrastive learning wouldn't work as well, where you try to close the gap with contrastive learning with a single model? Would it be a competitor of this model?
Yes, you mean to close the domain gap between the modalities? Yeah, but I think this approach is a more modality agnostic, let's say, so that it doesn't specifically close the domain between the specific source modalities that are used, but it kind of does a modality agnostic generalization, let's say.
I see.
Okay.
I have a quick question as well. Can you please go to the results slide?
Yeah.
Slide right before.
Yeah.
So I was a bit wondering why, I mean, definitely, I think we can say from the appearance that the thermal infrared is far different than near and or RGB.
Yeah.
But from numbers here, we can see that comparing these two, I would expect that it's much easier to have near as a target domain or modality with these source modalities compared to this one. So we can see in the MAP is much better here. So you can see this difference that I just mentioned in the numbers, but we cannot see it. And it is the rank 1 accuracy, right? So,
yes.
So we cannot see it here. Do you have an idea what's the reason behind that?
Well, rank 1, as you probably know, it measures the ability of the model to get the first correct, but MAP is a more robust metric. So it measures the ability of the model to classify as many true positives as possible. So we can say that MAP is a more robust way to evaluate the model.
I was asking because since this is more like this is an image retrieval problem, like you format it. And rank 1 is more intuitive to me as a measure to perform to measure the performance of an image retrieval more than MAP. But that's why I was wondering, like, okay, you use MAP here. I understand that with MAP we can see the difference between these, let's say, between the difficulty of transferring these modalities. But I was, as I mentioned, I was wondering because why is the rank 1? So is the statement like, I mean, I don't know if this generalizes, but is the statement that rank 1 might not be the best way to measure image retrieval, or just in a specific case?
Yes, especially when there are more than one true positives in the gallery set. It is either better to use more than rank 1, like rank 1, rank 5, rank 10, etc., or to use MAP that evaluates how all the true positives are closer to the top of the sorted list. And so, for example, if there is a correct rank 1 at the top of the sorting list, but the rest of the true positives are at the end of the gallery set list, that will be caught by MAP.
Right.
Does that make sense?
I agree. Thank you.
Okay.
So
Thank you.
Again. Okay, so we continue with the talk number 4. I don't remember what's that, so I have to have a quick look. So it's Vasim. Vasim, are you with us in the Zoom meeting?
Yes, I am.
Perfect. I stop screen sharing and you can start sharing your screen at your earliest convenience.
Perfect. Can everyone see my screen?
Yes, we can. So feel free to start.
Awesome. Thank you so much. Hello, everyone. Thank you for taking the time to attend my presentation today. I'm going to be presenting our latest work on enhanced thermal RGB fusion for robust object detection. So the motivation of our work is that for real-world applications, it is necessary to utilize sensors that operate in different spectrums to accommodate for varying lighting and weather conditions. So fusing information from multiple sensor modalities can be expected to mitigate the limitations of each sensor This meaning that we don't have anything called as a perfect sensor. Each sensor will operate differently. It will have its own advantages and disadvantages under certain conditions. So speaking a bit more about thermal sensors, they're becoming more popular to use in machine vision applications. They're suitable for outdoor applications as they are not drastically affected by environmental conditions as color cameras, for example. And they're also becoming cheaper to mass produce. And in this image that we have here on the side, we have a color image and corresponding thermal image taken at night. And as you can see, the thermal image is way less prone to lighting effects. Like as you can see in this vehicle, for example, the pedestrian right across of it is barely visible in the color camera, but in the thermal image, they're very clear. The pedestrians over here are almost non-visible at all in the color camera and the color image, but in the thermal image, they're much clearer. And also the vehicles are much clearer in the thermal camera because it is much less prone to strong lighting than color images. So what we're trying to do is we are trying to study the efficacy of sensor fusion for object detection, as object detection is frequently a pre-processing step for most state-of-the-art tracking algorithms. So tracking algorithms that utilize the tracking by detection paradigm, where we first run images through a detector, get the bounding boxes, and then conduct box association to map tracklets across different frames. For that reason, we focus on improving the performance of detectors by utilizing sensor fusion. So most of the challenges we face in object tracking is that occlusion, which can lead to tracklet breaking, making it difficult to recover a tracklet. And then the quality of the tracker will heavily depend on the reliability of the detector, which is one of the main motivations of our work. We want to improve the performance of object detection models by utilizing sensor fusion. Because if we miss only one detection in one frame, this can potentially break a tracklet. So the contributions of our paper are can be summarized in three terms. First, improve a previous data set by registering the RGB and thermal images. So we take a data set of thermal and RGB images. We conduct work to register the images, making it suitable for sensor fusion research. And then we compare the performance of object detectors using different backbones with and without the utilization of existing fusion operations. And finally, we introduce a novel fusion approach for RGB and thermal images. So the first step, going over the data registration process, we see here a sample from the data set where we have a color image and the corresponding thermal image. As you can see, the two cameras are of different resolutions, different fields of view. Like if you want to take an example to understand the difference, take a look at the tree. It is much larger and in a different position than in the thermal image. So the first thing that we do is we run an orb feature, an orb key point detector to detect the key points in both images. And then we use a brute force measure to match the top 10% key points between the two images. Once we have matched those key points, we use RANSAC to calculate the homography matrix between the two images. Now, since this was a fixed camera setup, finding the homography between two frames can then be applicable to all of the dataset images because the sensors are fixed and it's a fixed capturing mechanism. After that, after we apply the transformation, now you can see that the thermal and RGB images are quite aligned. And then those annotations that you see here are shared across one annotation file. So the annotation file for thermal images is now fully applicable to the RGB images. And at this point, we can now conduct sensor fusion research. So what we do is we train and evaluate one of the state-of-the-art object detectors, task-oriented object detection tool with two different backbones, ResNet 50 and ConvNext, and we compare the performance of the object detector on this new dataset utilizing different already existing fusion operators. So some of them are arithmetic fusion operators like addition and multiplication, and then learnable fusion, which are MFB and BGF. As we can see, sensor fusion, obviously, as expected for the most part, they do increase the average precision of object detection models. And then we introduce a new fusion operation, which we call enhanced sigmoid gating. So this novel gating mechanism is designed to learn the significance of each modality on a per pixel basis before performing the multimodal fusion operation. And then with our approach, the best performing models achieves average precision of 79.8%, a 4.4% increase over existing fusion operators. And this diagram here shows a summary of our suggested approach. Basically, here is the input image. So before we apply any feature extraction for any fusion, each modality goes through a one-by-one convolution with sigmoid activation, which will then hopefully learn the probability or the significance of each pixel in the image. Then this probability matrix, where we're assigning a probability for every pixel in the input modality, is multiplied by the pixel values of the original input image. And then this will hopefully diminish the values of irrelevant pixels and amplify the values of significant pixels. We do this for both modalities. And then the resulting feature map can then be fused. The resulting feature maps can then be fused using any other existing fusion operation. And this is one of the most powerful features of this approach that we're suggesting, is that it is a step that could be applied in conjunction with any other fusion operation that already exists, whether arithmetic or learnable. Then after this fusion, the tensor goes for normal feature extraction, and and then for object detection accordingly. So those are the results of our approach after, with and without our suggested sigmoid gating. And as we can see, we do show a decent improvement on existing fusion operations, so without sigmoid gates that we're suggesting and with sigmoid gates that we're suggesting. And that concludes my presentation. More questions?
Thank you, Vasim. Do we have questions? I think you were first.
So I think the baseline is without any.
You cannot hear us, right?
Just
Yes, I think you have to come closer.
So I think one important baseline is without any fusion operation, just apply your detector to the visual image or thermal image and compare with the fused result, which is better. So that convinces me the fusion works in your application. Do you have such evidence tonight?
So that really depends. So in a previous paper that we've done, we've highlighted the advantages and disadvantages of each modality on its own. So obviously, thermal is going to do well at night. RGB isn't going to do well at night. However, thermal will struggle in cases where there is little variance between foreground and background, or in cases where there is some areas of the image where there's shade and other images where there isn't enough shade, where you have sometimes direct sunlight hitting the state, but other parts are shady. So the baseline is thermal alone and RGB alone, but then thermal on its own might perform better under certain circumstances, and RGB alone might perform well under circumstances. What we're reporting is the average performance on the entire data set captured at different times of the day under different weather conditions as well.
Okay, I think that's okay. But if you have the data baseline also listed in your table, that the information will be complete.
I couldn't hear the second part of your question.
I mean, if you have the results from your individual image modality, let's say visible and the thermal in table as well, so that will help us to understand your solution better.
Yes, we do have those results in the table. Let me just share my screen again.
Okay, thank you. Yeah, we have the kind of other.
So this is RGB alone, and then this is thermal alone.
Okay. Thank you, Vasim. There was one more question. I think it was, again, you have to figure out who it was. You're kind of competing.
So I was thinking that Convex was a better backbone than ResNet. And yet in your result, you have better result dwells better with SNet. So how do you explain why SNet is better than Complex?
So I believe that the main reason why this is the case is because we didn't make any changes to the detection head of TOOD. So in the original implementation of TOOD, the detector was designed with the feature extractor of ResNet 50. So all of the hyperparameters for the detector are optimized for ResNet 50. We didn't optimize them more for Convex. We just changed the feature extractor. We didn't attempt to make any changes to the detection head. However, that isn't necessarily always the case. Like we see, for example, that TOOD with ConvNext performs better when using MFB, which is a learnable fusion operation. It performs better than ResNet 50 with that fusion. But generally, you're right that ResNet seems to perform better than ConvNext, and I believe the main reason is that we didn't attempt to configure TOOD for optimal performance with ConvNext.
Thank you.
Thank you, Wasim. A quick one, Erhan.
So, for the learned weights,
can you go to the mic? I think you cannot understand your advice.
So you're learning these fusion weights. Quick question is like, are they context aware? Like, are they making this learning these weights based on the other neighboring pixels? And the other question is more like an abstract question, like, do you have any insights, like in what conditions it gives more weight to infrared one versus RGB one? Is it like when one of them is sharper, it's getting more weight, for example? Do you have that insights?
So that's actually a very good question. The learned weights for the fusion and the sigmoid gating is per pixel. So it doesn't utilize information from surrounding pixels. However, that's a very good point. It would make much more sense if it is taking into consideration neighboring pixels to learn the probability of a specific pixel or the importance of a specific pixel. As for your second question, it also doesn't do that. What it does is each input modality goes through this weight learning process absolutely independently. So there isn't this correlation between the probability learning from one modality and the other. However, through this research, one of the main things we learned is that specifically with early fusion, there isn't any stage where you reach where you say, okay, now this is the optimal solution. You can technically keep on coming up with different combinations of operations that you can do for fusion, and then you will just keep on improving and improving. So there's theoretically infinite number of fusion experiments that you can do. So the question of when do you reach the optimal state or the final solution, that really depends on the task that you're trying to solve. What good is good enough is task dependent, I believe, in this case.
Okay, thanks.
Yeah, but so I was thinking about the same thing, like if we could somehow visualize the features that get highlighted by these probabilities. I mean, we saw the numbers, but yes, but it's also very interesting also to see like if we can get some kind of idea what kind of properties, of image properties are highlighted by these probabilities. And
I
also
think the idea of generating a saliency map of or the heat map of what pixels are being amplified with this.
Right. Exactly. And I was also wondering why we do it on pixel level, because pixel level is quite raw, and it might be also interesting to test that for if we start convolving, to like do it with these early stages of convolution to understand if convolving the image helps us to get some more meaningful probabilities for neighboring pixels or something like that.
One idea that I've been thinking about and discussed with some colleagues is, as we do neural architecture search, because we don't really know, or if you have the enough resources, then you can have a learned architecture of your model. I believe a similar solution can be made for fusion operators, like learnable fusion architecture, which will conduct as much experiments as you want to find for this camera setup, for this application, what is the best fusion workflow to achieve the best results.
Good. Okay, Wasim, thank you very much. We're gonna head on.
Yeah, thank you.
Thank you again.
So let's keep the fingers crossed that now sharing will not force Zoom to crash again. We are now at talk number 5. This one's yours, right?
Yes.
Perfect. So let's see if it will work. We have to go to this view. And it's working, it seems. So let me minimize that and let me give you a pointer. And we are good to go.
Okay, well, thank you. My name is Guillaume Alexandre Bilodeau. This is a joint work with Noreen Anwar, Philippe Duplessis-Guindon, and Wassim Bouachi. So what we want to do in this work is given a stereo pair where we have one thermal infrared image and one visible image. And given detection of humans, we want to register the corresponding human silhouettes that are detected. So if we are able to do that, well, this allows us to do a fusion operation like we've seen in the talk before. And since we have a stereo pair, we can also estimate depth. So we work on this topic before, and actually we presented some earlier version of this at this workshop. So basically, to solve this task, what we're doing is that we are matching patches. So we sample patches on the persons, and we match them between the two modality. So we have basically it's a two-stream network where one extract features in thermal infrared, and the other extract the feature in the color stream, and then we can combine the two streams together to predict the disparity. So it's the translation between, so we rectify our images after calibration, and we can estimate depth by computing the for matching points, their distance in the x-axis. So by doing this, we got good results, but we noticed that close to the boundary, the precision of the disparity were not very good. So we decided to explore two possible ways to improve our result. So the first way that was published on arXiv was to use an instance mask. So basically what we have normally is some kind of bounding box around the silhouette, and we just match pixels inside this bounding box. So what if we use a segmentation mask? We hope that it would improve, and it did. It improved a little, but not as much as we would like. So what we're presenting is this paper is that to see if we use high resolution feature, can we improve significantly our results? So by high resolution feature, we mean that we use a neural network, so a backbone that keep high resolution feature at every stages. You will see in the next slide how HRNet looks like. So this is our global architecture. So we have two streams, RGB stream and the thermal infrared stream. For both stream, we extract, so we have patches that we want to compare to see if they're similar or not. If they're similar, so we have the spot where we have identified the translation and the disparity. So we have the two patches and both modality, they go through the backbone. So this gives us feature map for the infrared, feature map for the color image. And after that, we use a two branch to find the disparity. In the first branch, we do the correlation between the two feature maps. So we get the correlation volume, and the peak in those correlation volume is where we have our disparity. So the highest similarity. And in the second branch, we just do the concatenation of the features. And we use a fully connected network to classify and find the disparity. So both correlation and concatenation have their advantages. So we do both and combine the results. So HRNet, it's a network that looks like this. So you have here we have 3 stages. At every stages, lower resolution feature are added. So you can see here that we added lower resolution feature. At the third stage, we do the same. And between each stage, there is the information is combined between the various stage. So now the question was, how do we use this information coming from HRNet? So the first possibility in A, it's to use just a feature that come from the last stage. So we need to upsample them to put them all together. And this is what we use to represent the information. And the other possibility that you see in B here, it's to concentrate only on high resolution feature. So take the one from the last stage and the feature from the previous stage. So to test our proposed network, well, we tested on 2 data sets. We use a HRNet that is pre-trained on segmentation task on image depth. And the result that you see, it's well, actually what we have, we need to find correspondence between pixels in both modality. And what the result that we have is the percentage of good correspondence with an error of 1 pixel, with an error of 3 pixels, and with an error of 5 pixels. So it's harder to get an error of 1 pixel because you have to be more precise in your disparity evaluation. In 5 pixels, it's much easier. So our baseline is this first one. So this were the result that we had previously. And by using the high resolution features, we have been able to improve very significantly the result with both ways, by combining scale and also combining stages. In that line here, we have the other word that I talked about, where we use instance mask. So for instance mask, it improved a little, but not that much. We tried to combine both. So we didn't present this in the paper because it was not really conclusive. So we tried to use instance mask and high resolution feature, but it did not really improve. So just having high resolution features were enough. So on both data sets on which we tested, we got similar conclusion. If we go a little more in depth in the results, so we compare the 2 ways to combine the information from HRNet. So at scales and with stages. So in general, combining information from 2 stages is better than combining the information from several scales. We believe it's because with the stage, we only use high resolution feature, while in the other case, you have to do an upsampling to combine the features. So maybe it's a little less efficient. Okay, the results are kind of very similar. And we also tested using only the various stage. So this is shallower in the network. This is deeper in the network. And the last layer give better results. So that's why we combine the 2 last layers. So in conclusion, our experiment have shown that using high resolution features is really useful for our tasks. So when we take information from the thermal and the color from the color spectrum, having better feature that have more detail allows really to get better disparity. And also it seems that combining feature at various stages is better than at various scale. And finally, it seems that if you have a very good feature extractor, extracting segmentation mask is not that useful. And the thing is that it's more difficult to extract also a segmentation mask in the thermal, because as a lot of people have said, there's not that many data set with thermal segmentation. So you need to use a mask RCNN trained on color image, so you get approximate result in the thermal. So our code is available, and that's it. If you have questions.
Yes, yeah. Yeah, quick question. So we need high res feature because thermal are low res enough. Is this the reason? For instance, if I apply
this high-res feature to just RGB stereo, not RGB and thermal stereo? Would I get similar results?
I think it's always better. HRNet was better because, well, they compare on various tasks, object detection, segmentation. It's better because you have features that are finer grained, so you can really get more details from your original image.
So these extra details, where they come from?
It's that you don't downsample your features. But that's the thing, by downsampling your features at different stage, you kind of do more abstractions. I guess it's good for image classification, but when you want to precisely match two things, I guess it's better to keep more information than removing residual information to be more general.
I wonder if you already tried that for just a single modality.
No, honestly, no, I don't.
Because
When I do stereo, it's always with two modalities.
to be with actually.
Yeah. Yeah, if we want to really see if it works in all situations. Yeah.
I think there was a new data set published, I think from KAIST, where they have the stereo camera system for visual optical and for thermal infrared. This might be a good data set to have a try on that maybe. I think it should be published this CVPR. So
okay.
If I remember correctly.
Yeah. One quick comment. The reason why instance mask is not helping could be, is it possible that it's because of the instance mask is not that precise, like maybe it's not within the 5 pixel range accurate, then it doesn't matter. That could be maybe one reason.
This is what we think. Also, maybe the way that we use it, we did not explore. We kind of concatenate the mask with the image data. Maybe if we inject the information, like some kind of prompting somewhere, let's there's a tutorial I think on prompting computer vision tomorrow, so maybe there's some way to do that.
The other thing is about architecture. I didn't see the detail, but have you considered or used cross attention, or it's just a correlation there?
We wanted to do that, but it's a master student. He had to finish his master, so it's upcoming work.
When we question from me, because when I saw the slide, I was a bit confused because we were talking here about this branch that does the correlation, but having a look at these patches, they are maximally uncorrelated because they're so different. But do we like assume that in this latent feature space that we have, we do a correlation on the feature and then they are correlated? This is the assumption.
Well, the network has to learn features that, when they're correlated together, correspond to
so with
what
branch, it's more enforce the latent feature space to be correlated.
Yes, this is what you would do.
Okay, thank you.
Just a quick question. Did you try this in other auction? Because this is for silhouettes. But did you try man-made structures, something like that, or not yet?
I think it could be anything that
No, I think it would be better, I think, because
we focus on human because human are the most important thing. I don't know, but theoretically it could work with anything if we can detect it. If it has a thermal signature that can, it's visible in both modalities.
Okay, so thank the speaker again. Okay, so just plug your USB stick and we will do it right from the USB stick to presentation. This I really hope it will work out. So which one is the corner? This one. Yes. So just double click. So you are Carl? Yes. Okay. So you will present the next set of slides. We have to try again to convince Zoom that it will not crash. It seems to work, I guess. Okay, so yeah, cool. So feel free to start.
Thank you. Hello, everyone. I'm Yue from the University of British Columbia, and today I would like to introduce our paper, Multimodal Object Detection by Channel Switching and Spatial Attention. So first, I would like to quickly go through the background and objective of this research. So as we know, different sensors can provide the information of an object from different perspectives, and some of sensors are complementary. For example, RGB cameras can obtain color and texture details when the light is sufficient. And IR cameras, on the other hand, can ensure the contour of the object can be obtained when the light condition is bad. So the image on the slide shows the complementarity of these two sensors. So the object in the bounding boxes, meaning that in the current modality, it can provide more information about this object than the others. So the objective of this research is to fuse the complementary information from different modalities to improve the accuracy and stability of the object detection model. So to accomplish this task, we adapted a classic object detection framework called FastRCNN, which includes two ResNet model as the feature extractor for IR and RGB image, and FPN feature pyramid network, which allow the model to learn the object from different scales. And finally, object detector to detect the object from the feature maps. On top of that, we propose CISA, a plug-and-play multimodal fusion module, which can fuse the RGB and IR model from both channel and spatial perspectives. Because in the framework, we have two backbone models, which will introduce extra computational overhead. So we did decide to design the CISA model to be a lightweight fusion model. So it can effectively improve the performance of object detection without compromising the efficiency of the detection model. So next, I want to introduce the details of the CISA module. So CISA actually contains two parts, channel switching, which refers to CS, and spatial attention that refers to SA. And channel switching is a lightweight operation that allows efficient and effective feature interaction across modalities. So the detail structure is on slide. We can see the model will take outputs from the two backbones and feed them into ECA blocks, which will compute the weight of each channel in the feature maps. And the channel switching will be performed based on these weights. So when a weight of a channel is lower than a threshold, it's meaning that it is less important for the final detection results. So the model will replace it with the corresponding channel from another modality. So in this process, the model will like enhance the weak features using the information from another modality. Well, it can also maintain the strong features exclusive to each modality. And the output of this step will be fed into next process, spatial attention. So spatial attention is a parameter-free process that can provide intermodality attention from spatial perspective. So it serves like a complementary for the channel switching. And in this step, the model will highlight the important location of the feature maps. And the model will take the output from the last step and concatenate them on a channel dimension. And then both average and max pooling operation will be performed on the channel dimension as well to generate an attention map. And the sigma sign here, meaning the sigma function that will map the attention map into the percentage. So we change it, we map them to the score. And we multiply them with the concatenated feature maps to generate a weighted feature maps. And finally, we will split them to RGB and IR and add them to get the final output. So as the only operation in this step are the pooling operations. So it won't bring any extra learnable parameters. So will not introduce any computational overhead for the detection model. And next, I want to show some qualitative results of our model. So the first two columns are the output from IR and RGB, like a regular FastRCNN, and the last one is our model. The blue and yellow green bounding box, meaning the car, person, and bicycle objects detected by the model, and the red bounding box, meaning the error case. So either false positive or false negative. And on the first row, we can clearly see that our model can use the complementary information from both IR and RGB. As in the IR, as the contour information is not clear, so it didn't recognize the bicycle object. But in RGB, as the light is sufficient, so they provide a lot of color and texture detail. So the bicycle object is successfully detected by the detector, and same as our model, as it can use the information from RGB. And the second row, we can see as the scenario is in the nighttime, so the accuracy of the RGB detector is significantly dropped, but our model can still use the information from IR, so keep the accuracy of the detection results. And other than that, we also evaluate the models on a quantitative way on two public data sets, FLIR and VIP. So we use focal evaluation metrics to evaluate the average position of the models. And based on the result, we can conclude that our model can actually use the complementary information from IR and RGB, as it outperforms those two single modality models. And compared to the multimodal detectors, our model also get the best results, as our model is the only one that considers the information from both channel and spatial level. And finally, we also evaluate the memory usage and inference time, because it is really important for the multimodal detectors, as usually it will consider more information than the single modality one. And our model gets the lowest memory usage compared to all the multimodal detectors. And compared to the regular fast RCN, our model have around 600 megabytes memory usage overhead. It mainly comes from the extra backbone for the IR inputs. And for the inference time, our model requires slightly more times than the ProbN and faster RCN. It's around 8 milliseconds, but it is acceptable time if we consider the overall performance, include memory usage and accuracy improvements. And also 31 milliseconds per frame is acceptable for most of time critical tasks. And that's all of this presentation. Thank you.
Okay, please.
Will your framework work for like SSD network?
For what?
Like a SSD type of network?
No, I didn't test it on that type of network.
Okay, can you go one slide back?
Mhm.
Are these methods that you compared your approach with, are they also based on faster RCN?
Yes, I implement them every algorithm on fast RCN and in the same library, so it's a fair comparison.
Okay, cool.
Yes. Mhm.
Great to hear that.
Yeah.
Yes, please.
Are you assuming that RGB and IR both have the same field of view and pixel matching?
Yes, they are registered.
So you have that assumption there.
Yes.
And when you selected your faster or CNN, if we change it to other models,
yeah, it should be.
So that should.
Yeah, it should. Yeah, theoretically it should be work, because the mean contribution of this work is the fusion module. So it's a plug and play model. So you can apply it in any other frameworks. Yeah.
Yeah. So this is really nice work, which I think also can be applied to a more difficult problem. Like imagine you don't have the RGB part, but you train with RGB and IR, and then have you ever tested the framework and you don't have the one of them?
Actually, we didn't test it on this case, but yeah, it's a good suggestion. Yeah. Yes.
Switching is somehow helping during the training. What
Yes.
to use, what not to use, and how to program, etc. So
Yeah. That's true. Yeah.
can you go back one slide?
Yes.
One more.
Okay.
Yeah. So on this result, the first row,
yes,
actually from both IR and RGB, there's one part detected at the far end.
Yes.
In the in your method, it's
Yeah, actually, that is a false positive case. Yeah, actually, that is an I guess I also see this problem, and I double check it as that's is not a car object. Yeah, it's not a car, but it's looks like it's a bus actually. But the only category here are the small car. Yeah. So
there's like a blue and a red box here, right?
yeah. So this is the false negative, false positive. So.
But with the blue and the red one, I thought that you have only like
Oh
red
yes,
one in the
yes. The red one is I apply it after the detection results. Based on the wrong choose. So I overlap.
Oh,
Yeah,
got you. Okay,
yeah,
I see.
yeah.
So the blue indicates that there was a detection, but the red one says that it's a wrong.
Yes.
Okay, got you. Thank you.
Okay.
Yeah, one more question. So the idea of the channel switching is very interesting. Can you briefly talk about the strategy, how you switch those channels?
So basically, I will evaluate like the importance of each channel. So when the channel is lower than like we will define threshold based on like the experiments. And when the weight of a channel is lower than the threshold, we will replace it with the information of another modalities. Yeah.
So you switch it, I mean, you replace it, but the original one, you just dump it or you?
Yeah, dump it. Yes.
Yeah. Thank you. And last follow up on that. So why not like replacing thresholding with percentage based one? Like, would it work or would it be more vulnerable? Like for example, percentage, like just remove 10%. Weights.
There is a problem of the percentage strategy, as sometimes if the information is like when we want to mix two like information together, sometimes it will cause a negative effect. So we choose the simplest strategy, just dump it and use the better one. Yeah.
Okay, let's thank the speaker again.
Quickly eject this USB stick. Yeah, you may want to take it. Give me a second to close everything. I guess you should be good to go. Okay, so we have one last paper to go. It's yours. Okay, great. So did we already transfer the slides? I don't remember. We didn't, it seems. Do you have like a USB stick with you or with the slides?
I copied onto your USB.
Did we?
Yeah, I borrowed somebody's. Yeah, I think it's
this one.
Yeah, this one.
Okay. Is it this one?
Yeah, this one.
Oh, okay. Now I remember. Okay, cool.
Okay.
So
we're good to go.
I think that we have to go to the presentation mode. Oh man, I need some Spanish guy here.
Okay.
It's international control.
I see. I'm not aware of this topic. Sorry for that. But okay, we're good to go. Yes.
Yeah. Okay. Yeah, I'm the last one in front of your dinner, so I'll be quick. Yeah. So this work is joined with University of Maryland and Air Force Academy, where they host my summer visit for the last 6 summer. So I'm very grateful to that. So our work is on this object recognition, classification challenge. So the main trick is really this label splitting. So the original semantic label is only 10, right? And they're very unbalanced, and some are over representing and this and that. We basically, the key trick to this is to expand the label space to 2-dimensional, and then we'll be able to learn that. So, the problem, the key problems, there are solutions, results, and future work, this and that, as usual. Yeah, so for this audience, I think it's pretty obvious, right? The problem is very low resolution image from SAR and from electro-optical sensors. We want to do the classification. We have like 10 classes, And I mean, it's a very challenging problem, even for human eyes, right? It's very difficult to see. So fortunately for us, I mean, our framework works out pretty fine. I think our top line accuracy is ranked #2 for track 1 SLR, and the #3 for the track 2 EO plus SR. I think per presentation this morning, it's #3 overall, and we are the #1 US team. So last year, I think we were the top US team as well. I mean, we were #10. But we were very embarrassing. Like out of those top 10, like 8 from China, right? So I was talking to our program officer, this and that. It was very embarrassing. So anyway, yeah. So the problem itself is illustrated by this data set. I mean, one comment I want to make is to make the SAR image like give us a complex signal, the original complex signal, because the face can be very useful in this type of work. So I understand. I mean, it's processed from complex signal, right? We only have a magnitude, but it will be very interesting if we can somehow utilize face information. So the key challenge is, the signal quality resolution, and the pixels are not registered. In our opinion, is not precisely registered. Right? They have some sort of discrepancy, and also this extremely unbalanced kind of training samples. And of course, I mean, coming with this problem, there's quite a bit of unpleasant intra-class kind of variation. So the other data set we worked on was like a aerial image, kind of RGB image classifications, like a 45 class from Northwestern kind of Polytech. So that one is also having the same problem. Somehow we solve those two actually with the same framework. So the key solution is it's two parts. One is the data set augmentation. So I mean, that's pretty standard. We just do all this flipping and then affine transform. So it's like you have some random affine projection of the imagery itself. So this way we enhance the images to like a 10 per each original one. And also we have a very sort of brutal and rude kind of a way of balancing the data set. We just randomly sample 6,000 from each one. So this way, more or less, we have a balanced data set. So I think that one trick really works here is this random affine transform. So we apply a random affine transform on those imagery samples. So somehow you enrich the data set. And then the learning itself is really this kind of label splitting idea. So I will explain this. So it was actually kind of from the previous research program of error image classification, right? Say if your semantic label is airfield, right? But airfield in Arizona versus airfield in, say, Alabama, it looks very different, right? So in Arizona, they're like a reddish kind of background with the stripe, right? And in Alabama, it's mostly green, right? So if you force them to use the same semantic label, right? You could imagine, I mean, the network will have a hard time to find a feature embedding which can properly separate them. So the key kind of motivation here is why not just give them a supervised label, right? So give them an appearance label. So how do we derive an appearance label to the imagery? So we use a pre-trained VGG network, right? And then we come up with embedding. And from this embedding, right, we just do dimension reduction and then give them a KD tree. KD tree partition. So here it's like just a realization. So if you just do 2 dimension, right, you partition. Each leaf node is just naturally an appearance label to your image data set. So with this trick, right, you can actually look at this. So for example, in this particular challenge, we build a KD tree of 128 leaf nodes, right? Steps of 7. So if you look at all those appearance label, right, and there's a associated semantic label, associated with them, it's some very interesting behavior. Because on the one hand, right, you have 128 appearance label, on the other you have 10 semantic label, right? There's a Cartesian kind of a product, right? A lot of them actually has no data samples there, but by doing this way, right, we basically kind of expanded the original problem from a 1-dimensional kind of label space to 2-dimensional, and this kind of greatly kind of enriched our kind of granularity of kind of classification. So anyway, so this 128 cross 10 semantic label roughly resulted in like 800 kind of unique labels for the problem. So of course, then we do the learning, right? So with like 800 kind of labels, I mean, just do a softmax. It's not very effective. So what we do is we use softmax to basically initialize the network weights. So the stage one pre-training use softmax to get some strong convergence. And then we sort of replace with like a triplet loss. So I mean, triplet loss is very well understood in this world. But the trick here is how do you make the triplet of a high quality, right? So the intuition here is you want those positive pairs to look different, right? Because if two sort of cars they're already similar to each other, probably the softmax stage already learned that in the network, right? So here the strategy is you need to find out those very easy to mix up kind of pairs, right? So with the help of this appearance kind of splitting, we have a very natural way of doing that, right? So whenever you sample anchor, right, as then you choose those positive pairs such that they don't have common appearance label, right? So this way you make them sort of hard positive pairs, right? And then for the negative pairs, I mean, you do the other way around, right? So you always look at the samples which they have the same appearance label with respect to your anchor, right? So this way you make sure they are harder, right? So and there are several combinations. So by building this appearance, the KD tree of different depths, this and that, right? You can control that. So all this kind of together gets into a kind of a triplet mining strategy. So how do you choose the best way, right? And also there's quite a bit of trick in training the triplet loss, because even the same ideas, I mean, different students they get different results. So credit to Regulus and my other student Zijun, they put in a lot of effort. They figure out a way, a training strategy actually get the best out of this network. So anyway, I mean, this is a very clumsy kind of illustration. It basically says that the same network, we have multiple stages of training, softmax for initial convergence, and then sort of triplet mining to get the best out of the network. So as far as backbone is concerned, we didn't do anything fancy about the backbone. We just use whatever is out there. So I think the final table will show that. So we use the ResNet 34 EfficientNet B0 swing T several combination. And then out of this, I think the best performing one is a ResNet 34, and EfficientNet is not that bad either. And the inference time is pretty manageable. It's like a 0.02 second on CPU machine on desktop. So overall, I think it's a very useful kind of solution. So for track 1 SR, I mean, we are like a second in the top accuracy. For track 2, we are number 3, and that's pretty much where we stand. So I think what's more interesting for us is I mean, so in summary, the contribution is really kind of a data augmentation by affine random affine projection, right? I think that's probably something kind of more interesting. And the training strategy, I mean, the learning framework is expand your label space to 2 dimensions, right? And then you have a training strategy of softmax plus like triplet loss with, I mean, a lot of tricks of manipulating those regularizers. And also the triplet mining itself is quite an art. So the intuition is very clear, right? You want those positive pairs to be hard. You want those negative pairs to be easy to confuse, right? So this way kind of network works out pretty good. So for future work, I think our future pipeline as it stands now is very kind of naive. So from another work, we have a very good pipeline. So it's like a joint frequency domain and a pixel domain learning. That one is really kind of, I mean, new state of art in those deep blocking, in those pixel level kind of task. So we improve our feature pipeline by exploiting that. And also kind of, I think probably more interesting for the research community is for this problem, right? Under image degradation and the compression conditions, right? How far you can push that. So we have a project with the Air Force Lab kind of a compression team. They're very interested in that. There's of very, I mean, it's of great practical value, right? Because all the sensor you deploy is very easy and cheap, but eventually you need to aggregate this information back, right? The aggregation process involves compression and communication. That by itself also introduces kind of degradation. So I mean, that's kind of very much the work. Okay, thank you guys.
Thank you, Zoo.
Oh, thank you.
Do we have questions? Yes,
oh,
please.
go ahead.
For the, again, I ask a question about backwards. So, swing, it seems, well, theoretically, I guess it should perform well. Is it it's not performing well? Is it because the data set is too small, or do you have to use a smaller?
Yeah, partially because the training strategy part, the actual training part make a huge difference, right? So maybe a different student, he spend more time tweaking on certain network, right? It works out better. But overall for this program, I think that all this network is a bit overkilling. So we replace that with a much lighter, simpler kind of network, as I mentioned, like a joint frequency domain and pixel domain kind of pipeline. We have that for deblocking. I mean, the video compression community is very sensitive with complexity. So that network is much lighter than this three.
More questions? Yes, please.
Okay.
Hey, Poppy, I have a question. If you think true, do you have any special, because last about 20 years ago, it's very hot for high dimensional impact, like X-ray, K-ray, many. So do you have any?
And it's for computational kind of convenience, because we have a multi-scale appearance label splitting, right? So for the data set, we can have like 128, 256, 512 appearance labeling. So you could do like a k-means, this and that, right? I mean, at a different level. But in a way, for the convenience of computational solution, we choose KD3. There's no other kind of specific reason. But when we realize, and when we realize that, it seems like to make sense as well. I mean, otherwise we could use like a TSNE, this and that, right? I mean, have a lower embedding, and then whatever number of appearance model you could choose. I mean, of course, that would be faster, but in the end, actually, the performance more or less the same. Because initially, what we found, well, what we were doing is just do TSNE, right? I mean, you have an embedding, and then you do a k-means. So this is your appearance label. I mean, supposedly that's better than this PCA plus KD3, right? But actually, in the end, not much difference. So for the ease of implementation, we use this one. Yeah.
All right, so let's take this feature again.
Oh, thank you, guys.
Yeah. Okay. All right, and it seems we made it finally. I thought that last year's workshop was quite challenging with the technical setup. This year it was even more difficult, as we realized all. So sorry for the delays that the technical issues that we had at the beginning of the workshop caused, especially to the first speakers. So yeah, this basically ends the program of the workshop. Before we all go for dinner, I want to ask Riyad to give us some concluding remarks, some comments, and yeah, he's the general chair, so it's about him to finish the workshop here.
Thank you, Michael. I think you did a great job. So let's give a round of applause for Michael. So I have to say one thing, that although it's one-day workshop, but really it actually takes a lot of effort to come up with a solid program like the one that you witnessed today. So I want to also thank other folks actually who helped all year basically to come up with the program. Our publication chair, Dr. E. So please give him a round of applause. So he made it the last minute because his flight got canceled, so he has to drive. For how many hours you drove? How many how many hours you drove?
Well,
5 hours.
the border took me a while.
Just to pass the border. Okay. Yeah, I also want to thank actually the program co-chair Irhan, who asked a lot of good questions. I hope we will benefit from his questions as well. So let's give him another applaud of applause. Finally, our challenging chair, Professor Angle, he, it's not easy to, as you know, it's not easy to organize challenges, and it takes a lot of effort, a lot of coordinations, set up. So he worked with his student. He put many hours, to make the challenge smooth and respond to all the requests from those who submitted. In total, how many submissions do we have? Like these 3 challenges, like 400. Yeah, and in the back, right? Yeah. So please give both of them a round of applause. Also, I want to thank actually all the authors who made it actually to in person, in particular, who gave nice talks, who made actually this really a very nice day for us to learn new things. And on the topic of challenges, so I want to actually get some feedback from the audience. What's your thought actually regarding these challenges? Sean, like, do you have, for instance, a new idea for a challenge for next year? I think I talked to a few folks. If you have ideas, you can definitely share your thoughts actually with us. Send us an email and propose a new challenge. And also, but however, the feedback I would like to get, we have, for instance, a challenge on super rest thermal imagery, and I wonder if people see this is a nice challenge to continue investing effort, or should we drop it and maybe switch to a different type of challenge? If you have any feedback or comments, please share it with us here. So do you think this is useful? Like, I want to come back to your stereo approach, right? You have a thermal and you have a RGB, right? And with the network you can do right, super res. So what's your thought about this? Yeah. So you think we still continue? We need to continue for next year? Okay.
Yeah, because there's so much. The thermal camera is very expensive. You want to have high resolution, so if you can add details like this.
Okay.
Food detection, tracking, and activity recognition, any application.
It sounds good. Sounds good. Yes, please.
We are thinking for next year. We've not yet decided to put some application, because super resolution is an image processing, but maybe some application, some option detection, that could be also more attractive. But it's something that we try in mind, not yet decided.
So do you plan to have like a special journal, on the topic, or?
No, because next year we have 20 years of this work.
Right.
That's what I want to see. That's 10 years anniversary. Let's make something unique.
Yeah, this is the oldest workshop of computer, I see.
Okay.
So
now other workshops can take such a long period.
Yeah, I also want to say actually that organizing a special issue for a journal, we've done this actually with the top journals in the past, IGCV, CVIU, and other journals. And it takes time, and if somebody is interested, in helping in, being a editor of a special issue, please let us know. We definitely welcome help. I know actually when I collaborate with Michael and Angle on a book, I mean, it took a lot of coordination, a lot of effort, took about over a year and so on, and to just come up with the book. So we definitely welcome contributions and help from the community. As I said, like, so although it's one-day workshop, but trust me, if you look at the number of emails we received and how many emails we answered, it's a lot, so I want to take your feedback also about some of you submitted papers. Maybe some papers were rejected or others were accepted. what about the quality of the reviewers, the reviews? Were you satisfied? I mean, please feel free to talk loudly about this. One of the requirements is to basically keep the reviewing process, reviewing quality high, as Michael actually mentioned early in the morning. If you have any feedback, please, share it with us. So
Yeah, actually for the reviewing, paper reviewing, this year, CVPR uses the open review.
yes,
But we kept using the CIP with assigned reviewers. So maybe you have the opinion whether the open review could be better or only welcome.
that's good question. Yeah.
We will see next year. Maybe we're gonna be forced to use open review then.
What's your thought?
We are dependent on these deadlines from CVPR, so it's quite difficult to find a better way. Yeah. Ideally, yeah. Maybe it's time to come to an end.
All right. All right. So again, thank you very much for attending and staying with us till the end of the workshop. So enjoy CVPR, enjoy Vancouver, and hopefully we'll see you next year with more contributions. So thank you very much. Yeah, good job, man.
You can log out from the lights.
Yes, I think so. Goodbye to all the remote attendees who are still with us. See you next time.